Okay. Okay, good morning, everybody. So welcome to the second day of the conference. So before we start, I have two announcements. One is that if you would like to return to Prague back for scientific reasons, then in 2 years there will be a large conference, iChip 2024 in Prague. It's an international congress for energy physics. It's mostly high-energy experimental conference, but there are also theory sessions. And so this is the announcement for the conference. Now, the second kind of announcement, or the second information, is that we decided to kind of look back at historic records and ask the question. I showed this slide before. We have already kind of a record, long record of conferences. Who's the most frequent participant? So who participated in most Amplitudes conferences? And surprisingly, this is a complicated question to answer. And the reason for that is that there are some data missing from 2012 and 14 conferences. I got some data today morning from David Kosover about 2014. Maybe we'll be able to dig out also some 2012 data, which are no longer available. Something can be recovered from speakers list, but not from the participants list that no longer exist. So this is an interesting question. From the data I have so far, I kind of created a preliminary ranking of people, but this is in no way final. So if you don't see your name here and you participated in enough conferences, or you think you did, then just come to me. I will update the ranking, and at the end of the conference, we will announce the winner. So now, preliminary winners, or winner, the person who participated on all 12 conferences is nobody. Yeah. So we haven't found anybody in the list who made it to all 12 conferences. Okay, if you did, just come to me, and yeah, you will probably win, or for sure. But the preliminary ranking looks following. So we found 2 people who participated for sure in 11 out of 12, which is Henrik and Johannes. Then Einan and Gabriel, there are some data missing. It was 10 or 11, so that would be easy to figure out if they joined the leading group. Me and Lance participated in 10. David Kosover in 9, but then there is a larger group of people where it's not clear, something between 7 and 9. So in any case, if you participated in more than 9 conferences, yeah, please come to me, and you will be added to the elite club, yeah, into a frequent flyer Amplitudes group. Okay, that's all. Thank you. And so now we start the scientific program after some fun. And we will have the first out of 3 external reviews. So this will be for 45 minutes on adjacent fields which are of our interest. And the first review, which will be today morning, is by Dalimil Mazaj from the Institute of Advanced Study, who's an expert on conformal bootstrap. And okay, and does it work well? Okay. And he will talk about, or he will review us on the recent progress in dispersion relations in CFTs. Yeah, please.
Okay, does this mic work? Okay, great. Okay, so thanks a lot for the introduction, Jaro, and welcome everybody to Prague. As you may know, it is my hometown, so I hope that you're gonna like it here. And also let me thank the organizers for putting together this wonderful conference, and of course inviting me to speak. So as already advertised, I will talk about dispersion relations in conformal field theories. That's the pointer, yes. And as a means of motivation, which may be closer to the heart to the Amplitudes community, I'd like to start by discussing dispersion relations for the case of the S matrix. So the idea of dispersion relations for the S matrix is to reconstruct the amplitude from the imaginary part. Oh, it looks like there are some parts of the picture missing. Hopefully it won't be a problem later. Well, okay, so we have some 2-to-2 scattering amplitude, so some say scalar particles, A S of t, and we'd like to reconstruct it from the imaginary part. And why do we like that? Well, there are 2 basic reasons. The first reason is that unitarity imposes some nice positivity constraints on the imaginary part. So unitarity has a sort of a more direct imprint on the imaginary part rather than on the amplitude itself. And the second reason why we like dispersion relations is that the imaginary part is often simpler than the full amplitude. So for example, in tree-level theories, the imaginary part is just a sum over of the delta functions. Okay, how do we derive dispersion relations? So the basic idea in the case of the S matrix is to just write down a Cauchy integral formula where you express AS of t as a sort of closed contour around some value s. We're working at fixed t, and then you can deform the contour to pick up the discontinuities on the branch cuts. So in this way, we pick up the imaginary part or discontinuity on the U channel and the S channel branch cut, and this gives us the amplitude as in terms of the imaginary part. What are the ingredients that go into the derivation? Well, the first one is analyticity that allowed us to deform the contour like that, and that's really a manifestation of the physical principle of causality. And of course, there are many subtleties about analyticity. It's not really the full analytic properties of amplitudes are not really totally well known, but this won't really be a problem in the CFT case. And the second ingredient is the Regge bound, which is the statement that the amplitude is bounded by some power of s as s goes to infinity. In this case, I assume that the power is 0, but if the power is something positive, then you can still use subtractions to make things work. Okay, and now in today's talk, we somehow like to generalize this from scattering in flat space to scattering in ADS. So what's the idea? Well, just like the S matrix is the right observable the right boundary observable for flat space, the boundary observable for ADS is the correlation functions of the boundary CFT. And just like we can write down dispersion relations for the S matrix, we can also write down dispersion relations for the CFT, as we will see momentarily. And you can wonder, why is this interesting? For me, there are two possible motivations. One motivation is to implement the conformal bootstrap for holographic CFTs, so we'll see that in the second part of the talk. And second motivation is that these dispersion relations provide some fruitful interface between S matrix and conformal bootstrap method. So hopefully the two communities, the bootstrappers and the amplitudologists, can learn from each other in this setup. Okay, here's the outline of the talk. There'll be 3 derivations and 2 applications. The derivations of dispersion relations in position space, Mellin space, and using light ray integrals. And 2 applications, one to bounce on ADS effective field theories, and one application in the planar unequals for super-Young mills. So the first part is going to be a bit formal, so please bear with me, but I really believe that in this case of dispersion relations, it was really important to get the formal part right before we were able to apply to these nice, exciting ideas. Okay, so derivation number 1 in position space. So let's start with the very basics. The first question is, what is the analog of the amplitude? Well, it's just the 4-point function of the boundary correlator. So let's just take some 4 scalar operators. And thanks to conformal invariance, the 4-point function can be written as such, where G, U, V is a function of 2 cross ratios. So U and V are these conformal cross ratios. And what can you do with it? Well, most importantly, you can expand the correlator using conformal blocks, using the OP of the 2 phi, of the operators phi and phi, where the expansion involves this OP coefficient squared and the conformal block, which is some known function of the scaling dimension spin and the conformal cross ratios U and V. And you can do this in 2 inequivalent ways, using in the S channel and the T channel, and the equality of these two expansions is really the main sort of equation in the rest of the talk is the crossing or conformal bootstrap equation. Okay. Now, just like analyticity is important for S matrix dispersion relation, it's also important for CFT correlators. So what are the analyticity properties of the correlator? It's best understood if we pass 2 variables z and z bar, which are related to U and V as follows. So in Euclidean signature, z and z bar are complex conjugates of each other, and in Lorentzian signature, they would be independent and real. But in general, the amplitude, or the correlator, is a function of z and z bar as independent complex variables. And it can be shown rigorously that it's analytic in this doubly cut plane. There's a cut at 0 and 1 in both z and z bar, and everywhere away from these cuts, the correlator is analytic. Let's discuss some interesting limits in this parameter space. So first, the OP limits, the S channel when z and z bar go to 0, T channel when both z and z bar go to 1, and the U channel OP where z goes to infinity in the upper half plane and z bar in the lower half plane, which leaves the very, very interesting and important limit, which is the Regge limit, or in particular the U channel Regge limit, where both z and z bar go to infinity in the same half plane. And an important property characterizing this Regge limit of a correlator is the Regge intercept or Regge spin, which says that the correlator is bounded by some power of z in this limit of large z, where the power is j minus 1. J is this Regge spin or Regge intercept. And non-perturbatively, we know that j is always at most 1, meaning that the amplitude itself is bounded. All right, so having discussed the analog of the amplitude, let's understand the analog of the imaginary part. So the analog of the imaginary part of the amplitude is the so-called double commutator, or also known as double discontinuity, denoted d-disc. So the double commutator is computed in Lorentzian kinematics, where you put the 4 operators in this causal region, where 1 and 2 are time-like separated, 3 and 4 are also time-like separated, and all the other pairs are space-like separated. And this maps to the region where z and z bar are both negative, and the double commutator is just the discontinuity in z and z bar simultaneously. So it consists of 4 terms when you expand the commutator, and it's really just the discontinuity in both z and z bar on this right branch cut. And there are some important properties of this double commutator that I'd like to highlight. One of them is when you take a d-disk of a conformal block, you get this sine squared factor, which suppresses all the double trace operator. So the d-disk of every double trace operator is 0, which is somehow the CFT analog of the statement that the discontinuity of all contact diagrams vanishes. And the other important property is positivity. So in unitary theories, the double commutator is positive in this kinematics. So these are completely analogous to what happens for the imaginary part of the S matrix. Okay, just for completeness, we can compute the S channel double discontinuity. So that's the one that I wrote on the previous slide, where we have a commutator of 1 and 2 and 3 and 4 in this kinematics. But there is also a T channel double commutator, which is obtained by some permutation, where we have a commutator of 2 and 3 and 1 and 4 in the correspondingly permuted kinematics over here. And that corresponds to computing the discontinuities in z and z bar on the right-hand branch cut. Okay, very good. So having discussed the amplitude and the imaginary part, let me discuss the dispersion relation. So this was first written down by Carmen and Carnot, and in a slightly more indirect way in this other paper. So what Carmen and Carnot did in 2019 is that they basically proved a theorem which says that suppose that the Regge intercept of the correlator satisfies that it's negative, then there's a formula for the full 4-point function as an integral over the S channel double discontinuity and plus the T channel double discontinuity. So we are integrating over a pair of cross ratios, W and W bar in both cases, and we are obtaining an amplitude as a function of 2 cross ratios. So this kernel is a function of 4 cross ratios. They are rather complicated but explicit functions, Ks and Kft. So there are some known functions involving elliptic integrals, which were found by a rather ingenious combination of computation, self-consistency, and guesswork in this paper by Simon and Dean. So it leads to some natural question. One question is, how can we derive the dispersion relation more systematically without employing some guesswork? And secondly, physical theories only satisfy the weaker condition that the Regge intercept is only bounded by 1, not by 0, like as assumed here. So we need to introduce subtractions. So how do we do that? And it turns out that the best way to answer these questions is to go to Mellin space, which is the second derivation of dispersion relations. Okay, so in Mellin space, we introduce a new object, which is the Mellin amplitude. It's this ms of t, where s and t are basically like Mandelstam variables. And there's a formula, the Mellin representation of the correlator as a double integral of the Mellin amplitude together with some extra, gamma factors, which make various formulas look nicer. And this Mellin representation is formally the inverse of the Mellin transform of the correlator, which is just a sort of double integral over the cross ratios, transforming you from uv to s and t. And the idea of introducing the Mellin amplitude is that it is a much closer analog of the scattering amplitude than the correlator itself. All right. So just to demonstrate why it's a good analog of the amplitude, here are some properties of the Mellin amplitude. Firstly, it satisfies crossing symmetry. It's invariant under switching S, T, and U. And secondly, we can understand discontinuities of the Mellin amplitude using the OPE. So if there's an operator O in the phi OPE, then this becomes a sequence of poles of the Mellin amplitude as such. So if there is this operator in the 4-point function with some OP coefficient like that, this implies that the Mellin amplitude will have a pole at this location, delta minus j plus 2m, and where m ranges over non-negative integers. So it's really a sequence of poles, and the residue is some kinematic polynomial, just like we would have in flat space, except this polynomial is slightly different from the usual Legenders, and the residue is also multiplied by the OP squared. So the analytic structure looks as follows. If we work at fixed Mandelstam U, there is a sequence of S-channel poles, or the sort of S-channel discontinuity, coming from the S-channel OPE operators, and there is a sequence of T-channel poles, coming from operators in the T-channel OPE. And the Regge bound, where we say that the correlator is bounded by some power of z, becomes a corresponding Regge bound on the Mellin amplitude. So it's just s to the j at large S at fixed u, or s fixed s plus t. Okay. So having discussed all of that, we can now think about dispersion relations. So the obvious thing to do is just to write down the simple single variable dispersion relation in Mellin space. So we write the Mellin amplitude as a contour integral, Cauchy contour integral as such, and deform the contour by assuming analyticity to pick up the infinite sequence of S-channel poles and sequence of T-channel poles. So we get a formula for the amplitude as a sum over S-channel residues and a T-channel residues. And this particular derivation, besides assuming analyticity, also assumes that the Regge intercept is negative. Okay. So how are the position space dispersion relation and this Mellin space dispersion relation related? Well, it actually turns out that they are exactly the same thing. So this is just the formula from the previous slide, and we can perform the inverse Mellin transform back to position space. And it turns out that we recover the original position space dispersion relation. So if we transform this to position space, on the left-hand side we just get the correlator, and on the right-hand side, the sum over S-channel poles becomes the integral over S-channel d-disk, and the sum over T-channel poles becomes an integral over T-channel d-disk. As a bonus, this procedure of Mellin transforming back gives us an explicit formula for the dispersion kernel, which, okay, it's not totally explicit. Well, it's completely explicit, but it's a bit hard to do this integrally in practice. But at least there is a constructive way of deriving the kernel from Mellin space. Okay, now this finally allows us to think about subtractions. So remember, so far we assumed that the Regge intercept is negative, but in general the amplitude does not vanish in the Regge limit, and we need subtractions. The Regge bound is that j is bounded by 1, meaning that the amplitude is bounded by first power of s, and this means that the single subtraction is enough in general. So a natural choice of the subtraction is to put a subtraction point at the first double trace operator and a symmetric pole in the T-channel. So, and use this sort of Cauchy integral formula, this subtracted Cauchy integral formula. And again, we can do the same thing as before and transform it back to position space to get a subtracted position space dispersion relation. And in this form, the position space dispersion relation is a theorem. So originally we can sort of derive this kernel using Mellin space, but once you have such a formula, you can rigorously go and check it that it's valid by sort of contour deforming in position space. There's a small asterisk on the theorem, which I'm happy to discuss later, but it's basically a theorem in complex analysis, this formula. Okay, so that's all very nice, but it's kind of formal. So how are we going to use it to learn something new about CFTs? So the thing to do is to expand the dispersion relation using the OPE. So expand the 4-point function on both sides of the dispersion relation using the OPE. So on the left-hand side, we just get the usual sum over conformal blocks. And on the right-hand side, we get a sum over these new objects, which have been called Polyakov-Radje blocks, where this P is the dispersive transform of a single conformal block. So the P is just a integral against this dispersion relation kernel of the double discontinuity of the conformal block. And this expansion is actually very similar to the idea in the Polyakov-Mellin bootstrap in various papers by Gopakumar, Kavirajsen, and Sinha, where they write the correlator as a sum over Witten diagram. So these functions are closely related to Witten diagrams. And now we have a rigorous proof that the 4-point function can be written either as a sum over conformal blocks or as a sum of these new blocks. Okay, so a way to think about it is that this equation is some new type of conformal bootstrap equation. Well, it's some new set of constraints on the CFT data, parameterized by U and V, which reorganizes the usual conformal bootstrap equations. And in the rest of the talk, we'll be using these constraints to learn some new things about CFTs. Okay, but this constraint as written is still quite complicated for general U and V. And the right thing to do is to expand it at small u. So just to take the OPE limit at small u of the sum rule, then we get a much simpler sum rule that has been called a B2V, 2 for 2 subtractions, and V is still the variable that is left undetermined in the dispersion relation, where there's a closed formula for what this sum rule does. It's just some very specific integral of the conformal blocks, but importantly with this extra factor of sign squared in front, which introduces suppression of double trace operator. So the crucial point is that B2V has double zeros on all double trace dimensions, 2 delta phi plus 2n plus j for sufficiently high n. So here's a plot of what a typical dispersive sum rule looks like. So it has these double zeros, which suppress double trace contributions from some point on, but for a small value of the dimension, there don't have to be double zeros at double trace operators. And this is very useful in many applications. I should also say that these types of dispersive sum rules have been first discussed in 1D CFTs in these 2 papers, and they were also used in Lucia's talk yesterday. But in the rest of the talk, I'll be talking about higher D CFTs. Okay, so that was derivation number 2, and finally, derivation number 3 uses causality and light ray integrals. So this is maybe the most physical one. Yeah. Very good. So let's just start from causality constraint, which is a statement that the commutator of 2 space-like separated operators is 0. And if we insert it into a 4-point function in the middle, we just get the usual crossing equation. Now, why is that? Well, the reason is that an OP of two operators converges or can be used if they act on the vacuum. So in the first term in the commutator, it's x1, x2 acting on the vacuum. We get the S-channel OP, and in the second term, in the commutator, it's x3, x2. So we get a T-channel OP. Okay, so this is just if we expand this in conformal blocks, we just get the usual conformal bootstrap equation. But to get the dispersive sum rule, we are supposed to integrate this. I'm supposed to go back. So to get the dispersive sum rule, we are supposed to integrate x1, x3 along space-like separated null rays. So in this picture, 2 and 4 are fixed, and 1 and 3 are being integrated over some null rays, where the null ray for 1, so there's supposed to be sort of a third direction perpendicular to the screen, where 1 and 3 are space-like separated. So there are really 2 null rays on top of each other here. Okay, so that's the formula over here. Just a double light-like integral of the correlator. And this naturally leads to the double commutator. The reason is that null integrated local operators annihilate the vacuum. This is because you can deform this contour to the upper half plane using holomorphy, using the fact that light cone energy is positive. So in the absence of this kernel, we can replace this double integral with this double integral. So we just replace the 4-point function by double commutator, because the second term in the commutator, x1 hits the vacuum, it's now integrated, so it goes away. So ultimately we get this integrated crossing equation, which becomes the dispersive sum rule, or also it's been called superconvergent sum rule. Okay, so that was without inserting the kernel, but we should really insert some extra kernel here, because it's necessary to ensure the convergence of the integrals. This is the same thing as the need for subtractions. So we need the kernel for the integrals to be well defined. And this causes the sum rule to not vanish on some light double traces. So the final result is a sum rule that's a sum over all the operators in the OPE of f squared times omega, which is the sum rule acting on conformal blocks that looks as I showed before. And this object, in general, has double zeros on all the double traces with sufficiently high n. And any omega with this property, so with the property that all double traces with high enough twist are annihilated, is called a dispersive sum rule or a dispersive functional. Very good. So that's the end of the more formal part, where I gave you 3 different derivations of the CFT dispersion relations. And now we are finally ready to see some cool applications of them. So first application is bounds on effective field theories in ADS. Just first a few comments about holographic CFTs. So in general, a holographic CFT, well, what's a holographic CFT? Well, in general, you can say that any CFT is some quantum gravity in ADS, but this is most useful in the regime where gravity is semi-classical, meaning that spacetime is large in Planck units. So L ADS times M Planck is much greater than 1. And in this case, the excitations whose energy is well below M Planck just consist of a collection of weakly interacting particles, like the graviton and there can be other light particles in your EFT. Now what does this mean about a dual CFT? The graviton maps to the stress tensor, and the 2-point function of the stress tensor, also known as the central charge, must be large. The other operators, well, there are single particle states which map to single trace operators, and multi-particle states map to multi-trace operators that look like this. Strictly at infinite C, we just get a mean field theory. So it's a collection of non-interacting single trace operators. And when we deform away from infinite C, the double trace operators are going to develop anomalous dimensions that are suppressed by 1 over C. So they'll look like 2 delta phi plus 2n plus j plus some corrections of order 1 over C. And the point about dispersive sum rules is that they naturally incorporate the structure by suppressing the double trace anomalous dimensions. So they are somehow naturally made to implement conformal bootstrap in the case of holographic CFTs. Okay, so let's consider some UV complete theory in ADS, which is dual to some boundary CFT. At low energy, we just have general relativity with this action. But if we look a bit closer, there can be higher derivative corrections, such as alpha 2 r squared, alpha 3 r cubed. And let's think about these higher derivative corrections, the alpha 2 and alpha 3. Our dimension analysis would tell us that they are suppressed by inverse powers of the EFT cutoff, M gap, which is the scale of new physics. And in the language of CFT, this becomes the delta gap, which is a scaling dimension of the lightest single trace operator not included in the effective field theory. And the question that we'd like to ask is, why can't these higher derivative corrections not be large in the units of the UV cutoff? So why cannot it be, say, 10 to the 10 or 10 to the 100 with the appropriate power from dimension analysis? So this question was partially answered in this very nice paper of CEMZ, where they show that if these corrections are much larger than 1, they lead to a causality violation. But the new precise goal is to derive exact bounds on these order 1 coefficients. So for example, for alpha 3, we'd like to be able to say that it's bounded from below and above by some order 1 number that we'd like to find times the right power of the UV cutoff. So in particular, if one can derive such bounds, this would be a proof, or it would go a long way towards a proof of the conjecture of HPPS that a large central charge and a large delta gap in a CFT imply bulk locality. Okay, so let's think about this in a sort of a toy model where there's also a scalar coupled to gravity, where the scalar has higher derivative interactions, G2 with 4 derivatives and G3 with 6 derivatives. So the holographic dual CFT would have 2 light single trace operators, some scalar field dual to the scalar phi and the stress tensor. And the EFT couplings, G2 and G3, are encoded in the double trace anomalous dimensions, these gammas, which are anomalous dimensions of the double traces. And we can derive constraints on these couplings by applying dispersive functionals to the bootstrap equation, which is just causality, like I explained before. And the reason this works is that the dispersive functionals will extract the EFT couplings and relate them to the OP contributions of the heavy states, about which we are agnostic, except that they come with definite signs due to unitarity. So the logic is very similar to usual dispersive arguments for the S matrix, but now implemented in the conformal bootstrap. More concretely, we take the 4-point function of the scalar, and we can write as a sum over conformal blocks, and split it into the IR part of operators below the UV cutoff and the heavy part above the UV cutoff. And when we apply the dispersive functional, split it into the IR and the UV contribution as such, and the sum rule coming from the bootstrap tells us that the sum of the two must be 0. Now the crucial point is that the IR part of the dispersive sum rule is computable in terms of the EFT coupling, so G2 and G3 and the Newton's constant. Okay, so that's the IR part, and about the UV part, we can choose the functional omega such that it's non-negative on all the UV operators. So when we do that, we get the inequality coming from the sum rule that the IR part must be non-positive, and this inequality immediately gives us bounds on the couplings. Eventually, we optimize over the choice of omega satisfying these properties to find the best possible bounds. Okay. What happens in practice is that it's useful to think about the flat space limit of these constraints. So in a flat space limit, the 4-point function just becomes the S matrix. The IR part, well, we can expand the amplitude in the IR. There is a graviton exchange, and G2 and G3 are 2 contact diagrams of weight 2 and 3 in the STU variables. And the causality constraint in the CFT, which is just a sum over the IR and the UV part, maps exactly to the S matrix dispersion relation, where we write 0 as an integral over a large circle, deform it to get the sum over some IR contribution and the UV contribution. And this is, of course, this idea of using these constraints to prove bounds on EFT couplings has a long tradition in the S matrix, in the S matrix community. And the strategy for the CFT is to first find the optimal flat space bound using semi-definite programming, and then show that it can be uplifted to an optimal functional in ADS. So we are sort of using the S matrix argument to provide optimal functional in ADS. Here are the results. At the leading order at large delta gap, the result is the same as in flat space, as I just explained. So everything to the left is excluded, and the different curves correspond to different space-time dimensions. And you see that the two variables are really the dimensionless combinations of delta gap and G2 and G3. But in ADS, this picture gets some 1 over delta gap corrections coming from a finite size of ADS, and it's still an open problem to determine the systematics of these corrections. Okay, in the last 10 minutes, I'm going to discuss a newer application from this year to planar n equals 4 super Young mills. All right. So let's think about the ADS analog of the Virasoro-Shapiro amplitude. Let's consider the 4-point function of the stress tensor supermultiplet in n equals 4 super Young males with central charge C, which is related to n of SUN as n squared minus 1 over 4, and some Toft coupling lambda. And this set of 4-point function of the stress tensor supermultiplet is determined in terms of a single function of two cross ratios U and V, which itself depends on the central charge and Toft coupling. And let's expand it in the Toft limit at large C and fixed lambda. So infinite C, there's just the disconnected part, which doesn't depend on lambda. And what we'll care about the most now is the next order, which goes as 1 over C, which is the sum over all planar diagrams in n equals 4 super Young males. So this is the planar 4-point amplitude at some fixed value of lambda, which holographically is dual to the full sort of string, the full string scattering amplitude at genus 0. It's sort of an integral over all the world sheets with genus 0 in ADS 5 times S5. So really this planar amplitude, GUV of lambda, is the ADS version of the Virasoro-Shapiro amplitude, for which there is a closed formula. But we don't have a closed formula in ADS. So that's because there's an extra dimensionless parameter, which is just the Toft coupling, which measures the size of ADS in string units, where at small lambda, the amplitude is controlled by perturbative Young males, and at large lambda, it comes from supergravity with stringy corrections. So as I said, currently, there's no closed formula for this Virasoro-Shapiro amplitude in ADS for general lambda, and we'd like to use the bootstrap in combination with other techniques to learn some new information about it and maybe eventually fix it. Okay, so some extra useful information is the OPE. We can decompose the planar correlator using conformal blocks. There is a protected part, which is not too interesting, but the interesting part is a sum over single traces and double traces. These single trace operators, they correspond to massive string modes, which famously have scaling dimensions that go as lambda to the 1/4 at large lambda. And these dimensions are in principle available from integrability. For example, the quantum spectral curve can determine these dimensions. On the other hand, the OP coefficients, f² of the single trace operators, are not known at finite coupling. There is the hexagon approach, but the hexagon approach to integrability, to 3-point functions in integrability, is only really useful for long strings, for long operators, and not for these short strings. So there's no known way to fix these f's, and the hope is that using the bootstrap, we can do that. All right, so the first type of bootstrap result is trying to understand stringy corrections from dispersive sum rules, which is based on this recent paper of Aldai, Hansen, and Silva, where they first passed to the Mellin amplitude. So M is just the Mellin transform of the planar amplitude, as I discussed before. This Mellin amplitude has poles at the unprotected stringy modes, the single trace operators, as such. And we'd like to understand the systematics of corrections to supergravity at large lambda. At infinite lambda, the Mellin amplitude is just the answer in supergravity. And then there is a sum over contact diagrams, S² plus E² plus U² and STU, which come with the appropriate inverse power of lambda. So this is just determined by dimensional analysis. This comes from integrating the stringy modes. And each such vertex is itself multiplied by some infinite series in 1 over square root of lambda. Okay, so to determine the Virasoro-Shapiro amplitude in ADS is like determining all of these alphas, betas, and so on. The flat space limit fixes these alphas, the leading terms. So for example, alpha A0 is determined using the zeta function gamma as such from the flat space Virasoro-Shapiro amplitude. And let's try to go beyond the alphas. So dispersion relations express the alphas and betas as sums over stringy modes. And by combining that with integrability, flat space limit, and localization, these gentlemen were able to derive I think this thing may be a bit low on battery. Oh, there we go. So they were able to derive a formula for this leading correction beta to the Virasocial per amplitude using some closed form of using zeta functions and the gamma function. Right? So that was at expansion and strong coupling. And let's think about the problem at finite coupling, at finite lambda. And this will be based on the recent paper of Karanuot, Kornado, Trin, and Zarai. So they focused on the Konishi multiplet, which is somehow the lightest scalar unprotected operator in this OPE, whose dimension is available from integrability. Looks as follows compared to the perturbation theory at weak and strong coupling. And we'd like to learn about the OPE coefficient of Konishi, which is not known from integrability at the moment. And the idea is to prove an upper bound on this OPE coefficient at finite coupling using unitarity and crossing. Now, this is similar in spirit to the bootstrapability program that was put forward in this paper by Cavaglia and Gromov, Julius, and Prady. However, the problem with implementing this is that the double trace contributions in the OPE violate positivity. It's only the single traces which are positive. So we need to get rid of the double traces, and the way to do it is using dispersive sum rules, which completely remove all the double traces because they have those double zeros that annihilate all double trace contributions. And this is actually possible only thanks to the better than usual Regge behavior in n equals 4 with n equals 4 supersymmetry, that you can remove all the double traces. When you do that, you get these results. So these authors were able to find an infinite family of dispersive sum rules, omega I, which only receive a protected contribution and a contribution from single traces, and then using fairly standard numerical bootstrap techniques, together with spectral input from integrability, determine bounds on the Konishi OP coefficient. So for example, at weak coupling, 0.1, they get this bound, which compares very well with 5-loop perturbation theory, so the method seems to work. And then at strongish coupling, which is 0.3, but by the way, boundary between weak and strong coupling in this variable is 0.25. That's where the weak coupling perturbation theory stops converging. So for 0.3, which is in a strong coupling regime, they get this bound, 0.299, which lies inside the window known from other methods. But this window is fairly large, and it would be good to improve this estimate better. But the question still stands. The question is this bound actually exactly saturated by the planar n equals 4 super-Young Mills for any lambda? Okay, so that's, let me summarize what I've said so far. 4-point functions in conformal field theories admit a dispersive representation in terms of the double commutator. When we use the OP inside the dispersion relation, we get a large class of constraints on the CFT data, which are known as dispersive sum rules. In holographic theories, these sum rules suppress double trace operators and express higher derivative couplings as positive sums over single trace operators. And this can be used, firstly, to systematically implement positivity bounds on ADS EFTs, and it also teaches us some new facts about the Virasoro-Shapiro amplitude in ADS. There are many additional topics related to dispersion relations, which I didn't have time to discuss today. Maybe the largest of them is their use to implement perturbation theory. And some aspects of that were discussed in Agnes's talk yesterday. There are also completely STU symmetric dispersion relations of Gopakumar Sinha Zahed. You can think about dispersion relation in momentum space, which is also very interesting, for multiple correlators, and for boundaries, defects, and 1D CFTs. And I'm sure there are many other topics that I forgot to mention. And finally, in terms of future directions, it would be great to develop dispersion relations for higher point functions, which would allow us to study multi-trace operators in CFTs. Also, put spin on the external operators that would allow us to constrain graviton scattering in ADS. Another interesting topic is to study dispersion relations in CFTs in the flat space limit, and use it to understand elasticity properties of S matrices, which was really the subject of Lucia's talk yesterday. And finally, something that I think is very interesting is to generalize dispersive sum rules to exhibit double zeros not at the non-interacting double traces, but at interacting double traces. So to give some anomalous dimensions to the double zeros. and use it to prove optimal bootstrap bounds for interacting CFTs. So that's all. Thank you very much.
Yeah, thank you very much for a very nice review. Any questions for Dalino? Lance?
Yeah, thanks for this great review. It's fantastic. What about going further away from just local operators? In planar n equals 4, we like Wilson loops or things that are hybrids, like form factors and so on. Is there any chance you can apply extensions of these techniques to those quantities?
Yeah, that's a great question. Let's see. Well, I think there are some partial results for other types of correlators. I think there are, for example, inversion formulas and perhaps dispersion relations for thermal correlators, like the two-point function, the thermal two-point function. So that's a type of correlator which has been studied, but nothing else to my knowledge. It's certainly possible. You know, as long as you can define a good analog of the imaginary part, then you should be able to write on dispersion relation. But that's all I can say at the moment.
More questions? Martin.
Do you get some extra mileage from the dispersion relations in case of 2D CFTs?
It really hasn't been explored, and it should. You can ask what happens to these, for example, to these ADS positivity bounds in ADS3, and I don't think, well, yeah, I'm afraid I don't know if dispersion relations have been used in 2D CFTs. But sort of, yeah, all the analytic results that I'm aware of in 2D CFTs, they seem quite disconnected from dispersion relations. But, it'll be interesting to think about it further.
Okay.
Yeah. Sorry.
Thank you.
Okay, any more urgent questions? If not, thanks Daniel again. So thank you. And we will move forward to Shi, who came to Prague with a heretic title of the talk. So he wants to persuade us that off-shell is good and on-shell is bad, I guess.
Okay, thanks very much for the invitation to speak. So I'll tell you about some recent work on trying to systematically formulate the effects of D instantons in superstring theory. As you'll see, string field theory is going to be a crucial ingredient for the story. I'm going to be mostly talking about this recent paper. The paper is a bit long, but the most important part is actually hidden in a subsection, which is going to be the focus of this talk. There's a bunch of related work in parallel, and I should particularly emphasize the work of Ashok Sen over the last couple years. In fact, we started this project before Ashok Sen's recent work on string field theory approach to instantons, and we could only finish this project thanks to Ashok's insights. The worldsheet formulation of string theory, often said to be just perturbation theory, is actually more. And in fact, this is what was already pointed out by Joe Polchinski way back in '94, even before he understood the role of D-branes. So he pointed out at the time that there are these D instantons which should be responsible for some set of non-perturbative correction to closed string scattering amplitudes. And so in addition to the usual genus expansion of closed string worldsheets, you should also have a d-instance expansion, the capture effects of order e to the minus 1 over g string, the string coupling. It schematically looks like this. So the d-instance can be thought of as a d-brain-like object that is localized in both space and time. Represented by this red dot here. The closed strings can go in and out of the, get absorbed or emitted by the d-instance. And the actual worldsheet diagram looks like the following. So in all these diagrams I'm drawing, these are supposed to be worldsheet surfaces with boundary. The boundary represented by the red curves, which are subject, so you have a CFD on the worldsheet. These boundaries are subject to a boundary condition. All of these different red curves, red lines, all actually, sorry, so this part is not supposed to be a red, this that's supposed to be a handle. Anyway, the red boundaries are supposed to be subject to a specific boundary condition that is governed by this d-instance. Now, if you move the position of d-instance, you're going to change the boundary conditions here. So you have some disconnected, generally disconnected diagrams, which are empty with no closure insertion, and then you have diagrams with appropriate closure insertion. So this set of diagrams here represent some d-instance correction for the, let's say, 2-2-2 closed ring scattering amplitude. Now, this is a bit schematic. Now, in order to, so roughly speaking, you expect, this was what Joe thought in 94, you're supposed to sum up such diagrams and perhaps integrate over the moduli space of the boundary condition, and that's supposed to give you the d-instance contribution. Now, there are some important questions as to what extent these contributions are meaningful and to what extent they correct the perturbation theory, and I'll come to that later. Okay, so now the most naive thing one might try to do, following your nose, is to just do the usual on-shell perturbation theory, but now with worldsheet with boundary. And that has been attempted, I would say, since the 97 work of Green and Gutperl until recently. This approach sometimes can give you sensible results, but it has a few deficiencies. It has, in specific, I'll talk about three deficiencies of this on-shell approach. The first is just that actually, in this way, already it was seen in the pioneering work of Green and Gutperl in 97, there is no a priori prescription to determine the normalization of the measure on the d-instance moduli space. This is in contrast to, let's say, if you start with a quantum field theory path integral, you can find the instanton field configurations and expand around that and derive the measure. In this case, nobody tells us how to do that. There's no formalism for determining the measure in this on-shell approach. But nonetheless, if you just assume that there's some unknown but universal normalization, say for the one d-instance contribution, then Green and Gutperl went ahead and calculated the leading one d-instance contribution to the full graviton scattering amplitude, which is actually captured by this diagram. This diagram might look a little surprising. If you haven't thought about this, you might think it's a single disk, but actually, even though the diagram looks disconnected, but it's actually a connected amplitude because the four disks are tied through their boundary conditions, which then you integrate. And when I say integrate, you're supposed to integrate over both the bosonic moduli, which parameterize the location of the instantaneous space-time, as well as the fermionic moduli, which are represented by the insertion of the spin fields on the boundary. So anyway, Green and Gutperl calculate this up to normalization. The calculation, the result was correct up to normalization. Unfortunately, the result was actually fixed by supersymmetry. So you could have guessed that without computing these diagrams directly. Well, it was nice to get that, but they couldn't fix the normalization. But instead, the normalization can be indirectly determined by demanding consistency with S-duality. And that was essentially what was done. Now, in a kind of, I would say, a philosophically parallel story, a few years ago with Bruno Balthazar and Victor Rodriguez, we studied the d-instanton effects in the two-dimensional non-critical C=1 string theory, where, for example, you can consider the closed string amplitude of one closed string coming in, bouncing off the Liouville wall, going back out. There are these non-trivial d-instanton effects which one can calculate similarly. In this case, once again, we do not have an a priori string theoretic way to determine the normalization in this naive Anshau approach, but we were able to fix the normalization by matching with a proposal of the non-perturbative completion of the dual matrix model. And once you fix that normalization, it passes many other non-trivial tests. But this was still about the Anshau approach, and the gist here is that the normalization, while you know, it's we don't maybe cannot derive from first principle, but you can determine it by some duality argument that it's supposed to be universal in these string theories. This you know, in the string field theory approach of Ashok-Sen, there is in fact a first principle way to determine the normalization, but I will not review that in detail in this talk. The second point is, which I think is slightly more crucial, is that there are typically open string divergences in these Dinsenthal computations, as already noted by Polchinski back in 1904. So even the most basic diagram with two closed string insertion on the disk actually is just divergent. It's divergent because there's a limit, so you have to integrate over the moduli of the surface, and there's a limit where the surface pinches, and you get a contribution from a open string propagator, but this open string is there's open string modes that are always on shell. Remember the Dinsenthal, these open strings are, they live on the Dinsenthal, which has no world volume. It's a 0 plus 0 dimensional world volume. So if it's on shell, it's always on shell. And the propagator is just literally 1 over 0. So that doesn't make any sense. But that's what you would find if you actually do the naive on shell computation. So this is divergent. Now, it was pointed out in Zhou's 94 paper that actually there's a mechanism for cancellation of this divergence. This divergence will get canceled against a diagram of different topology. So this is a bit like the Fischler-Susskind mechanism in the closed string context, and we have been calling this the Fischler-Susskind-Polchinski mechanism. Now, while Zhou explained that this cancellation occurs between diagrams of different topologies, in order to actually carry out the practical computation, you have to choose some regulation scheme, let's say cutting off the moduli space near the boundary of this surface versus that surface. And it's not obvious how to choose this cutoff near the boundary of the moduli space of surfaces consistently for surfaces of different topologies. So this is now something like string field theory, because string field theory in particular will give a consistent way to decompose the moduli space. In practice, there will be this finite ambiguity depending on the scheme. This problem was already noted in the work of Green and Guthbrough back in 1997, but it was unresolved at the time. In the work from a few years ago we did on the 2D C+1 string theory, we also noted this ambiguity, and we fixed it by comparison with the proposed dual matrix model. There was no a priori worksheet way to fix that. But this ambiguity was then resolved in the subsequent paper very elegantly by Ashok-Sen using open plus closed string field theory for the Dinsenthal in this 2D string context. But the scheme of Ashok proposed is very general, and I will discuss its application to superstrings. And a third deficiency I want to mention, which is actually a bit curious, is just the fact that usually, very often you expect the integration over the moduli space of these Dinsenthals to have singularities. Now this is not surprising. You also have this issue in ordinary quantum field theory, and in fact actually you can often run into trouble when the instant moduli space is complicated, and you have to, it's not obvious how you can resolve it, and when the instant moduli space is singular in the ordinary quantum field theory context, it indicates a breakdown of the sort of the semi-classical approach to the instantons, and it's not clear how to resolve that in general. But string field theory somehow is smart. So you can have a situation where, well, okay, so let me first contrast the fact that in the on-shell, what I call the on-shell approach, you typically compute some diagram like this and with some boundary condition, and we integrate over the moduli space, which roughly speaking can be viewed as the moduli space of exactly marginal deformations of that boundary condition. So it's a moduli space of deformations of boundary CFT. In string field theory, you don't do that. In string field theory, you never deform the boundary condition. You always choose a boundary CFT to begin with, and the open string fields live in the Hilbert space of that boundary CFT. And instead of integrating over the moduli space, you're integrating over open string fields. So these two things are not the same, but they're closely related through this, the notion of background independence of open string field theory. And this has interesting application to multi-instance contributions, which naively would look singular from this approach. The integration of the moduli space looks singular, but when you view this as a path integral over open string field, due to the non-abelian nature of open strings, the singularity gets resolved. Okay, now let me come to the actual particular observable that I'm going to be focusing on, which is the 2-to-2 supergraviton amplitude in type 2B string theory in 10 dimensions, which we believe is non-perturbatively well defined. And as well known, thanks to supersymmetry in this case, it is factorized into just the supergravity tree-level classical amplitude multiplied by a single scalar function, which is a function of S and T Mendelssohn variables, as well as n tau and tau bar, which are the moduli that parameterize the type 2B Minkowskian vacua. You can think of this tau as expression value of the axion dilaton field. And in particular, the imaginary part of tau is the inverse string coupling, as usual. So it is also well known, I think, particularly to this audience, that this function m, the scalar function, has the following form. It starts with 1, that's the supergravity limit, and then plus STU times some function of just tau and tau bar. These STUs, when I write underline, these are in Planck units, but from string perturbation theory perspective, it's also useful to consider some other combination, alpha prime S. But anyway, viewed as a derivative expansion or momentum expansion, it starts with terms like STU times a coefficient, which is a function of the type 2B string moduli of vacua. This first coefficient, for example, is the well-known coefficient of the so-called R to the 4th effective coupling, and this function is known exactly through a combination of supersymmetry and the soft theorem arguments. And then the higher order terms, which will generally may not be analytic at 0 momenta, and they also may not be BPS protected. Now, in the string perturbation theory approach to this, one would organize this M according to a different expansion. So you start with a perturbative expansion in 1 over tau 2. So this is the usual genus expansion here, where this MH is the genus H perturbative string amplitude, which is well defined as a function of S and T. And then one might expect some kind of instanton sum, where here I'm writing kind of schematically a sum over a contribution from the instanton with some charge I call n comma m. So this is kind of like having n regular d instantons and m anti-d instantons. And I wrote the quotation mark in this sum because it's not a priori obvious to what extent there's a sense in which the sum is meaningful. Because as well known, you might expect that the perturbative expansion is asymptotic series, in which case the usual prescription is that you have to choose some way to resum, say some kind of Borel resummation, and the instant contributions are supposed to be corrections on top of that Borel resummation. In fact, that's exactly what happened in 2D string theory. But in the case of type 2B, I'm going to be discussing situations where I can pick out the specific momentum dependence where if I know the perturbative contribution is of a specific form and it doesn't interfere with the d-instant contributions of a specific type, and in those cases, the instanton contributions are unambiguously determined. And then there could be some gravitational instanton effects on top of that. I will not discuss that in this talk. But the point is that there are some d-instant effects, at least, that are unambiguously defined in this kind of expansion. So I'm going to focus for now on the one d-instant sector. So what I call n and m are 1 and 0. Now even with restricted one d-instant sector, there's still a string loopy expansion. And importantly, this loopy expansion is an open string loopy expansion. So there are expansions in powers of gs as opposed to gs squared, which is 1 over tau 2 here. So this L is the open string loop order. At leading order, this was a computation of Green and Gapro back in 1997, whose normalization was fixed using string field theory by Ashok Sen in 2020. And as I already mentioned, the diagram looks like this, except now I also have to insert these boundary spin fields, which correspond to, roughly speaking, integrating out the fermionic moduli of the instanton, and you can get some results, which is the coefficient of this R to the fourth term multiplying e to the 2 pi I tau, and this derivation of sense agrees with the prediction of S-duality. The focus actually of this talk is going to be on the next leading order, where new subtleties arise. So you have a diagram like this. So for the first time, you have a disk with 2 closure insertions. But then you can, just by counting of all that character, you'll recognize that there's a bunch of other diagrams of the same power of GS, such as the one with annulus, with 1 closure insertion like this, or just these 4 disks multiplied by some either a 2-hole disk or a 1-hole torus. Okay. So the result of this next leading order contribution, which I call M1,0 sub 1, this 1,0, remember, this refers to the charge of the instanton, and this subscript 1 refers to sort of quote-unquote the one-loop order in open string. And this we have determined, actually. So there's a constant piece, and then there's a momentum piece that goes in powers of STU. So actually, all this complicated diagram, this stuff has to go into the constant piece somehow. So all these zeta functions, this is actually the easy part. This part you can actually get without too much work with the on-shell computation, mostly come from this diagram. It's this constant part that was a bit of a headache that we mostly spent 2 years trying to figure out, even though we actually already knew the answer. The answer was that this constant piece is actually fixed by arguments, again, using supersymmetry and the soft theorem involving moving along the moduli space of type 2b vacua that determined to be some number, 3 over 256. But we were disturbed by the fact that the naive on-shell computation gave the wrong answer. You get some different number, but the point is that the naive on-shell computation was ambiguous anyway. We had to choose some arbitrary scheme, and it's not clear why that should be correct. And that would have been a little disturbing. So you might say that, why bother with all this work, because you can already fix it by some indirect arguments. The point is that to be able to reproduce this from a first principle computation would be a non-perturbative test of supersymmetry. It's not obvious that the type 2b vacua actually preserves supersymmetry at a non-perturbative level, and there's no alternative first principle way to determine this answer. But the claim is the string field theory will do this. But actually, I'm not going to tell you that we have successfully computed this C1 from string field theory, because this has all kinds of complication diagrams like this, and it has been a bit too difficult up to now to actually get the answer. But as often happens, when the problem is difficult, you can generalize the problem, and in the generalized problem, you might find a simpler part that you can solve, and that's what we did. So, to get this number from first principle computation proved to be still difficult, but you can generalize by considering an n-point maximal R symmetry violating amplitude of this sort. And roughly speaking, we're looking at the momentum expansion in the form some derivative acting out the axion dilaton, the holomorphic tau variation to some power n minus 4, R to the 4, this kind of terms. And in terms of the super language, in terms of the super amplitude notation, we just write this as a del 16q multiplied by some combination of the Mendel-Stern variables for the n-point amplitude. In particular, we'll focus on the 1 Dinsan contribution next to leading order, which goes like e to the 2 pi I tau, this from the 1 instanton, tau 2 to the minus 1, this from the open string 1 loop order, quote unquote, and the del 16q, and then you have some momentum dependence. And once again, all this momentum dependence actually was easy, and we determined this. There's some payoff to this, which we discussed in the paper, but I won't get into that in this talk. This constant, which generalized the C1 on the previous slide, is now 3 over 256 plus some quadratic expression in n, the number of particles, which you can then reorganize as a combination of 3 terms. One goes like n squared, the other one goes like n, and the constant term. So now it turns out that one can easily deduce by inspecting the combinatorics that actually this first coefficient only had to do with the disk with the 2 closure insertion, whereas all these complicated diagrams involving more complicated topologies only go into A2. And this A1 involves some further subtleties of open string field redefinition that I won't have time to discuss. But anyway, the point is that once you generalize this, actually we can calculate these 3 different constants, and the first one is actually quite easy. So this is the one we actually did in this specific subsection in our paper. So let me describe now in the remaining time how the string field theory works. So in the string field theory approach to the Dean-Sound effects, which was developed by Ashok-Sen in the last few years, the Dean-Sound contribution to the closed string effective action is captured by a functional integral over open string fields. So here I use psi c to denote the closed string fields, which you can take to be on shell if you wish, but this psi o are the open string fields. Thank you. What are the string fields? The open string fields, well, the string fields live, roughly speaking, in the quote-unquote Hilbert space of the worldsheet CFT with the ghosts included. Now that to call it the Hilbert space will be abuse of terminology because there's no positive semi-definite as definite inner product with the ghost sector included. What you have instead is a Grassmann-Odd symplectic pairing, which is rightfully interpreted as a BV anti-bracket in the sense of Batalin-Wierkowicki. In fact, as was explained beautifully by Barton and Zwiebach in the early 90s, the string field theory is most naturally formulated through the Batalin-Wierkowicki formalism. The reason for this is just that, I think most people are familiar with starting with a classical gauge invariant action and gauge fixed via Faddeev-Popov and get gauge fixed path integral with the ghosts. But if you think about it, the quantum gauge theory path integral is only meaningful after gauge fixing. There's no reason, a priori, why you should have the classical gauge invariant action to start with. The BV formalism is a machine that just lands you directly on the gauge fix of the path integral, but has all the right features that you like to have. And one of the advantages of that is the structure of the BV formalism is preserved when you integrate out some degrees of freedom, which is why if you open, say, Weinberg volume 2, you'll see that the BV formalism is useful in proving the perturbative realizability of Yang-Mills theory. The string field action is in some sense a Wilsonian action, and that's why the BV formalism is appropriate and actually quite essential for the full consistency of the framework. But anyway, the point here I just mentioned is that this string field action is a priori a BV action. The string fields include the so-called BV fields and anti-fields, and you have to choose a BV gauge condition to get rid of these anti-fields by choosing an appropriate Lagrangian subspace, which you call L, in this space of string fields with the symplectic Grassmann-Odd symplectic pairing. Anyway, the string field action includes some kinetic term involving the BRT charge acting on the string field. In the usual on-shell formulation, one also kind of works in some sense in the Siegel gauge. This is commonly adopted in string field theory, but in the Siegel gauge, the kinetic term for the string fields, say in this case specifically the open string fields, will actually vanish if the open string field corresponds to weight 0 operator in the boundary CFT. So if they have no kinetic term, then means the perturbation theory breaks down if you just want to perturbably expand in open string Feynman diagrams, as one would usually like to do. So there are 2 types of open string massless modes which give rise to this problem. One set of these open string modes are collective modes which are heuristically in correspondence with the moduli of the instanton. So one expects the integration of these open string modes to be turned into integration of the moduli space of the instanton, which is fine. But then there's some additional ghost modes. This is in the superstring context where you have the beta gamma system. And anyway, so there's some additional ghost modes for the open strings. And in the Siegel gauge, you actually run into a problem. This has to do with this 1/0 divergence of the propagator. But Ashok-Sen decided that the Siegel gauge was actually just bad. You had to work with a different gauge, which I call the Sen gauge. And in the Sen gauge, it turns out that the ghost zero modes have an interpretation as one of them is actually the Fourier-Popov ghost associated with fixing some U1 on the instanton, and the other one is something new that has a finite propagator. And so the point is that this additional, this new component open string field, which actually has a finite propagator that arises only in the Sand gauge and not in the conventional Siegel gauge, actually give rise to a contribution to this disk two-point amplitude through a string field Feynman diagram of this very simple form. It's kind of a two-point Feynman diagram with a single propagator and two vertices. It has no analog in the conventional Anschauer approach. To take this into account is absolutely crucial to get the correct value of this constant A0 that I mentioned at the beginning. And that was discussed in this particular subsection in our paper, which is why I said this was the focus. And so now just to recap, the main result I discussed in this talk, which is a part of the paper, is this specific contribution to this constant term in the 1 distance contribution to the 4-point graviton amplitude next to the leading order, sorry, not 4-point, the n-point MRV amplitude in type 2B string theory. And there's a specific coefficient which was predicted by supersymmetry plus soft theorems that was, can only be correctly calculated using string field theory. And this also serves as a non-trivial test of the non-perturbative supersymmetry of type 2B vacua. There are these additional coefficients A1 and A2, which are much more subtle, and we still haven't managed to produce that from string field theory, but that's work for the future. And I think they are important tests of the string theory formalism. I should say that I shouldn't give you the impression that all we can compute using string field theory are these things that are already fixed by some other integrated arguments. Generally, going to higher orders, one do expect terms that are subject to this kind of ambiguities that you require string field theory that are also not BPS protected in any sense. Thank you.
Yeah, thank you. Thank you very much for a very interesting talk. So before opening for questions, I have a very naive, maybe this is too naive, but you mentioned in the beginning that the kind of technical problem is 1/0 term that would naively appear in the on-shell approach. In the field theory scattering amplitudes, we also have problems with bubbles on external legs. So I wondered if it can be related to this.
Yes, thanks for that question. So first I should actually contrast this to the case of D instantons. Sorry, not D, ordinary D branes, where you also have similar diagram you can draw where the boundary end on the D brane, and you just have a closed string scattering off the D brane. In that case, of course, you have you have the open string propagator, and you have you can run into singularities, but we understand the physical interpretation of these singularities. But for the generic closed string momentum on shell, you will evade the singularity. Here, they cannot be avoided. Then the other kind of context of, say, like mass generalization or something, you would have you would naively run into these divergent propagators in the naive perturbation theory, which you are supposed to resum, and then it shifts away. In this case, I guess I'm not aware of such an approach. I shouldn't say that it's not possible to try to do that. In fact, I should also say that I chose this provocative title mostly because you see here the goal is to understand what the correct formalism is. It's not so much, or not so much concerned about the computational efficiency at the moment. And once you understand the formalism, you might be able to come up with a clever on-shell approach to this, but so far that clever on-shell approach doesn't yet exist.
Okay, questions for Xi? Martin?
So can you comment on the extra fields which remain there after the Siegel gauge fixing or the sense gauge?
Yeah. So let me see. So what I'm trying to say here is that the open string fields that would not have well-defined perturbation theory, so you cannot put them into a Feynman diagram. Potentially, the dangerous ones are these. In sense gauge, these bottom two are excluded. You have these two. One of them is understood as Faddeev-Pavlov ghost that one can handle. To explain this is a bit subtle, and this is a kind of elaborate story, but it can be treated. Whereas this guy here is something new. But actually, thanks to the fact that it's not in single gauge, it actually has a finite probability. The probability is in some sense 1 as opposed to 1/0. This has to do with the fact that the statement that the massless mode or the zero-weight states give rise to divergent propagator, that's only true in the single gauge. This relation this makes use of the single gauge. In sense gauge, this relation is just not true. And you can have a massless mode with a finite propagator. Quote-unquote mass. They can have a zero-weight states with a finite propagator. This you can just check is just true. Now these collective modes, these things, the point is that when you integrate them, you are not supposed to treat it perturbatively. You should not, so when you draw the Feynman diagrams of string field theory, you're not supposed to include the propagator of these guys in the Feynman diagram. Instead, you're supposed to view the integration over these modes, in some sense non-perturbatively, as actual integration over the modular space. Well, as I mentioned earlier, it's not exactly the same as the modular space. So if you choose some way to parameterize the inside modular space, say from boundary CFT, there may be a non-trivial field redefinition relating the coefficients of these open string fields and the actual moduli. And that field definition is non-trivial, and you had to determine that somehow. And that's closely related to this open string field background independence. So these are precisely the subtleties that will go into the computation of this A1, for instance, which is why this is much harder, and we're still working on that.
Thank you.
Okay. If there are no more questions, thanks Xi again. And let's go to the coffee break and reconvene at 11.
Okay, should we start? So the first speaker of the current session is going to be Paul Haslup, who is going to talk about internal boundaries of the amplitude.
Thank you. Okay, thanks very much. Thank you for the organizers in particular for this beautiful conference in a beautiful city and for the opportunity to speak. Okay, so I'm going to talk about a paper that came out the other day with my students, Gabriella Diane and Alistair Stewart, who have led a lot of the work on this. Okay, and the title is the main point is that there are what we call internal boundaries in the amplituhedron. So I'll basically explain what this means and various other aspects that I think have been missed in the amplituhedron until recently. Okay, so I'll start with an introduction. Most of you will have seen something like this before. I'll then sort of discuss in a little bit of detail what canonical form is and how it's defined recursively. And then point out a consequence of this is that maximal residues should all be plus or minus 1 for a positive geometry as standardly defined. But then we'll see that, in fact, the loop amplituhedron doesn't satisfy this requirement. It needs a generalization of the concept of positive geometry. So we define a generalized positive geometry, which in some sense is just a small tweak, if you like. But in fact, it has some slightly nicer properties, I would say. It's more complete in a certain sense. And then we sort of, it then suggests a slightly bigger generalization into weighted positive geometries. And these sort of feel like the nice object to be working with. They have a very direct relationship with the canonical form directly at the level of the geometry. So that's the main point. And then we'll sort of look at deepest cuts in relation to some of these things. Okay, so the amplituhedron. So I'm sure everyone's seen a slide something like this before. So the kind of toy model of the amplituhedron is polygons in P2, so two-dimensional projective space. And the idea is you think of what are the points inside a polygon. And obviously a point in a polygon lies to the left of the line 1, 2, and to the left of the line 2, 3, and so on and so forth. And in projective space, this to the right, I suppose, to the right of the line 1, 2 becomes this constraint. Y, I plus 1 is bigger than 0. Okay, so now there's another thing that you might notice that isn't really relevant in this case, but becomes so later, and that's that the set, sorry, ignore that plus, the set of brackets y1i has a so-called flipping number pattern. So y is to the right of the line 1, 2, to the right just of the line 1, 3, but then it flips and it's to the left of the line 1, 4, and 1, 5, and 1, 6. Okay, now this is not an additional constraint here, but it's just an observation. So it means that wherever y is, you start off with a plus, you finish with a minus, and there's one change from plus to minus at some point. Okay, so the amplituhedron then is really a very natural generalization of this. So obviously this was from Nima Akani Hamid, Yara Trinka, and then this flipping number version was also with Hugh Thomas. So this is the toy model that we just looked at, and basically just generalize things in a sort of a fairly natural way. So instead of living in P2, which is, you can think of as the Grassmannian of lines in a three-dimensional space, generalize this 1 and 3 to two arbitrary parameters, so k and k plus m. Then the z's also live in P2. This one you generalize slightly differently, so this may not be immediately obvious, but it's the right thing to do. This generalizes to m plus k minus 1. So this is the same space. So this is k-planes in k plus m dimensions. These are then lines in k plus m dimensions. And then the geometry itself are just these inequalities, defined by these inequalities, and they have a natural generalization. So in the case of interest in physics, m equals 4, but this amplitude exists as a mathematical object for any m. And for m equals 4, the generalization is like that. And then there's another thing which isn't immediately obvious from this kind of just trying to do the obvious thing point of view, is that the sign flip now becomes an additional constraint. So we said that y1i has one sign flip. For the amplituhedron, we have y123i has k sign flips. So that's the maximum possible number of sign flips. And in fact, there are other geometries where you can tweak the number of sign flips that I may mention briefly as well. Okay, so but basically, there's this amplitude ANKM. It's just a mathematical object, a geometrical object. And the toy model case is the case AN1, 2. Okay, and there's something called a loop amplituhedron as well. So I won't talk too much about this, but basically it's the same as before. It has this y, which is a k-plane, but it also has lines. It has L lines as well, and they satisfy various mutual inequalities. Okay, but it's just a geometrical object. In the end, these are just inequalities, and you can choose coordinates for them and put them on a computer or whatever. Okay. Well, okay, this is a bit too early. So far I've just talked about geometry. From the geometry, then, there's another ingredient that one needs, known as the canonical form. So from a geometry, you can extract this thing called a canonical form. It's a volume form, living in the same space as the geometry. Well, it's a form on that space. And here's some examples. A triangle is a 2 form, because I'm in a 2-dimensional space. In fact, this is pretty much the only thing you can write down in this case. But the canonical form for a polygon can then be obtained by summing the canonical forms of the individual triangles. And then a positive geometry is defined as a region possessing a canonical form. Okay, so I haven't defined the canonical form yet. I've just given you an example. I'll define it shortly. Okay, I also haven't mentioned anything to do with physics yet, apart from the bit at the end that got in too early. So the point is that the amplitude is the canonical form of the amplituhedron. And here's a nice example of that. That looks quite similar to the canonical form of the triangle. And in fact, this is the canonical form of that geometry I gave if you put in the parameters 5, 1, 4. And then similarly, the endpoint, so this is the 5-point NMHV tree amplitude in certain variables, certain quite natural variables. And then the endpoint case is again a sum of these guys. And again, that sum looks quite similar to this sum here, and it's just the natural generalization of that. Okay, so the amplituhedron, the canonical form of the amplituhedron gives you the amplitude. And the same is true for the loop level one that I gave you earlier. This is a bit of an aside, but it's stuff I also did with my student Gabriela Diane, is that if you then tweak the number of sign flips, then you get the canonical form of products of amplitudes, and you can make this all very precise. And in fact, if you just remove the sign flip constraint, then you get a sum of products of amplitudes which precisely give you the, what you get if you square, if you take the full superamplitude, square it, and then pick out a fixed n MHV degree and a fixed loop order. Okay, so what's the canonical form? Okay, the canonical form is defined recursively via its residues. So, first of all, it's a volume form and it has log divergences on the boundary of the geometry and no divergences anywhere else. The only divergences are on the boundary. And then the residue on any particular boundary component is given recursively by the canonical form of the boundary. So I've given a badly drawn illustration here, but I wanted to give an illustration with curvy lines because often they're given as straight lines, which is maybe a little bit misleading. So here's a geometry. It's just some region in some space. It has a boundary here. But this boundary can be defined by some equation, like a polynomial equals 0. So the equation extends further. The corresponding canonical form then must have a pole at f equals 0. And the residue of that canonical form, which you can just, well, it's just a residue, is given by a form df wedge omega, and then omega then is the canonical form of the boundary geometry. Okay, so the boundary geometry, which is this red line, has a region there, the white bit, and that has a canonical form, and that becomes there. And that must be true on all the boundary components, all 4 boundary components here. Okay, so that's a recursive definition. Obviously, you need to finish somewhere. So you finish at when you get to dimension 0. So eventually you reach dimension 0, and then the canonical form of a point is just given by plus or minus 1, where the sign is dictated by the orientation, and that you have to also take through the orientation, which gets induced onto a boundary at each stage. Okay, so I guess one point I want to highlight here is that a multiple residue, at least as far as I can see, is defined, or, well, certainly a way of defining it is a residue of a residue of a residue, where here I just mean a single residue. So residue, residue, residue of a residue, you have to say, in principle, you have to tell me the order and which residue I take in which order. That defines a multiple residue, and the geometry perfectly matches that. I should be talking about boundary components of boundary components of boundary components, and not necessarily of a co-dimension K boundary component, which you see a lot of. I mean, often this works, but in general, the boundary component of boundary component of boundary component K times of a geometry is not equal to the co-dimension K boundary component. So here's a simple example of this. So this is kind of a house with a flat roof and a slanty roof. I'd spent a few, well, probably too long searching Google Images to try and find a house that actually looked like this, but I failed. So anyway, so now you can ask what is the codimension 2 boundary corresponding to this line at the front? And I guess one natural answer would be AC. It's just the intersection of that line with the geometry. But if you're thinking of it of boundaries of boundaries of boundaries, then you get different answers. If I take the flat roof, codimension 1 boundary, and then the boundary of that, I get AB. And similarly, if I take the slanty roof, and then the boundary of that, I get BC. Or if I take the wall, and the boundary of that, I get AC. So I get different answers depending on, the final configuration is the same, but I'll get different answers. And that's perfect. The amplitude perfectly matches what the algebra does, because the algebra does the same thing. The residue of a residue of a residue gives different answers. Okay, so that's kind of one point that I think some people know about, but it hasn't really been emphasized very much in the literature. But now I want to go back to this point. So this point here means that all maximal residues, at least all residues of residues of residues of residues, eventually get me to plus or minus 1, according to this definition. So let's look at a simple example. Let's look at the two-loop MHV amplitude. Okay, so we all know what that is. It's just given by double boxes. If you rewrite it in this twister language, then a loop variable is A, B. I have two loop variables, so I've got A1, B1, A2, B2. Okay, either you know this or you have to believe me. This is what you get. Now I can just choose coordinates. So first of all, I can set the z's to the identity using a GL4, and I can choose coordinates on my loop variables like this. And then this just becomes the following, multiplied by dA1, dA2, dB1, dB2, and so on, because it's a form. And now I'm going to take various residues of this. So first of all, I'm going to take 4 of these residues. And I get, where do I have to point this? Okay, so I take residues here, 1, 2, 3, 4. Now here, the order of these 4 doesn't really matter. But you can easily check that you get this result. Okay, so that's fairly straightforward. Basically, this term gets killed and nothing else very interesting happens. But that term getting killed is interesting, right? This is a complicated residue. It's a non-composite residue. But when I kill that, it factorizes. Okay, so that residue is factorized, and I've got two new poles appearing, or one new pole, if you like. So now I take the residue in A1 equals A2, I get that. Now I take the residue in D1, D2, and I get that. Okay, you don't need to follow all the details, but you can believe me that this is the final answer. And now I can take a residue in A2 and then in D2, and I get the answer 2, or minus 2. The sign there is not so important. Okay, so what's going on? So it seems as if this is, the loop amplitude is not a positive geometry. Okay, but I mean, it's not that everything is wrong. Everything we know about the emptyhedron is still working fine. It's just that this recursive definition needs a bit of a look at. So let's examine what's happening geometrically then. So we have a geometry, we have the amplitude. Let's do exactly what we just did, carefully taking all the boundaries one by one. So if you take the boundaries corresponding to the 4 residues I did first, you end up with this geometry. Okay, and then you see this sort of factorized pole comes out as a factorized inequality. And the canonical form corresponding to this is precisely what we had before, right, at that stage. So we're doing the right thing. Now, look at this geometry. Now, because you can think of this as x times y is bigger than 0. X times y bigger than 0 has two regions. It looks like this. And the orientation is the same on both of them. These orientations given by the red lines is the same. Okay, so that's a picture of this boundary. And now consider the next residue, which is this one. I'm going to set d2 minus d1 to 0 and look at the residue, or the boundary there. And you see that that's the picture that we get. And this means that I have a region on that side with one orientation and a region on the other side with the other orientation. And this is what I mean by an internal boundary. So I've got an internal boundary separating 2 regions of opposite orientation. So in particular, this is not oriented, because it's orientable, but it's not oriented. I don't have a continuous orientation here. I have a discontinuity at that point. Okay, so in more general, an internal boundary then is what you get if you take two regions in 2 dimensions. I have a boundary here and I have a boundary here, and I put them together. So if you put them together and they're the same orientation, you have what's called a spurious boundary, which is no boundary at all. But if you have an opposite orientation and then you put them together, then you get what I call an internal boundary. And that's what's going on here. Okay, I'm probably going a bit slow, but this is a toy example of what I've just done. So this is a simple geometry, x, y plus z bigger than 0, z bigger than 0. This is what it looks like. You can see you've got these hyperbolas. For fixed z, I've got hyperbolas. This is the bottom looking up. So the base at z equals 0 is precisely the geometry we just saw. And then if I then look at y equals 0 boundary, I get this internal boundary. Okay, and it's related to a composite singularity. I don't know the precise. They always seem to occur with these composite singularities, which have been observed a long time ago before any of the Amplitudes business. But these are important. Okay, so that's the internal boundary. What do we do then? Well, we can easily generalize the canonical form to include an internal boundary. So now the recursive definition, before it just had this part, df wedge omega. Omega was the canonical form on the boundary. Now I have to distinguish between an external part and an internal part. Okay, and I put a factor of 2 next to the internal boundary. Okay, and then I carry on as before. So this is now the recursive definition. Okay, and here's an example. Here's a geometry, simple geometry, 2 triangles, opposite orientation. I can work out the canonical form just by adding the canonical forms of the 2 triangles. And then if you look at the residue when y is 0, so along there, then the residue on y equals 0 splits into sort of 2 pieces, which precisely give you the canonical form from there to there, plus 2 times the canonical form from there to there. Okay, so it agrees with the formula. And in some sense, these generalized positive geometries are more complete because the claim is that anything that triangulates in GPGs is a generalized positive geometry. Whereas this is not true for positive geometries themselves. For example, here's 2 examples of geometries which are not positive geometries precisely because they contain these sort of internal boundaries. But they're perfectly reasonable looking. And in particular, they triangulate nicely, but they're not positive geometries. Okay. But then this suggests a further generalization to what we're calling weighted positive geometries. So the idea here, looking back at this picture, the idea here is that this thing looks like I've got the geometry once here and twice somehow here. So let's put a weight of 1 there and a weight of 2 there. And let's introduce a weighted positive geometry. Okay, so it's basically, instead of defining my geometry is here, I define my geometry as it has a weight 1 here and a weight 0 elsewhere. But I can also have other weights, other integer weights. It's slightly more intricate because you have to, it sort of needs to talk to the orientation a little bit. So an orientation form you can think of as a volume form up to positive scalings. So we define a weighted orientation, which is a pair between the orientation and the weight. But the weighted positive geometries are kind of nice, well, they have various nice properties. You can add them together and you don't need to worry about whether they overlap or not, because if they overlap, here's one geometry, weight 1 here, weight 2 there, they overlap, and that just means I have weight W1 plus W2 on the overlap. So you can add them together without, which you couldn't do for geometries before. There's also a natural projection operator onto boundaries, where now we have these so-called internal boundaries are now just discontinuities of the weight function. And on the discontinuity, you naturally induce a weight on the boundary. So W and W prime becomes W plus W prime. Okay, and then here's an example. So I start off with this geometry, weight 1, orientation opposite here, weight 1. I induce on the boundary. Here I have 2 guys, so I have weight 2. Here I have 1 guy. And then at this point here, I have weight 3. Okay, and then to go from weighted positive geometries to generalized positive geometries, they're just things with weight 1 in the generalized positive geometry and 0 elsewhere. To get to the positive geometries, however, they're weighted positive geometries with weight 1 in the bulk, but then the induced weights also have to always be plus or minus 1, 0, and that is a kind of an additional, from this point of view, that's a sort of artificial constraint. Okay, I should say that actually there was something called a Grothendieck group of pseudo-positive geometries introduced already in this paper as a kind of formal sum of positive geometries. So you can view the weighted positive geometries as a sort of concrete realization of these formal sums. Okay, good. So, I mean, that's the main point. I wanted to, okay, I'm out of time, but if I can just summarize this slide briefly. We wanted to kind of have a characterization of these generalized positive geometries. And one thing we can say is that if a region is defined by multilinear inequalities, then we know it's a generalized positive geometry. And that's a broad class which includes the amplituhedron, which itself is defined by it can be defined by multilinear inequalities because it's defined by determinants. And determinants are multilinear functions of their components. So if you choose variables as their components, then you've got it. You've got generalized positive geometry. Okay, good. I'll flip through to the conclusions. There's the deepest cut I haven't got time to talk about, but we reanalyze the deepest cut and find internal boundaries for the so-called all-in-one point deepest cut. So there's a few things I think may need looking back on. Things where people talk about codimension K boundaries, sometimes they're okay, but not necessarily always. We need to look at precisely what that means. Okay, so I guess one of the main outcomes for me is the concept of the weighted positive geometry, and there's the whether that can have a wider application to various generalizations of amplituhedrons, the cosmological polytope. There's various places where it looks like a positive geometry, but things aren't necessarily quite working in the same way. And the hope is that the weighted positive geometry can give the right sort of language to talk about these things. Other things is just to look more carefully at the boundary structure, and in particular, it'd be nice to make a closer relation with the symbology from the amplituhedron. Okay, thank you.
Okay, we have time for some questions.
Let's go.
Okay, can I just have a quick question? So for the L-loop amplituhedron, do you have a kind of argument that you can get up to L number or L factorial, or do you know how much does it grow this, the value of the leading singularity for the general L-loop amplituhedron? Also, if you go, for example, to higher N and K.
What's the question?
If you calculate the leading singularity on the amplituhedron
Yes.
form and L loops, so you already showed that.
What can you get?
Yeah, what do you get?
I mean, you can certainly get 1, for example.
Yeah, what's the maximal number?
What's the maximum number? Okay, I see. interesting question. I mean, we've looked at these. The other way of phrasing it is how many deepest cuts can you take the boundaries of? So certainly more than one. I can't give you a precise answer as to how many. I don't think off the top of my head. It becomes intricate even at 4 loops. It's not as the actual geometry. Well, I can draw a picture of the 4-loop geometry, but you kind of have an internal cut, and then you get an internal boundary with external boundaries in a sort of intricate fashion. So,
Okay. Are there any other questions?
I think there's a guy at the back.
Maybe just urgent ones because we're a bit out of time.
So is it easy to define? Is it easy to define the dual positive of your generalized positive geometry? And can we use the volume of the dual positive to get the conical form of your generalized positive geometry?
Sorry, can you say that again?
Sorry, so I want to ask whether it's simple to define the dual positive of your generalized positive geometry. Dual positive.
Oh, the dual of the generalized positive geometry. I think. Well, I'm not sure it's easy to define it for the positive geometry, right? But in the cases that you can, I don't think it should be much different. I don't think it should affect the existence or not of a dual. The inequalities, the basic inequalities, nothing's changed as far as the inequalities are concerned. It's just an observation about in the inside. When you take enough boundaries, you get these funny internal boundaries appearing.
Yeah.
But the sort of general definition of the amplitude hasn't changed.
Yeah, I mean, for example, if we want to get a conical form of a positive geometry, we can use the volume of its dual positive to get the conical form. Allow you generate the positive geometry. So I was wondering if there is similar method to get the conical form.
Right. So
use the volume of a dual positive.
Yeah, I haven't thought about that. But I mean, this is for n to the NMHV, right?
Okay. I see.
You're talking about.
Yeah.
Perhaps since we're a bit running of time, perhaps we should continue this conversation off the records.
Right. Okay.
So thanks again to Paul.
Thank you.
And our next speaker will be Livia Ferro, who is going to tell us about the loop momentum amplituhedron.
Thank you. Just let me try. Okay, very well. Okay. Well, first of all, I would like also to thank the organizers for the invitation, and above all, also for organizing such a great conference. It's good to be here in person after 2 years. So, thank you very much. So today I am going to talk about some work in progress with Tomy Lukowski. And in particular, I'm going to talk about the extension of the momentum amplituhedron at loop level. So we actually already heard some introduction from Paul. So I'm going to complement these informations, some we already heard. But I'm going to kind of see another point of view of the positive geometries. Okay, good. So the positive geometries really represent one of the most recent advances in formulation of observables in quantum field theories. So there has been an explosion of these new kind of formulations. And in particular, roughly speaking, we can think about positive geometries as geometries which have some notion of positivity. And this notion of positivity is substituting some other notions, so for instance, locality and unitarity. But roughly speaking, you can consider them as a generalization of the convex polytopes. Okay. And well, in this talk, I'm going to consider scattering amplitudes in n equal to 4 super-Young-Mills, and I'm going to talk about amplituhedral. First of all, a few words about positive geometries. So, positive geometries are regions with boundaries of all dimensions, and each boundary is again a positive geometry. Every positive geometry is equipped with, we heard already, with a unique differential form, which has logarithmic singularities on all the boundaries of the geometry, and this is called the canonical form. And if we have a positive geometry, which is physically relevant, then the canonical form is a physical quantity. So for instance, the scattering amplitude. So if we have a set of external kinematic data, then there exists a geometrical object, which is then defined by imposing some particular positivity constraints. And from this positivity constraint, we can see that locality is derived from the fact that this geometry has the appropriate boundaries, and unitarity is derived by the appropriate factorization into smaller pieces when we approach one of these boundaries. So in n equal to 4 super-Young-Mills, we have two kind of objects. One of positive geometries, one is the amplituhedron and one is the momentum amplituhedron. So what are the main features of these two geometries? So the amplituhedron is formulated in the momentum twistor space, and so it's really relevant for the planar sector. The MHV part is factorized out, so actually it is relevant for the Wilson loops, and it really has both tree level and loop level. The momentum amplituhedron is instead defined in a non-chiral spinor helicity space. And at the moment, and then I'm going to show you then the loop generalization, it is defined just at tree level. So the natural question is, can we generalize then the momentum amplituhedron to include the loops? And here in this talk, I'm going to show you how. And then also a natural question is about the non-planar sector. So the non-planar sector is actually not reachable from the amplituhedron point of view because it is formulated in momentum twistor space. But there is the hope then, since we are working in the spinor helicity space, then we are not constrained to be in the planar sector. There is some problem with this. Okay. So we already heard the definition of the amplituhedron. So at tree level, the amplituhedron is relevant for n to the k prime MHV Wilson loops. And it is the image of the positive Grassmannian G plus k prime n through the following map, okay, where we have that y is the sum over c times z. Now I'm going to talk a little bit more about this. So we have a matrix C, which is an element of the positive Grassmannian. So the Grassmannian, Gk prime comma n, is the space of k prime planes in an n-dimensional space. And when we say that, for the non-expert, when we say that we take the positive part, we take all the maximal ordered minors to be positive. So we have the following map, and then we can also go to the momentum twistors, just the bosonic part. So this Z here are the bosonized momentum twistor superspace, and the positive region is given by the fact that matrix Z is positive. Now, the momentum twistors, here I gave their definition. So the first two components are lambdas, and the other two components are x times lambdas, and x is the dual space. The momentum twistors, they sit inside the bosonized space. And we already heard about the sign flips. And so this map defines a subset in the kinematic space of the Zs, for which we have the following brackets. So these are the brackets of small z larger or equal to 0. And the following sequence has k prime sign flips. So what about the momentum amplitude? The momentum amplitude is relevant for n to the k minus 2 MHV amplitudes. So you see if k is equal to 2, then we have the MHV amplitudes. And it's the image, also the positive Grassmannian G plus, k comma n, this time, not k prime, through the following map. So this time we have a y twiddle and y, which are defined in the following way, where lambda twiddle and lambda are the bosonized spin-relicity variables. Okay? And the positive region in this case is given by the matrix lambda twiddle positive and the matrix lambda perp positive. And again, the spin-relicity variables, so lambda and lambda twiddle, they sit inside the bosonide space in the following way. And this map defines a subset then in the kinematic space lambda twiddle, for which these brackets are positive or equal to 0. So these are the usual angle and square brackets of lambdas and lambda twiddles. The Mandelstam are also positive. And then we have the following sequences k minus 2 sign flips, and the sequence of the square brackets. This sequence has k sign flips. Okay? So this is the sign flip, also definition of the momentum amplitude. Now, I would like to talk a little bit about the boundaries and the singularities, as it will become important later on when I talk about the loop level. Now, in general, the amplitude, they encode the physical singularities of the amplitudes in their boundary structure. So for the momentum amplitude, we have, now here I'm considering the facets just. So the facets correspond to collinear limits, where the brackets, angle and square brackets, are equal to 0 for II plus 1, and to the factorization limits. And actually, for the momentum amplitude, the full stratification is known. Okay, so we can go deeper in geometry and find all the amplitude singularities. For the amplitude, the facets they are given by this formula, and actually the full stratification there is not known. Now, the important point here is that since the MHV amplitude is factored out in the amplitude, now we don't have any boundaries which correspond to these angle brackets II plus 1 equal to 0, because these are the boundaries which come from the MHV amplitude. So the point is that these two objects are very different at tree-level. The boundaries are really not the same. And actually, the tree-level momentum amplitude is really not a simple translation of the amplitude construction. And I make now this point, and you will see why I'm making this point here now. Okay, so what about the loop level, the loop geometry? Now, the loop amplitude is there. We know its definition. Now, at loop level, then we have the loop amplitude is the image of the following map. Now, I have extended. So here, instead of having just the matrix C, I also have L, 2 planes, these. So these are 2, n matrices. And so this would be the tree-level part. And this is then the loop level part, where I have the 2 planes. Now, each loop here corresponds, we also heard about this during a song talk. Each loop corresponds to a line AB, which also corresponds to a point X in the dual space-time. And so, when we wanted to do the loop integral, then this will correspond to the integral over the space of lines AB, which can also be rewritten as the integral over a pair of points A and B, which is divided by the GL2 redundancies, which label their position on the line. Okay. So the integration over the loop momentum can be written in the following way. Okay, sorry about this. Now, there are also some positivity constraints. Okay, so before we just had the matrix C positive. Now we have this particular positivity, it's called extended positivity. And so the matrix C is positive, and then I stack on top of the matrix C, each of the matrix D, and then I ask for them to be positive. Now this comes from the idea of hiding pairs of adjacent particles. So for instance here it's the two loop case, and we can imagine to chop off these four columns, and if I add some positivity from for the big matrix, then one has some inherited positivity which will then remain there in form of these positivity constraints. So we can schematically also think about these matrices C and D in the following way. So we have a matrix C, which is a K prime times n matrix C, and then we have L, two planes, which live in the complement, in the n minus K prime complement of C. Now, well, now one can think, we talked about the amplitude. This is in momentum twistor space. What about the regular, let's say, momentum, okay, ordinary momentum space? Now, there is a main obstacle in generalizing this to the ordinary momentum space, and the obstacle is that it's difficult to find some proper global definition of the off-shell loop momentum. So in the dual space, so when we have in the X space, this X, which represents the loop, is uniquely defined up to a global shift. While in the momentum space, actually I can redefine the loop diagram by diagram. I can always add or subtract some momenta. Okay? So the integrand changes, and it changes diagram by diagram. And so there is no global definition of the off-shell loop momentum. Okay, so what are we going to do? And now I'm going to present two approaches which actually failed, but I think it's still interesting to see how they fail, in a sense. So the first approach is to mimic naively the hiding particles approach that we saw before for the spin-Orellicity space. Now remember that the amplituhedron, we have y twiddle and y. And remember that y twiddle is a C lambda twiddle. Okay? So what about trying to extend this to include then some D matrices as the amplituhedron? So write something like L twiddle equal to D lambda twiddle. Now, there will be some mutual positivity condition, but actually this will not work because there is not enough space to take the perp here. So we don't know what to do with lambda. So this is the picture of before, but translated for the momentum amplituhedron. Here the matrix is K times n. And here I would have that the D matrices live in the n minus K dimensional complement. But then when I go consider y equal to C perp lambda, then this C perp will already occupy this space here. So we actually don't know what to do with the D's. And the relation of L twiddle and L, these ones to the loop momentum, is also not clear. It's a problem of... okay, well, it was a beautiful picture, but which went too fast. Okay, so there is actually another approach. And this would be to parameterize the loop momentum using then the BCFW construction. Okay? So the BCFW in spin-Orellicity space for the loop amplitudes can be schematically written like this. So we have the loop amplitude here and points, We take, so this will be the sum over these diagrams, which are the factorization channels with a BCFW bridge attached, and the forward limit also with the BCFW bridge attached. Now here I have an amplitude with one loop less and two particles more, and I take two particles, actually A and B, and I merge them. And then from this construction, I can in principle find the matrices, I could find the matrices C and D. I use the on-shell diagrams and I can find the boundary measurements. Then, so from here, we have the loop momentum is defined as lambda twiddle plus alpha, and then lambda 1 and lambda twiddle n, which are the external particles. And my expression for D4L is the following. So the good thing is that the lambda and lambda twiddle can be parameterized in terms of the external momentum. So this is good. This is what we see also in the loop amplituidron, right, where the momentum twistors of the loop are parameterized in terms of the external momentum twistors. But from here, the positivity conditions are really not obvious. So we don't know which kind of positivity conditions on the matrices we should put. Okay, so. Okay. So we go back to the boundaries. And I mentioned before the singularities. In particular, the singularities which are connected with the facets. Okay? So we have seen that the singularities at tree level are very different, but actually if we look at the loop level, the singularities can be really mapped between momentum twistors and momentum space. Okay? So we couldn't have a direct translation between the tree amplituidron and the momentum amplituidron. So at tree level, we cannot really, because these geometries, they have very different boundaries. But maybe we can do it at the loop level. And indeed, this is what I'm going to show you in a second. And so here I'm going to present the extension of the momentum amplituidron for loop amplitudes. Now, we're going to consider a direct translation. Okay? So what was not possible at the tree level, because the boundaries were so different, I mean, the geometries are really different, then we can do at the loop level. Now, for the external particles, we have here, there are the momentum twistors. So we have the first two components are the lambdas, and the other two components are x's times lambdas. And for the loop, remember, we have ZA and ZB. And so I will have lambda A and lambda B, and X lambda A and lambda B. From the amplituidron, we have, remember that we have that ZA and B is equal to the sum of D, these are the elements of the matrix D, times the external. So these are a combination of the external momentum twistors. So directly, we can see here, if we take the first two components, we have that lambda AB, then it will be the sum over the same elements of the same matrix times lambdas. Okay. And this will have a natural inherited GL2 on lambda A and lambda B. And so we can write actually the off-shell momentum in a GL2 invariant form in the following way, where if lambda transforms as lambda G, lambda twiddle will transform with the inverse of G. And then we can consider the other two components, the last two components of the momentum twistors. And, well, we are right here. So I will have x lambda equal to the sum D of xi lambda I, so the external ones. And then we can use the relation between x and lambda twiddles, and at the end, we will find that the lambda twiddles for the loop can be written as this particular combination of the lambda twiddles of the external particles. Now, importantly, we made a choice here. So in going from here to here, we made a choice on how to relate the loop momentum to the dual space, and this is the choice, so x minus x1. And even more importantly, this is a global choice, okay? So we choose this from the beginning. This is an input in the map. So the loop momentum amplitude then is defined as the following image, is the image of the following map. Where now we have the tree level, which I presented already before, and then the loop momentum is written in terms of the external lambda twiddles, and the matrix D, and secretly also C. And so this map associates to every point C and D here, the tree level variables lambda twiddle, and the loop momentum L. What about the positivity? The positivity then is inherited from the amplitude. So for every element C in G+, we can actually define another matrix, which is C check QC, with Q, this operator, which actually was already there many years ago, was the map relating the Grassmannian for the spinor helicity with the Grassmannian for the momentum twisters. And this actually implies that the C check is also in the positive Grassmannian, but with K minus 2, not K. And then we have the same positivity conditions for the loop amplitude. So we will have C check positive, D C check, and then also all the loop matrices with C check positive. Let me just briefly give you an example, and the example are MHV amplitudes. They are the easiest example. Now K minus 2 is equal to 0, so C check is empty. So there is no positivity condition involving C check, so we just have the positivity of C and the positivity of D. For the MHV amplitudes, we don't have to triangulate at tree level, but at one loop, but we know also that at one loop, the amplitude is triangulated by the Kermits. So we can really write that the momentum amplitude at one loop for MHV amplitudes is the union of the images of the map, phi twiddle. And what does it mean for this, for the differential forms? Okay, the differential form, then it will be the wedge of the differential form for the tree level and the sum of the differential forms for all the Kermits, where these differential forms are written in this way, and you see that we have well, the proper singularities, and we also have the spurious singularities. So this brings me to my conclusions. Maybe? Okay. So what are the main features of this construction? Well, we've seen that since the singularities of the loop integrants can be mapped between spinor helicity and momentum twistor space, then we can actually think about a direct translation from the amplitude at loop level and from the loop amplitude then to the momentum amplitude at loop level. We have written the loop momentum in a GL2 invariant way, and actually we have found a global definition of the loop momentum, which is fixed directly by the map phi twiddle. Now there are still various challenges and open questions. The first one is that this definition relies on the positivity conditions, which are not really natural from the point of view of spinor helicity space, so there might be some improvement on this. The most important point is the one about finding triangulations. Okay, so for instance, if you go to NMHV amplitudes, then we don't know how to triangulate what we would call the one-loop Grassmannian. So the question is, I mean, one possible way would be to try to solve the BCFW construction, recursion relations, to find a GL2 loop momentum. And then once that we have this, well, we still have clearly the planar loop integral, so it would be interesting to generalize this construction then to the non-planar sector, so go beyond the planar sector. And with this, I would like to thank you, and maybe at some point it will come. Okay, thanks.
Thank you. Okay, so any questions?
Thank you very much for a nice talk. So for the loop part, because it's a direct translation of the momentum twister part, so one would probably assume to find for the loop amplituhedron the similar structures that Paul just presented in his talk. That would be probably also literal translation of the weighted geometries that would probably make the same sense in this setup. Or
Sorry,
what
I
do you
didn't
think?
hear the first part.
No, because the loop part is a direct translation of the momentum twister part.
Yes.
So the observations that Paul presented in his talk, I assume would be also true for the loop momentum amplitude.
Yeah, I suppose so.
For
Yes.
spinor helicity.
I think so, yes.
Okay, thank you.
Hi, thanks for a very nice talk. I wanted to ask, so you mentioned that the boundaries at the loop level you expect to be mapped between the momentum amplituhedron and the amplituhedron.
Yeah.
But I was wondering, one class of phases in the loop amplituhedron are related to tree-level amplituhedron, like the leading singularity ones. So I would expect also that those type of facets would be different, since the tree-level amplituhedron and the momentum amplituhedron
Could you
are
lower
different.
1 second? Yeah, or put the microphone closer. Yeah.
Yeah.
Can you say again the part? Sorry.
So the last part is part of the boundaries of the loop amplituhedron are related to the tree-level one because of the leading singularities of loop level. So I would expect that the facets which relates to the tree-level amplituhedron would be different between the loop momentum amplituhedron and the loop amplituhedron. Is there a reason why you expect to be the same? So in your,
I was I was considering the facets for the 3 and 3, really. So the fact that one cannot really translate or just a change of variables between the two.
Mm-hmm. But you expect at the loop level that there's going to be a translation between the two?
So if I look at the singularities at the loop level, I can go from, I mean, it's kind of direct translation because you can just use the change of variables, right? Mm-hmm. So it's kind of just a guiding principle to find the same.
Okay.
Yeah.
No, yeah, I was just wondering, since the tree level sits inside the loop level, and that's why I was wondering.
It's a good question. Yeah.
Okay. Then if there are no more questions, okay, we can thank Livia again.
Thanks. This looks like it's working better. And this way. What? So you can. This yours.
Okay, so we can welcome our last speaker for this session, which is Shruti Paranjate, who's going to tell us about non-planar BCFW geometry. Please.
So hello, I am going to tell you about non-planar BCFW Grassmannian geometry. This is work I did in collaboration with Yara Trinka and his graduate student Minshan Zheng. And it's work that's presented in this, okay, the pointer may or may not be working. So, okay, in the paper that is given over there. Okay, so before I start, I'd just like to say I'm very happy to be in this beautiful country giving this talk, and I thank the organizers for putting this nice conference together and for the opportunity. Okay, so that picture had not much to do with my talk, other than the fact that there were trees in it, and this talk will be at tree level. So the primary thing, the theory that I'll be talking about today is n=4 super Yang-Mills, and primarily we'll be studying this via two methods. The first will be BCFW recursion, and the second will be the Grassmannian formulation of n=4 super Yang-Mills. And when I say that, what I mean is that each of these BCFW terms will correspond to on-shell diagrams, which we will then calculate using the dual formulation. Okay, now we just heard a lot about how when you have planar amplitudes, you have various nice features that show up. Oops. Okay. So one of these features, of course, is positivity that we heard about in the last two talks. Another one, which seems rather obvious, is that MHV amplitudes have holomorphic poles. So the first thing we will do is to interpret both of these statements directly in the Grassmannian space. But the primary aim of the talk will not be to do this for planar amplitudes, but to be able to extend this to non-planar on-shell diagrams. Okay. Now, this might be a confusing thing to say because I already told you I'm going to be at tree level. So what do I mean when I say that I have non-planar on-shell diagrams? So what I mean is, more broadly, why one would want to study non-planar on-shell diagrams is because they show up in singularities or unitarity cuts of loop integrands, right? So that's why you would want to study them, but they're not easy to study. Partly because some of the nice properties I mentioned on my previous slide don't extend to these non-planar diagrams, right? So what would be useful would be to have a nice subset of non-planar diagrams, which could be our gateway into understanding them better, okay? And that subset, for me, is going to come from BCFW shifts that are non-adjacent, okay? So the usual story is that you have adjacent BCFW shifts and various nice properties follow. In our case, we're going to break our tree-level amplitude up into a sum over non-planar objects instead of planar objects. Okay? Now, this is a very artificial thing to do, but it's going to be helpful because we know this stuff. So can we describe these non-planar contributions in a nice way? And the answer is going to be yes, and the way we're going to do that is by introducing some Grassmannian geometry that will give us a good hold on these non-planar on-shell diagrams. So I want to stress that this will be not the most general diagrams, but the ones that appear naturally when you do tree-level non-adjacent BCFW. So yeah, BCFW. Okay. And the hope, of course, is that we can extend this beyond just BCFW, and we can talk about that later. I would also like to stress that for each of these Grassmannian configurations, we're going to be able to directly write down what is the corresponding BCFW term. Okay, good. So let's get started. Let me just start by telling you the usual story, which is that you start doing BCFW by choosing two lines, and you introduce some complex parameter, and you shift two legs, right? And then Cauchy's formula, or whatever your favorite method of thinking about it is, will then tell you that you can construct higher point amplitudes by breaking it down into lower point ones. And the easiest example is MHV at endpoint, because that has only one BCFW term, which has one anti-MHV amplitude over here and one MHV amplitude over there. Okay. So now, if you keep doing this, you can break your amplitudes in n equals 4 down all the way to 3-point amplitudes. And there are two types of 3-point amplitudes. You have your MHV and your anti-MHV. And this allows you then to write each BCFW term as a sum of on-shell diagrams. Okay. Good. So continuing the example we had, which is a n-point MHV amplitude where we've done an n1 shift, so an adjacent n1 shift. This is what the BCFW term looks like, where this is now the n-1 point amplitude. Okay. So examples, of course, are pretty easy to construct. You just have a 4-point amplitude with one term and a 5-point amplitude with one BCFW term, etc. So how do I go from this to actually writing down what is the object what is the amplitude? The way to do that is via this dual formulation where I've introduced, or where it was introduced, that you have this auxiliary C matrix, which is K cross N. So I should say that K is the nk minus 2 MHV amplitude that you are calculating. So for MHV, it would be 2 cross n. Okay, so you introduce an integral over this matrix in this particular way, where the matrix components are constrained by these delta functions over here. And the matrix itself belongs to what is called the positive Grassmannian. So this is GKN is a space of k-planes, an n-dimensional space, and the plus sign at the bottom means that all consecutive minors are positive. Okay. So I showed you two seemingly disconnected things on these slides. How this connects to the previous slide is that each on-shell diagram tells you something about which minors are positive, which minors are zero, and that tells you what cell of GKN that you are in. In particular, you can actually just look at an on-shell diagram and read off a parametrization, which then you can put together and calculate the corresponding BCFW term. Okay, so this is just a quick review. Here is an example. So if you have a 5-point amplitude, 5-1 shifted, you get a BCFW term like this. You can decorate it with these edge variables alpha, calculate the C matrix by boundary measurement, and then the corresponding, so the formula from the previous slide, so this one over here, now evaluates to this familiar Park-Taylor form for the 5-point amplitude MHV. Okay. Now, another way to see this, and this will be our preferred way to see this, is that when k equals 2, this constraint over here can be solved when you choose C equals lambda. So when I choose C equals lambda, the product of minors of my matrix just become products of angle brackets, and this is going to give you the Park-Taylor form. Okay, good. So I gave you various different descriptions, and you found that all of them converge to give you the familiar Park-Taylor form for MHV amplitudes. Okay. You had one BCFW term, which was one on-shell diagram, corresponded to one 2n minus 4 dimensional cell of the positive Grassmannian, and then I showed you a holomorphic expression for what came out of that. Okay. So now I want to show you or demonstrate how this stuff can just be read off of a Grassmannian geometry. Okay? This stuff meaning the holomorphic expression, and also the fact that this has some positivity properties. Okay. So the way to do this is to, instead of thinking about the matrix C as belonging to GKN, instead you think of each column of C as belonging to projective space of k minus 1 dimensions. Okay, so k minus 1, of course, in MHV case is just P1, which is a line. So you have some endpoints on a line. Now, because you know that C has to have consecutive minors positive, you can say that, you can say something as long as this works. Okay, so you can say that the positivity of the minors gives you some ordering of these points Z on the line. Okay, and so in that sense, in P1, these endpoints form a convex configuration, and as we know, this convex configuration is Park-Taylor. And we could have just found out, we could have realized that this was Park-Taylor directly from the geometry, because the only poles in the geometry, the only boundaries of the geometry are when 2 points get merged, right? 2 consecutive points. So the only poles in our amplitude come from these boundaries, which correspond to angle brackets going to 0. So those are the only, so this gives you a holomorphic description of the poles. Okay. So there are of course lower point poles, but other than that, at this level, these are the only poles available. Okay, so now that we understand how to see these properties from the Grassmannian geometry, we want to understand how this extends beyond this trivial example, which is just adjacent shifted MHV amplitudes, right? So the first thing that we'll do is to look not at MHV, but to look at NMHV amplitudes. Here, of course, the on-shell diagrams will still correspond to cells in the positive Grassmannian, but it's sort of unclear how the holomorphicity of the expression that comes out is, well, it's just not apparent that this stuff is holomorphic. So we'll see how to see this holomorphicity from the Grassmannian geometry. We'll then proceed to non-adjacent BCFW shifts, and we'll do that for both MHV and NMHV. I should mention that all of this actually does extend to NKMHV, but for the sake of simplicity, we'll only look at these examples today. Good. So in this case, we'll lose both the convexity and the holomorphicity, and so constructing the Grassmannian geometry is going to be a little more involved, and what we'll do is make an educated guess as to what these geometries are, and we'll find that actually this is the right thing to do. Okay, so let's start with the adjacent shifted NMHV amplitude. So in this case, you have two BCFW terms. You have one that is a product of two MHV amplitudes, and the other that is a product of an MHV bar with an NMHV. Now, this corresponds to a sum of on-shell diagrams, which, as I mentioned before, each on-shell diagram is just some cell in G3n now, rather than G2n, because we're at NMHV. So again, each of these cells can be thought of as some Grassmannian configuration in P2. Okay? Good. So in case you're wondering where this codimension n-5 came from, well, the dimension of a generic cell would be 3n-9, and then you would have to bring it down to 2n-4, and so you need some number of conditions that these geometries have to satisfy. So let's look at an example. For n equals 6, codimension n-5 means you need one condition. So if you start with some generic convex configuration of points in G plus 3n, so note that now we are in P2. These points are in P2. Then you need one condition to specify a BCFW cell, and you get a sum over these three configurations. So you see that one condition is now placed because one of the minors has been set to 0 in each of these. Okay. One thing to note, already at 6 point, this is easily visible that all 6 points actually lie on just 3 lines. At 6 point, this is kind of trivial, but beyond 6 point, this continues to be true, and we'll see that that is actually not a generic feature of non-BCFW cells. Okay, so this is a familiar expression for the NMHV amplitude, which is a sum of R invariants, and I've written down the expression for the R invariant over here, and you'll note that you get poles, which are square brackets, and you get these mixed poles. So what I want to do is to be able to read off the expression directly from the geometry, and preferably to be able to see all of the poles as just some mergers of points in this geometry. Okay. So we'll start with the first diagram, which has two MHV amplitudes on either side. And the BCFW term is then a product of MHV things with some pole. We can actually rewrite this pole by introducing an extra n hat in our geometry, which then allows us to rewrite this pole as this Park-Taylor factor over here. Okay? So I've rewritten MHV, MHV pole as MHV, MHV, MHV. Now this inspires us to draw the following geometry where you have a line over here which gives you the first MHV factor, a line over here which gives you the second MHV factor, and this third line which tells you that this pole is part of your BCFW term. Okay. And note that in this expression, which is just equal to the R invariant that I had on the previous slide, I now only have holomorphic poles where all of the anti-holomorphic or square bracket information is now packaged very neatly into the fact that you have an I and an n hat in these Park-Taylor factors. Okay. So what happens to the second diagram? Well, it's kind of surprising, I guess, that the geometry that I had on the previous slide actually generalizes now to this one as well. What I need to do for that is it's basically a recursive argument. So you'll note that NMHV at 5 point will have only MHV contributions. So then I can use that to build up recursively endpoint NMHV. And you find that that corresponds to basically taking this lower point thing and adding an inverse soft factor, which is the same as in the geometry, just adding this point n over here between 1 and n minus 1. Okay, good. So now we have this general expression for what a BCFW Grassmannian geometry looks like, and the corresponding R invariant will just be these Park-Taylor factors on these 3 lines. Good. So before we continue to doing non-adjacent and non-planar things, already over here you can see that these are specialized. This is a particular special subset of these diagrams. And that's because generically an n-5 codimension cell would have points that are constrained to lie on 5 lines. And you see over here that actually we are only constrained to lie on 3 lines. And that's because, that's the special feature of BCFW, it picks out these special cells. So in this case, you can see that what that means is that C equals B plus 1 and E equals D plus 1. And so now I can just continue this into 3 lines and get rid of the 2 parallel lines over here. So it's a special subset. Okay. So let's extend this special subset now to include non-planar contributions. So we'll start with a sort of trivial example, which is MHV. And we'll do a non-adjacent shift. So now I'm not shifting n and 1, but I'm shifting 1 and k. And what we'll find is that I still get a line because I still get some configuration of points in P1, but they no longer have that nice ordered behavior that they used to have. Okay. Which means that while the cells are convex with respect to sum ordering, they're not. You'll have to sum over things that each of them they are convex, but together they will not respect the final ordering given over here. Okay. So this is a sort of minimal extension to a non-planar example. What we want is to have serious non-planarity, which we'll see in the case of NMHV. So consider the simplest example of an NMHV amplitude, which is 5 point, and do this non-adjacent shift, which is 1, 4. Okay. Now you can already read off the Grassmannian geometry from here. So you have a MHV amplitude 1, 2i, so you have a line 1, 2i. You have an MHV amplitude I3, 4, 5, so you have this line I3, 4, 5. And finally, the fact that you'll have a propagator will say that you have to also include this Park-Taylor factor 4 hat 4, 1. Okay. Similarly, you can see that this needs to come from that one. Okay. So now clearly convexity is lost, and I can no longer just interpret this as being convex with some oh boy, okay, with some different ordering. So, okay. So, okay, right. So as promised, these non-planar Grassmannian configurations over here correspond to genuine non-planar on-shell diagrams. And so when I say that we have a description of these objects, I do genuinely mean that we have a description of some non-planar on-shell diagrams. Now, in general, the endpoint NMHV amplitude is going to give this non-planar configuration, which is non-planar simply because there are points that lie on these lines over here. Now, because each of the lines represents an MHV amplitude, you can actually use the Kleist-Coif relations to move the points that used to lie out here and out here back onto these lines over here, as long as you sum over the permutations that Kleist-Coif requires you to sum over. So this is all to say that you can take the configuration that we had on our previous slide. So you can take this, this configuration over here, and you can rewrite it as a sum over planar objects. So there's some planar expansion that you can do. So that leaves you with two options to write down the final term. One is you use the fact that the non-planar geometry can be written as a sum of convex configurations. You know what convex configurations correspond to, and then you have an expansion for your non-planar geometry. The second, remarkably, is that you can just find the non-planar R invariant by treating each of these lines, again, as Park-Taylor factors. The only difference is going to be that now 1 and I1 won't lie on either side of the Park-Taylor factor because I1 will sit in the middle of these Park-Taylor factors. Okay. So this picture actually extends beyond NMHV to all NKMHV. Now you're going to have, your geometry is going to lie in a higher dimensional projective space, so you're going to be in PK-1. This is an example at N square MHV. Again, you have some orderings and some Park-Taylor factors that you have to include for each of the lines over here that are populated by points. And you can write down generalized R invariants that will now be products of these Park-Taylor factors on all of these lines. Okay. So I'd like to, before I end, point out two interesting features of this construction. Okay? So the first is that, as I said, each of these non-planar configurations, you can write down some kind of product of Park-Taylor factors. And so your final answer for every amplitude is going to be a sum over products of Park-Taylor factors with some Jacobian and delta function included. Yeah. Which means that each individual term actually has some residual ordering that it respects, but when you sum it together, each term individually respects some orderings, but when they won't be the same ordering for each term that you're summing over. So this kind of leads you to the question of whether there is any kind of dual conformal symmetry that is left over, and that is not something that we fully understand now. The final thing I'd like to say about this is that because we are, for example, at 6-point codimension 1, you can think about, can you extend these Grassmannian geometries to talk about the higher dimensional cell? So for example, if you're at 6-point, is there a geometry like this, which when you go onto this boundary, the 1, 2, 6 boundary, you can recognize that you get a BCFW geometry of this kind, right? So in other words, can I extend this to more general non-planar on-shell diagrams, not just these BCFW ones? Okay, so this is just a summary. So earlier we had this positive Grassmannian description of adjacent shifted BCFW, and now we can extend this to understand how to read off the BCFW term from the Grassmannian geometry. We can also have these, we can also extend this to non-planar, so non-adjacent shifted BCFW. And we can write down the corresponding R invariants for each of these terms. Okay, so given that I'm almost out of time, I'll just leave you with this picture and a few questions. So thank you for your attention.
Okay, so are there any questions? Okay, then I would have a question myself. So have you thought already how to go beyond the tree level? Do you have any ideas?
So maybe before you go beyond tree level, the first thing you'll have to do is go beyond this 2n minus 4 dimensional bunch of on-shell diagrams. So you're going to have to sorry. Okay, so you're going to have Grassmannian geometries for these higher dimensional objects, so something like this, whose then you can go onto the boundary of one of these, and that'll give you BCFW. So basically, this description that we have for these BCFW cells, can you take it to the higher dimensional cells? And yeah, that would be the first step, to extend it. And this is something that for the already classified G3N, we're trying to do, so Yaroslav and his two students, Taro Brown and Umut Oktam, we're trying to see how we can extend this now to the top cells of G3N. And that would be the first step. Yeah.
Okay, thanks. And here we have a question.
So can I just ask about the dual conformal invariance? I mean, it's there, right? So, but your question is to ask how it's broken term by term and then somehow restored.
Right. So it's there because in the end what we're doing is rewriting the tree level amplitude in terms of these bad, quote unquote, bad objects. But I guess the question is when you sum over these like non-planar objects, each of them is going to correspond to some R invariant with some amount of ordering left over, the ordering being on these individual lines. And so would you be able to say that that has some amount of symmetry that's left over is kind of the question, which I don't know the answer to. Yeah.
Okay, so if there are no more questions, let's thank Shruti again.
Thank you.
Okay, thank you. So we
but yeah, I can still wait 1 minute or, oh, it's still not too. Good afternoon. We'll come from the lunch. There are some things piling up. I always forgetting to tell you. So I have 4 things. Where is Christoph? He remembered them. So first one is a cafeteria, just 1 floor below, and it's an option, the easiest option. So far I haven't seen the queue there. Of course, it's not meant for 200 people, but yeah, you can check how it is there. Second thing, posters. They ask me if they can take the construction out tomorrow afternoon when we are not here. So if you want to keep the poster, please take it, or if you leave it there, I don't know what they do with that. Oops. Third thing, what was it? Photo, thank you. It's important that I told you. There will be, we decided, yeah, it would be natural to do it tomorrow, but you know, it's slightly shifted the schedule, and then probably we could have different plans with the free afternoon. So it should be before lunch Thursday, just after we finish the lectures. And fourth? Slides. We are putting your slides on to the Indigo, so of course we should have asked you if you agree. So if you don't say anything, we take it as an agreement. Okay, that's it. And now.
Okay, welcome to the first afternoon session. We have 3 speakers. Our first is Sebastian Mazzara, who will tell us 3 things we've learned about infrared divergences this year.
Well, is this on? Yes, okay. Well, first of all, thank you so much for the invitation to give this talk. Today I will be talking about this recent work together with my brilliant collaborators, Nimar Kani-Ahmed, as well as Aaron Hillman, who is a final year graduate student at Princeton University. Okay, my motivation is going to be very quick. Basically, we have multiple ways of thinking about UV divergences. So for example, we can think of them as the loop momentum blowing up in the momentum space. We can think of the space-time points colliding in the coordinate space, or perhaps wordline segments shrinking in the wordline formalism. Let me highlight that especially the last part in the recent years has featured many fascinating connections between algebraic geometry, topology, and combinatorics, but also new computational tools that we can use to our benefit. On the other hand, most of the intuition now for the infrared divergences, I think it's fair to say that comes from the loop momentum space. So there we naturally think of the infrared divergences as coming from some collinear or perhaps soft limits. So one of the basic questions that we asked ourselves recently is what is the meaning of infrared divergences in the Schwinger parameters or in terms of word lines. Okay, so today I wanted to share 3 simple lessons that we've learned over the last year. The first one is going to be the wordline interpretation of infrared divergences. It will have to do with this fact of the wordline segments expanding as opposed to shrinking, which I will describe in the first part of the talk. Then the second part will be this idea of thinking of divergences as certain redundancies in the description of our Feynman integrals. And then finally, I will tell you how to use this interpretation and intuition to our benefit to a new computational scheme for infrared divergences. Okay, so I'm going to start very slowly with the Feynman integrals in the Schwinger parameterization. So this is something that we've seen yesterday in some of the talks. So here the notation will be that alphas will be the Schwinger parameters associated to individual edges, and capital E will denote the total number of internal edges. Okay, D will be the space-time dimension, which we'll take to be close to 4. Okay, in case you have not seen this representation before, then don't worry, because we'll see explicit examples in later slides. Also, if you rather would like to think about the loop momentum space, there's an easy way of reconstructing the loop momenta as being parameterized by these Schwinger parameters using this explicit formula that we'll use on later slides. Okay, so now at this stage, the integrand in the Schwinger parameterization involves these functions f, u, and n, which are called the semantic polynomials. So to those of you who are already familiar, recall that u is the one that sums over spanning trees, f is the one that sums over spanning 2 trees, and we can also include numerators responsible for some interesting spin interactions, but for the purposes of this talk, we'll set them to 1, but they can be easily included in the analysis. So once again, if you've never seen this before, don't worry, we're going to see explicit examples later on. Okay, so one of the basic things that I would like to emphasize is this overall GL1 redundancy. Physically, it should be interpreted as descending from the reparameterization invariance on the word line. Okay, so if we think of our Feynman diagram as having these Schwinger parameters, physically Schwinger parameters, we should think of them as measuring the lengths of each of the individual edge in this diagram. Okay, so the redundancy that we have in this description is that we can multiply all the Schwinger parameters by some common factor rho, which corresponds to either dilating, rescaling the Feynman diagram, and in the fancy language, we would think of rho as an element of GL1. Okay, so this tells us that we're only supposed to think of the Schwinger parameters as being defined up to this overall rescaling. Okay, we can of course do it, as is very common, do it at the level of equations, in which starting from this original formulation, we can integrate out the rho, this overall scale, and the way it works at the level of these equations is that here on the right-hand side, we mod it out by the GL1 redundancy, which typically is done by either setting the sum of the alphas to be 1, in which case we call those parameters Schwinger parameters, or it's sometimes more convenient to fix, say, 1 of the Schwinger parameters to be 1. And this is what I will choose in this talk. Okay? As a result of doing this, we got the gamma function, which is responsible for the overall UV of divergence, where E is the number of internal edges, L is the number of loops, and D is the space-time dimension divided by 2. Okay, so here it's very simple, but the thing that I wanted to emphasize is this trading of fixing of the GL1 redundancy, and which is connected to factoring out of the overall degree of divergence, something that we'll encounter later in this talk in more complex examples. Okay. So at this stage, I wanted to make some connections to other talks in this conference, and this has to do with this point of view on singularities that I've been trying to argue over the last couple of years, which is that we should treat them as saddle points of the wordline action. Wordline action is nothing but this ratio of the semantic polynomials that we've seen before, and once you write down the equations, basically these variation equations, what you can do is ask how many constraints those equations put on the external kinematics. And there are essentially 3 options. So first of all, we can have constraints in codimension 1. What this means is that we put that the divergence is there for any value of the external kinematics, and this is precisely what we call UV and IR divergence. Another case is that of the codimension 1. For example, when we set some Schwinger parameter, Mandelstam invariant S to go on the threshold, and this is precisely connected with the presence of the normal anomalous thresholds, something that we already heard about and we'll hear much more about in the upcoming days. And lastly, there's also a possibility of having codimension 2 and higher singularities. This is something that would set, for example, 2 Schwinger parameters to be, 2 Mandelstam invariants to be 0. And if you believe that the S matrix is supposed to be analytic, these are supposed to be absent. And it turns out that the absence actually put interesting constraints on the nature of singularities, something that we explored recently. But for the purposes of this talk, we'll focus entirely on the case of UV and IR divergences. Okay, speaking of which, let's look at the simplest example of an IR divergence. So we're going to look at this box where every edge, internal edge, is massless. We have one massless corner in here, and the 3 remaining corners are massive. What I'm going to claim is that what we have to do to see the collinear divergence is rescale these 2 Schwinger parameters, alpha 2 and alpha 3, with some common scale lambda, and then take this lambda all the way to infinity. So at the level of the cartoon, recall that we're supposed to really think of the Schwinger parameters as being relative to each other. What this means is that the Schwinger parameters alpha 2 and alpha 3 sort of arrange themselves in this configuration in which these 2 wordline segments become closer and closer. And I'm going to claim that this is the interpretation of the collinear singularity. In case you didn't believe this cartoon picture, what you can do is simply you can check what is the configuration of the loop momentum that corresponds to this divergence, and you can easily just check that in this case the loop momentum becomes collinear with the external momentum P2, as expected. Okay, so the next too simple example is the case in which we make not 1 but 2 massless corners. P1 and P2 are massless. In this case, we can just superimpose the picture that we've had before, but twice. So on top of the previous lambda parameter, we also have some scaling in sigma. Okay, so on one end, we can take lambda to infinity, giving us the previous collinear divergence. We can also do take sigma to infinity, which gives us a collinear divergence in this direction. But of course, now we have a whole 2-dimensional space of scalings in which we can take both lambda and sigma to infinity at the same time. And I'm going to claim that this is the soft collinear divergence. Once again, you can go and check that the configuration of the loop momentum corresponding to the rescaling is indeed when the loop momentum here becomes collinear with P1 and P2, but also at the same time is soft. Okay. Then you can keep going, and you can go consider more and more complicated diagrams, in which case the wordline scalings become more involved. So here's one example of a contribution to the QCD Caspar anomalous dimension, in which the IR divergence corresponding to this diagram is governed by the 4 different scalings, in which each of them is taken to infinity. Okay? So this might look a bit artisanal, but the claim is that we will actually see that these kind of divergences can be entirely classified for every Feynman diagram. Okay, so the summary of the first part of this talk is that we've found the wordline interpretation of IR divergences, and they come from the wordline segments expanding at different rates relative to each other. And this is in stark contrast with the UV divergences, in which you would think of the wordline segments as shrinking as opposed to expanding. Now, in the second part of this talk, we wanted to look at this interpretation of divergences as redundancies in our description of Feynman integrals. So to this end, what we're going to do is first, we're going to change the variables from the Schwinger parameters to this exponential variables tau for every single internal edge E. Okay, so under this change, the integration measure, let's say we've pulled out this logarithmic measure in here, just becomes flat in terms of tau. So we just have this measure in here. But more importantly, we do not integrate from 0 to infinity, but in the tau variables, we integrate from minus infinity to plus infinity. This change of variables has the advantage of the fact that all the divergences are now put at infinity. So recall that, roughly speaking, e to the tau measures the length of each internal propagator. So when you take tau to be plus infinity, you explore the IR physics, and when you take it to minus infinity, you explore the UV physics instead. Okay? So what this tells us is that all of the divergences, UV or IR, come from approaching infinity from different directions. Because now we have these coordinate systems, a system of different taus, say tau 1, tau 2, and tau 3, and depending on which way we approach the infinity, we might explore a different divergence, be it UV or IR. And you might be worried that there could be some divergences in the middle of the integration domain, but this would be kinematic singularities that can be avoided with this I epsilon prescription. So we don't need to worry about them. Okay, and then the point here is now that we've realized that all we have to do is explore the behavior at infinity, we can actually linearize this problem using the tools of tropical geometry. Let me mention that tropical geometry is something that appeared in many recent works, but by people in the audience in other contexts, in scattering amplitudes recently as well. Okay, so the tropical approximation is going to be of the integrand, which after pulling out the Jacobian, what we want to do is we want to approximate this part here. So u to some power, f to some power, and this part. What I'm going to do is I'm going to describe this part of the integrand as e to the trop, where trop is some function that depends on the on the taus and the external kinematics. And the point is that this is going to be an exponentially good approximation to the integrand at infinity, precisely where we care about the UV and IR divergences. Okay, so as you can read off from here, trop is going to be this sum of taus, just copy it from here, and then we have this max condition on the u, which means you just select out of the polynomial u, you select the monomials that are dominating in a given direction at infinity, and likewise for f, okay? And it comes with these prefactors that depend on the degree of divergence and the space-time dimension. Okay, so in case this was a bit too dry, here's an explicit example of a collinear divergence in 4 dimensions, the example that we've seen before, in which case the u polynomial is given by this sum of Schrödinger parameters that in tau translate to this function. Then in f, we have this combination that depends also on the external kinematics, s, t, and the masses. And now the tropical approximation is going to be the sum of taus. There's -2. 2 is the degree of divergence of this diagram in 4 dimensions. And then what we have to do is we have to select this max condition, which tells us take the maximum exponent appearing in those terms here. And we're assuming that st and other variables are of order 1, so we can ignore them in this approximation. Okay, so at the visual level, here I'm plotting some section of this integration domain, say tau 2 and tau 3, where I froze the other variables. And here on the left, I just plot the log of the integrand given by this function. If you work out in 4 dimensions, the exponents are 0 and 2. And on the right-hand side, I'm plotting the trop approximation, okay? And if you're sitting far away, you might not even be able to distinguish between them. And this is the reason why we use it. While in the middle of this integration domain, the 2 functions might be different. The idea is that the approximation is supposed to be very good when you take scalings all the way to infinity. Okay, and as we can see here, there's a preferred direction in here in which both tau 2 and tau 3 go to infinity. This is exactly the IR divergence that we've seen on this part of the plot, in which the 2 edges expand to infinity. Okay, at the level of equations, what we've done is we've approximated our integrand by dropping one of the terms that is subdominant by this function. Okay, as you can notice, as you can check, it's invariant under the original GL1, in which case we expand all the Schrödinger parameters with this overall scale rho. But now it also has this enhanced redundancy, in which also you can rescale alpha 2 and alpha 3 with this common scale lambda, and this integrand becomes unchanged. Okay, so we've upgraded our GL1 to GL1 squared. Now we have 2 redundancies. And as you might be familiar from gauge theory, every time there's a redundancy in your description that you have not modded out by, you get a divergence. Okay? So this direction in here is what we would call a divergent ray. This intuition also tells you that in order to extract the coefficient of this divergence, all we have to do is simply mod out by this divergence that is not fixed in here. Okay, so the first question that you can ask yourself is, what is the kind of divergence that we get? Okay, so this is very simple. Recall that the e to the trop was approximating the integrand. So approximately, we're looking at this function, okay? So if the trop is negative at infinity, this means that the integrand is exponentially suppressed. This means that in this direction, the integrand is finite. On the other hand, if trop is a positive function, this means that this blows up, so it gives us a divergence, something that we call a power law divergence. And there's also on the interface between the two, we can have the trop can go to 0. And in this marginal case, we are dominated by this logarithmic measure, so this signals a presence of a logarithmic divergence. Okay, at this stage you can ask, now that we know what type, now we can ask how bad of a divergence we get. So we've already encountered the case in which we had a single ray along which the trop function is equal to 0, and this signaled a logarithmic divergence, or in dim-reg 1 over epsilon. Okay, so that was the case for the collinear case. And then the simplest generalization is that if we have two directions that generate not a ray, but a cone. So a cone signifies the fact that there's a two-dimensional divergence, which is either log squared or 1 over epsilon squared in dim-reg. Okay, such as in the case of the soft collinear divergence. And then finally, you can, of course, generalize this to arbitrary dimension k, in which you would be dominated by 1 over epsilon to the k divergence in this case. Okay, so here's the result of what happens at the level of the actual formula, how to extract the leading coefficient of the divergence corresponding to a given diagram. Okay, so what happens is that you have to sum over all divergent cones. Now include this volume factor. Volume of the cone is proportional to 1 over epsilon to this power k, which we take to be maximal. And basically, this volume tells you about the shape of a given divergence. And now the interesting part is in here, in which all we have to do is take the original integrand, but now mod it out by the enhanced redundancy group. So not just the original GL1, but GL1 plus k, where k was the number of redundancies. And then we can also drop from the U and F polynomials, we can simplify them, we can drop the coefficients which were subleading, so the ones that did not matter for this divergence. Okay, so coming back to the example of the collinear divergence in 4 dimensions, I've already pulled out the 1 over epsilon factor, and then we had this 4-dimensional integration over alpha 1, 2, 3, and 4, and now we have not GL1, but GL1 squared. This allows us to fix 2 Schwinger parameters, for example, to 3 and alpha 3 and alpha 4 to 1. Okay, since we're already computing the most divergent contribution, we can in fact set the dim-reg epsilon to 0 in this case, and we can also cross out the terms that are subdominant in this direction. This bumps us from the 4-dimensional integral to a 2-dimensional integral, which you can simply do, and it gives you the correct result for this case. Here's the example of the soft collinear divergence, in which case we had this two-dimensional cone generated by 2 rays, lambda and sigma. Okay, in this case, we do not mod out by GL1, but GL1 to the 3rd power, which allows us to fix almost all Schwinger parameters, except for 1, drop all the monomials, and you land on this simple integral. Okay, this integral even I can do, and it's equal to 1 over st, which is the correct result in this case. Okay, here's the more complicated example of this Cas polynomials dimension that we've seen before, in which case we had 4 redundancies, here indicated in this picture, that this means that we have 1 over epsilon to the 4 divergence, and we can fix 5 Schwinger parameters. Okay, after you do this, you find that you get some number which is in agreement with the results in the literature. Okay, at this point, let me mention that there's, of course, a rich literature on closely related topics, and those include sector decomposition and expansion by regions, but also treating Feynman integrals as GKZ hypergeometric functions. So in contrast with those approaches, or rather on top of those approaches, the additional thing that we're exploiting here is the combinatorics of the semantic polynomials, which implements the combinatorics of IR divergences, and UV for that matter as well. Okay, so here's the summary of the Second part of the talk, divergence in this language is a GL1 to some power of redundancy, and you can compute the coefficient of this divergence by fixing k plus 1 Schrödinger parameters. So this is entirely analogous to fixing gauge in gauge theory. Okay, and now in the last part of the talk, we'll move on to the computational scheme, which will involve these so-called Feynman polytopes. And the idea here is that there's no need to repeat this analysis for every single diagram by hand. What we have is a general structure, and the general structure basically identifies a given subdiagram here called gamma of a big diagram G. And then we take all the Schrödinger parameters within this gamma and rescale them to a point, to 0. Equivalently, you can think of the complementary set of the Schrödinger parameters as going to infinity. And this is, in fact, an example of the collinear divergence that we've seen before. And the bottom line is that the claim is that all of the divergences are actually of this type. So all of the rays, divergent or not, are generated by these subdiagrams gamma. Okay, so this information is neatly summarized by the structure that we called Feynman polytopes. And the Feynman polytopes tell you exactly where the divergences are. So you can think of those rays as being dual to some facets of a polytope. And the direction of the ray tells you where the divergences are located. It also tells you what type the divergence is. And this is captured by the information of the value of this tropical function along a given ray. And also the combinatorics of this polytope tells you how they nest and how they overlap. So this can be done explicitly at the level of equations. So you can study this value of the tropical function in a given direction in the tau space. And you can solve that it's equal to these combinations of degrees of divergences of gamma and this reduced diagram, which tell you both about the UV-like and IR-like singularities. And let me mention that, of course, Feynman polytopes have been previously studied in the UV case with generic kinematics. So this has been done in beautiful papers on blowups of the Schrödinger parameter space, and also more recently on the numerical computations of finite integrals. One thing to emphasize is that IR singularities need non-generic kinematics because many of the masses are set to 0. So we couldn't actually directly use those results. And to the experts, also Feynman polytopes are in general not generalized permutohedra, which also didn't help. Okay, so at this stage, let me mention that there's, of course, lots of applications of this formalism to infrared divergences, including some of the interesting all-loop examples. Okay, so I will refer you to the details to this paper that we wrote together with Arkania Met and Hillman this year. But let me sort of emphasize one of the interesting cases that we studied is this set of rectangular fishnet diagrams with arbitrary loop order, when you have some n by m fishnet, and then we can compute exactly what are the leading divergences of 1 over epsilon to the m times n, which is the number of loops of this diagram in terms of some combinatorics of superfactorials and so on. Okay, so if there's time, and I'm already pushing it, I was going to describe the sort of the direction that we're taking into using this formalism to a consistent Laurent expansion in the reg around 4 dimensions. So this is very much inspired by the work of Brown and Kramer on BPH0 renormalization, and also Brown and Dupont on string perturbation theory. And here the idea is that once you've identified where the divergences are, what are their properties, and so on, you can leverage this information to a consistent subtraction scheme. And I decided it would be more interesting to just give you the simplest example of this in the action, which is this triangle contribution, which has both soft and collinear divergence here. So we've already learned how to compute the leading part of this divergence, which in this case turns out to be very simple. And what this formalism tells you also is how to expand it in epsilon. Okay, so what they land on is the representation of a finite integral, in which case all the divergences have been subtracted, so all the integrals are manifestly finite. And the divergences only come from these explicit prefactors. What this means is that you can just simply take this integration and you can series expand it. Okay, so to leading order, it gives you this simple integral that you can do either numerically or analytically, and indeed is the correct answer. Okay, so the summary of the third part of the talk is that the combinatorics of both UV and IR divergences is summarized by these Feynman polytopes that know about the type of divergences and how to also compute it. Okay, so what we've learned today is our 3 points. First was the wordline interpretation, in which the IR divergences are interpreted as the wordline segments expanding in certain directions. Then we've also learned about the interpretation of divergences as redundancies, in which you can also leverage this information to mod out by the divergences and compute the leading coefficients of those coming from those contributions. And finally, I sketched how we implement this in a consistent computational scheme for Feynman integrals, including some interesting all-loop examples. So with that, let me thank you for your attention.
Okay, thank you for that very nice talk. Are there any questions?
Yeah, thanks for the nice talk. I'm curious, maybe you said it, but what is the algorithm for finding all the possible singular regions within this divergences as redundancies?
Yes.
So in other words, what's the substitute for solving the Landau equations in this view?
So in this case, you can argue that all of the divergences are classified by these subdiagrams gamma. And then for each of those gammas, you just identify all subdiagrams and plug it in this formula. There's 2 cases that you have to consider. Basically, if the diagram is it has a scale or it doesn't have a scale. In both cases, the value of the Trop function, which is a proxy for understanding how fast the integrand diverges in this direction, is simply expressed in terms of these degrees of divergence. So after you identify that, you know if there's a divergence and what kind in a given direction. Yes.
Other questions?
Yeah, thanks for the nice talk. Could you also apply the last part of your talk, for example, to the for-loop diagram you showed and get all the subleading poles and epsilon out of it?
Yes, we're working on it, actually.
Thanks.
Hi, a very interesting talk. So the structure of infrared divergences is critical to factorization, but also the numerator structure and the structure of gauge theories. Is there an alternative approach to understanding why amplitudes factorize using this approach?
This is something that we looked at in the simplest case of the exponentiation of the amplitude, which was in n equals 4 supernumerals. In which case you can go back to one of the first slides in which I show the numerator that we've set to 1. You can also work out what those numerators are corresponding to some non-trivial n equals 4 supernumerals diagrams, and then you can see that the divergences exponentiate to some orders in perturbation theory. So this is something that we checked, I think, up to 3 loops, that if you compute the log of the amplitude, of the full amplitude, then you expect that starts at order 1 over epsilon, which is the part that exponentiates. So you expect massive cancellation of 1 over epsilon to the number of loops. In this case, 1 over epsilon to the 3. And we checked explicitly that using this formalism, you can see how this happens.
Question here. In massless theories, can you apply similar construction for position space amplitudes and relate it also to divergences of Wilson loops?
Perhaps, we have not thought about that, but the formalism is quite general. You're just studying an approximation scheme for the integrand in certain directions, and people have applied similar ideas to other cases, but I'm not sure if that has been done in the coordinate space. I think that's an interesting question.
Okay, I'm not seeing any more questions, so let's thank Sebastian again. So our next speaker is Simon Zoya.
Okay, hey. All right, well, first of all, I wish to thank the organizers for inviting me to this beautiful conference. It is really a pleasure and an honor to present my work in front of you. And today I'm glad to report on the recent developments in the computation of two-loop 5-particle amplitudes with one external massive leg. So the talk is roughly structured as follows. So there will be two main topics which I want to touch upon. One is the construction of a basis of special functions, which allows for a very efficient evaluation of all the required Feynman integrals. And this is some work which I did together with Dima Chicherin, who's here in the audience, and Vasily Sotnikov. And the second part will be more about the amplitudes, and in particular one specifically, the amplitude for W plus BB bar production and two-loop order, which I computed together with Simon Badger and Heribertus Bayer-Hartanto, and then I will also take this to the final step, which is the phenomenology. So I will show you some phenomenological study making use of these amplitudes, which I did together again with Bayer-Hartanto, and then René Poncelet and Andrei Popescu. All right, but let me first begin with some motivation. Now, why are we so interested in these very complicated amplitudes? And the reason for us is mainly LHC phenomenology. The reason is that really the spectacular progress from the experimental side, in particular the improvement in the systematic uncertainties, means that we are already in a position, and we will be even more so in the future, of having for many processes observables with an accuracy which is at the % level from the experimental point of view. So this is really a spectacular precision target, which really means that the usual slogan that we hear, that we have entered the precision era of the LHC, is not really a slogan, but it's really a fact. And now it's fair to say, unfortunately, that this great progress on the experimental side is not useful unless we theoretical physicists can keep up with that. So this is really a challenge for us. We need to push our theoretical predictions to a comparable level of accuracy. And if we want to do so, we really need to go in QCD at the next to leading order, at least. Now, this is well under control for processes involving 1 or 2 particles in a final state, and the current frontier, which we are tackling right now, is 2 to 3 scattering processes. Now, there's really many ingredients that go into a theoretical prediction, and, but I think, well, I will motivate this in my next slide, but really what is the bottleneck, it's fair to say, are the analytic computation of the two-loop 5-particle amplitudes which enter in the double virtual corrections. And so to motivate this, I wanted to show you in this very crowded slide the spectacular progress in the computation of theoretical predictions for 2 to 3 processes in the fully massless case. So these are processes which do not have any mass at the level of the amplitudes. Now, I don't want to go through all the references, of course, but I want to highlight 2 main aspects. First of all, that what really allowed to go from a situation where we had some analytic results for the integrals, in particular in the form of the canonical differential equations for the master integrals for the required integral families, to instead a situation where many groups could independently and very efficiently compute a lot of scattering amplitudes for these very complicated processes, was the availability of a basis of special functions, the so-called pentagon functions here. And the second thing I wanted to highlight is, as I said, that these amplitudes really are the bottleneck, because to prove this, after these amplitudes were computed in terms of these special function bases, it was just a matter of a few months before our colleagues also computed the theoretical predictions, in particular 3-photon production, diphoton plus jet production, and even more spectacularly, even 3-jet production, which is really a milestone for a perturbative QCD. So we want to push this further, and we want also to describe one massive particle in a final state. Now, this really would open up the possibility to study a very rich phenomenology. Here I listed a few processes which I took from the Lesouche precision wish list from last year, for instance. And the challenge here is that of an extremely complicated algebraic and analytic structure. So just to give you a measure of this, the kinematics is described by 6 independent kinematic variables, so that's quite a lot of kinematic variables. And there's really many square roots which we cannot rationalize simultaneously. So this makes the algebraic expression for the amplitudes themselves, so really the rational coefficients, extremely bulky and complicated to manipulate, and makes the analytic structure of the Feynman integrals very integrate. So the evaluation is very challenging. Okay, so this is the target. So these are the amplitudes that we want to compute. And the second thing I want to highlight is how we want to have them, because I think that almost anyone in the audience here could come up with some expression for the amplitudes. You could just take your favorite Feynman diagram generator, and this is not really a big deal to provide some expression for the amplitudes. But this is not really a particularly useful expression for the amplitudes because we can't get numbers out of that. So the question here is, when can we be happy about our expression for the amplitude? And it turns out that we really have strong requirements on the amplitudes because of the fact that we want to do phenomenology with them. So what we think is the ideal form of the amplitude is as a linear combination of special functions. So by special functions here I mean logarithms, multiple polylogarithms, and in general it's very interesting open questions what kind of functions can show up here. And then multiplied by irrational or algebraic, if there are some square roots, coefficients. And so, but this is still not sufficient because we must be able to integrate the square root of these amplitudes of a phase space. So this means that we must be able to evaluate this whole thing very efficiently in a stable way across a physical phase space. And this is very challenging in particular for the special functions which have branch cuts. And then the expressions must be very compact because we want to code them up in some C++ library, for instance. And so this, in general, means that we must be able to perform simplifications and cancellations analytically at the level of the amplitudes. For instance, we must be able to subtract the ultraviolet and infrared poles analytically. Okay, so now we know which amplitudes we want to compute, and we roughly know how we want them to look like at the end. So the only thing that remains to be done is to understand how to actually do that. So in this slide, I tried to summarize in a very simplified way what is the workflow that our group is employing to compute these amplitudes. So we start from an expression for the amplitude in terms of Feynman diagrams, which we generate using QGraph, for instance. Then we manipulate this expression to rewrite it in terms of some scalar Feynman diagrams, scalar Feynman integrals. And then we, by solving integration by parts identities, we re-express this in terms of the so-called master integrals, so the basis integrals, linearly independent integrals, which span the integral families. Then we expand everything in epsilon. We expand the rational coefficients in a Laurent expansion in epsilon, and the same also for the master integrals. And this means that order by order in epsilon, we express the master integrals in terms of special functions, and up to the order which we require for the computation. And finally, the experience has shown that it's also a good idea to subtract at this stage the ultraviolet and infrared poles, obtaining what is so-called the finite remainder or hard function, which is really the newly piece of information, and it's also the simplest object that contains all the information which we need. So all these steps are very standard and conceptually very straightforward. The challenge here is the computational one, because the expressions of all these rational coefficients are extremely complicated because of the many variables. So they can be rational functions with polynomial degrees of hundreds, for instance, in 6 variables. And so this whole tool of operations suffers greatly from the so-called expression swell. So the expression at the intermediate stages are really unmanageable. So the way we overcome this is by employing finite field arithmetic. So this means that we evaluate all the rational coefficients at all the steps of this workflow numerically. So we set both the kinematic invariance, epsilon, to some integer values, and then we take the modulus with respect to some large prime number. In this way, all the intermediate expression collapse to just numbers. So these are as compact as you could wish them to be. There is no further simplification that is required. And essentially, we turn this whole workflow into a black box, some C++ algorithm, which for given input values for the kinematics, epsilon, and the prime, gives us the values of the coefficients of the monomials of the special functions in a finite remainder modulo that prime number. And in particular, we use the framework finite flow. And then now doing this, evaluating at a single point now is no longer problematic because everything is very under control in the intermediate stages, and we just need to do this enough times, collect enough sample points, such that then we can reconstruct the analytic expression of the final result. And this is now much better because the final result is much simpler than the intermediate stages, and so it's very efficient. So it's also an interesting story. We had to come up with several strategies to improve on this, but what I want to focus on now is instead the master integrals and how we express them in terms of a basis of special functions. Okay, so in this slide I summarize what is the state of the art, let's say, for the computation of the Feynman integrals families which are required for this class of two-loop amplitudes. So all of them, well, the ones which have been computed, but I think also the ones which will be computed in the future are going to be computed using the method of the canonical differential equations. So this means finding a special choice for the basis of Feynman integrals such that their derivatives have this very special form where dependence on epsilon factorizes, and then the dependence on the kinematic is just through linear combinations of logarithms of these WIs, which are so-called letters, which are just algebraic functions of the external kinematics. Now, for the planar integral families, we so Ben Page here in the audience and his collaborators, and also Mao Zheng here in the audience, computed the canonical differential equations for this family. Then another group using the method of the so-called simplified differential equations provided expressions in terms of multiple polylogarithms. And then my collaborators and I also did the extra step of constructing a basis of special functions. And I will motivate in my next slide why we really needed to put the extra work to do this step. For the non-planar integrals also there are already some intermediate results, but we are not quite there yet with the basis of special functions, but I'm confident that it's just a matter of time. Okay, so as I promised here, I argue why it's really important to have a basis of special functions. And by basis I mean that the special functions are algebraically independent. So the reason is that, in general, multiple polylogarithms satisfy, well, there's two main reasons, let's say. So the first one is that multiple polylogarithms satisfy very complicated functional relations. Here in this slide, you can see one of the simplest ones for the dilogarithm, for instance. And now if you imagine that one of your master integrals contains Li2 of z, and some other integral contains the other three terms, and you compute an amplitude, and your algorithm does not know that the sum of these terms which come together is 0, then what you're doing in the end is reconstructing the coefficient of a 0, which is really not an efficient way to proceed. And in general, this is really, essentially what this amounts to is that the rational functions that you are computing, if you do not have a basis of special functions, are significantly more complicated, and you cannot even subtract analytically the poles in epsilon. So instead, if you have a basis of special functions, this is all taken care of, because once you express the amplitudes and the integrals in terms of them, there is no longer any functional relation among them that needs to be taken care of. So this means that the reconstruction is simpler and that the analytic expressions are more compact. And the second reason is that we can set up an extremely efficient strategy for their numerical evaluation. So in my next slide, I will talk about our approach, which is essentially some tailored representation which we implement in C++. But since it has been receiving a lot of attention lately, I also wanted to mention that it's also possible to apply the method of the generalized Power series expansion, for instance, implemented in diffpacks or many other packages. Seaside, I think there was a poster about this. So it's possible to apply this directly to the basis of special functions instead of the master integrals. And this is less efficient, perhaps, but it's very flexible. So I really believe that this will play an important role in the future. Okay, so before I show how we evaluate the functions, I wanted to show you quickly how we construct systematically the basis of special functions, because this is actually something extremely simple. So the tool which we used, which allows us to do this, are the so-called chance-iterated integrals. So I think many of you are probably familiar with the so-called symbol, and chance-iterated integrals are essentially the symbol plus also all the information about the transcendental constants. Now, the definition, you can see it here, it's an iterative definition. The number of integrations is the so-called transcendental weight. These WIs here are essentially the letters of the canonical differential equations. And well, these objects really satisfy a lot of properties, but we really don't need to go into the details of them. What I want to show you is how once we express the integrals in terms of these chance iterated integrals, all the functional relations are automatically implemented. And I thought that showing an example would make the point clear. So for instance, if you take the functional relation which I showed previously and you express all the functions in terms of chance iterated integrals, then you will see that, well, in Mathematica, you would just hit expand, and this would immediately give a 0. So essentially, once this allows us, so chance iterated integrals allow us to turn the problem of finding the functional relations in just a linear algebra problem, which is something that, of course, we can implement in a very efficient and systematic way. So once we do this, once we solve the differential equations in terms of chance iterated integrals, order by order in epsilon, we just need to do some linear algebra to extract the linearly independent components and then also algebraically independent. Okay, so about their evaluation. So if we are interested in NNLO QCD theoretical predictions, we need to go up to 2 loops, and we need to go up to transcendental weight 4 for the iterated integrals. At weight 1 and weight 2, what we do is to construct explicit expressions in terms of logarithms and dilogarithms using symbol technology. So again, this is something which can be done systematically by making an ansatz and fitting it, essentially. And what is crucial here is that we pick a specific physical phase space region. For instance, here we chose the S45 channel for some reason. And then the expressions for the functions which we construct are manifestly and by construction well defined in that region. So this means that we do not need to perform any analytic continuation, and that evaluating them numerically is very straightforward. Now, one could do the same also at weight 3 and weight 4. Would be more complicated, of course, but actually experience has shown that it's actually more efficient to take a different approach, more numerical approach, which is to construct one-fold integral representations for these functions. So at weight 3, this is really not very surprising because weight 3 is by definition defined as the one-fold integral of the weight 2 function. So this is really not surprising that we can do that. But actually also at weight 4, it's possible to do some integration by parts, and essentially we get a one-fold integral representation where the integrand contains only logarithms and derivatives of logarithms, and then weight 1 and weight 2 functions which we have already classified and constructed explicitly. And so the key aspect here is that the integrands, which we have here, are again manifestly well defined. They're analytic in the physical scattering region. So this means that provided that we integrate them only in the physical scattering region, again, there is no analytic continuation, everything is well defined, and the integration is very efficient. So this is what I was trying to represent here with this funny star. So this would represent the S45 scattering region, and essentially, we integrate our functions along some piecewise paths which never leave the physical scattering region, so that along the path, everything is analytic. Okay, and then we implemented these integrations in a very nice C++ library. And the result is extremely efficient. So you can see here some stability plot for these functions. So what I want to highlight is that we can evaluate all the functions which are required to evaluate all crossings of the planar integrals. So not just one, but literally all crossings which you might need to compute a leading color amplitude in double precision in just 0.2 seconds. And the stability is also really good. And then, okay, if that's not sufficient for you, we also provided higher accuracy in quadruple and octuple, which can be useful for if there are stability issues. Anyway, we really think that this is extremely efficient and that this is ready for phenomenology. And in fact, this is what I'm going to show you in a few slides. So once we had a basis of special functions, the same thing that happened for the massless cases, which I showed you previously, was possible. So we could immediately compute many analytic expressions for the amplitudes. So there's a few of them. So perhaps one highlight are the amplitudes for W plus 2 jet production, again by Ben Page and his collaborators. And then what instead I'm going to focus on is a special case of that, which is W plus BB bar production, including the decay of the W boson. And so this process is very interesting for many reasons. First of all, it's interesting on its own because it essentially allows for stress tests of the standard model. Indeed, this was measured both at the Tevatron and LHC by the CMS collaboration. But it's also interesting as a background to other more interesting, from a phenomenological point of view, processes. For instance, these two you can see here. Then it's interesting from a theoretical point of view because it's a perfect testing ground to explore the differences between the different schemes to treat the bottom quark. The bottom quark can be treated both as a massless parton or as a massive parton, and this makes a difference whether we include it in the PDFs or not, for instance. And as you might have understood, we treat it as massless since we only have the Feynman integrals with one massive external leg, which will be the mass of the W boson. Then, furthermore, this is a process for which really the NNLO corrections are required because the NLO studies have shown that the corrections at NLO are very large and the scale variation is also extremely bad. So we really need NNLO QCD predictions for this process. So, okay, so we computed the two-loop amplitudes, in particular in the leading color approximation, for which we only need the planar integrals, following the workflow which I highlighted in the introduction. We treat the big quark as massless, and this means that we need a flavored prescription to cluster the jets in a final state, and we employed first the flavor KT algorithm by Banfi, Salaman, and Zanderighi. Then we implemented the computation for the infrared subtraction in Stripper. We use open loops for the one-loop amplitudes, and in general, we took all the cuts and the setup in general from the CMS measurement, because our idea was eventually to compare against the data, of course. And here, finally, I can show you what I believe is the first cross-section or I don't know, differential distribution of this conference so far. And a few years ago, I would have been very surprised to know that I would be the one doing this. It was a really long journey for me. Anyway, so there's a lot of stuff in this slide. It's definitely too crowded, but let me highlight the main aspects. So this table here shows the inclusive cross-sections in two configurations. So inclusive means that we tag at least 2 B-jets in the final state. Exclusive means that we tag exactly 2 B-jets and no, we do not want any other jet. So we veto on the extra jets. Now, in the inclusive case, you can see that the K factor, which is just the ratio of NLO, the cross-section at NLO over LO, is very large, so it means that the corrections are 70%, very large, as I was saying a few slides ago. At NLO, there we see an improvement, and also an improvement in the scale variation here. We adopt the standard scale variation. And so we do see that there is a nice perturbative convergence, both from the point of view of the size of the corrections and of the uncertainties. Now, in the exclusive case, something interesting seems to be happening, because it seems like at NLO already we have a very small K factor, so the corrections here would be less than 20%. But here we must be careful, because this is a phenomenon which was observed already 10 years ago by Stewart and Tuckman. So in the exclusive configurations, there is a cancellation between the large quantum corrections, large K factors, and the logarithms of the scale which we're using to veto the jet, essentially. So anyway, the point here is that it's known that the standard scale variation does a really bad job at estimating the theoretical uncertainties. So we did also employ what we call the uncorrelated prescription, which they suggested, which we give here in the parentheses, and you can see it gives a much more conservative estimate, perhaps too conservative, but at least it's reliable. So here this is a clear sign that a better understanding of the theoretical uncertainties is required for the exclusive configurations. And the same kind of comments we can make about these differential distributions. We studied a few of them. Here you can see, for instance, the distribution of the invariant mass of the BB bar pair. For instance, here you can see again this very broad band is again the scale variation done with the uncorrelated prescription. You can see it's extremely large, but that's what we could do. But in general, anyway, the take-home messages from this slide that I wanted to get are that for this process, we are seeing perturbative convergence, and that the evaluation of the pentagon functions, which we required for the virtual corrections, is really not a problem anymore. So the pentagon functions really meet the phenomenology demands. And finally, I wanted to add something which is still a work in progress, but which I was very happy to see, which is finally the comparison against the CMS data. So we had to wait to do this because the experimental analysis do not use the KT algorithm, but use the anti-KT algorithm. And only recently, actually this year, Mikhail Chakon, Alexander Mitov, and René Poncelet proposed a flavored version of the anti-KT algorithm, which allows for a direct comparison against the data without having to unfold the predictions. And so we, as soon as they published it, we immediately employed it to recompute the theoretical predictions now for the total cross-section in the exclusive setup, which is why you see the error bars are so wide. And finally, we compared them against the CMS data, and it was really pleasant to see that there is a great improvement in the agreement with the LHC data. So clearly, the NLO corrections for this process were required and definitely improved the situation. Okay, and this brings me to my conclusions, actually. So I've shown you the construction of a basis of special functions, which allows us to express and to evaluate efficiently all the Toulouse 5-particle integrals with one external massive leg, at least in the planar case. But the result is important on its own, but it's also important the methodology, which is more general, of course, and which we are sure we will use also in other cases. And then I've flashed a few results for Toulouse amplitudes for this class of processes, and in particular I focused on the W production plus in association with a VV bar pair. And for this I presented the amplitudes and the NNLO theoretical predictions, which are really the very first ones for a process of this complexity. And with this I thank you for your attention, and I look forward to your questions. Thank you.
Okay, thank you, Simon, for that very nice talk. Are there any questions?
Hey, nice talk. I was curious a little bit about the error bars on that last plot with the CMS data. You did mention that sort of, well, your impression was that it was kind of unusually large at NLO. But if anything, I'm kind of curious about the other fact that the LO error bars don't include the CMS data.
Yeah.
Do you think that there's sort of been a systematic underestimate of error bars at LO given where the NLO data has ended up? And do you think that this would mean that maybe in future people should use different error estimation for those processes that can't be computed to such high orders based on what we know about the processes we can compute?
Well, I mean, so your question, well, first of all, thanks for the question, but so if I get it correctly, you're asking whether there is an overestimation already at leading order?
Right, like are they overestimating their precision?
But I mean, at leading order, it's well known that in QCD, the error bars at leading order are usually very large. This is why we need, this is why we need to do NLO and NNLO correction. So, I mean, I'm not particularly surprised by the error bars at leading order. But perhaps to clarify some aspects, so these error bars are particularly large also because we included something which is called DPI correction. So this is essentially some additive correction factor which we have to add, which keeps into account what are so-called double parton interactions. So this is something which we took from the experimental analysis themselves, so where they used the NLO prediction interface to parton shower event to estimate the contribution to the total cross-section coming from these double parton interactions. And they essentially claimed that, okay, we needed to add this factor, but somehow they could not estimate carefully, or well, I don't know, they could not provide an estimate for the error uncertainty. So they, as you can see here, they said very conservatively, we give it 100% uncertainty. So this has a large impact on the error bars. You can see, I have a backup slide with this. So, okay, this is from the original CMS paper. You can see that this DPI uncertainty also in all their analysis is very large, and in the one analysis where they actually simulated that using the parton shower PTA, the error bar is much narrower.
Okay, thank you.
Thank you.
We had a question here.
So on slide 19, again, that doesn't include any uncertainties from the Monte Carlo integration, and that's small in this case, because if you go back to the previous slide, they're, in the distributions at least, there are quite large bin-to-bin fluctuations.
Yes, so these vertical bars here are the statistical uncertainties from the Monte Carlo integration. So yeah, there are some, well, you can see it here, there are some fluctuations here which will probably, well, in order to flatten it out, will require to increase the statistics. So yeah.
Is that dominantly from the real contributions?
Yes.
Or does it also have some from real virtual? Do you know?
No, unfortunately I do not remember this,
okay.
But I will let you know.
Thanks.
We have a question right here.
So do you have any idea of how to extend your analysis to non-planar diagrams? Or do you have any numerical estimates on what the non-planar contributions might be to these kind of processes?
Yeah, so thanks a lot for the question. So the first answer is that, I mean, I'm really confident that it will be possible to do the same for the non-planar diagrams. So well, so there's two non-planar families. One is the hexagon box, for which the canonical differential equations are already available. They are substantially more complicated, but we already did some analysis and we already know that we can do this. So the point is that it doesn't make sense to do it only for this family without having the other non-planar family, because you can't compute an amplitude including only some of the non-planar integrals. And for these ones, I also am very confident that literally the same approach will work. I mean, based on the experience with the massless cases, we can say that most likely the numerical evaluation will be more challenging, so the evaluation times will not be 0.2 seconds, in double might be 10 times that, or this is the kind of factor that we see in the massless case, so we expect that it will be similar also in this case, but still this is perfectly suitable for phenomenology because, for instance, the non-planar massless pentagon functions have already been used for phenomenology, for diphoton production, for instance, the gluon channel. So from this point of view, I do not expect there will be any major problem. And your second question was about whether the non-planar corrections are required, and well, this is a very perhaps process-dependent statement. So for this process which we studied here, I didn't mention it, but I wrote it in the slide, we see that the double virtual corrections are just 5% in the inclusive case and 10% in the exclusive case. And if you do a naive counting and say that, okay, the non-planar correction will be suppressed by 1 over nc squared, then you see that, okay, they will contribute, but most likely that they will not be, I mean, they will fall within the very large error bars that you see here.
Other questions?
Thank you very much for that wonderful talk. I was wondering on how many numerical evaluations, how many evaluation points did you need for the reconstruction?
For the reconstruction, yeah. So in the end, so let's say that if you were to employ just, well, okay, I have some backup slide, but let's not go there. So if you were to employ just standard rational reconstruction algorithm, the way, for instance, they're implemented in finite flow without using any extra information about the physics of it, this would require millions of phase space points, roughly speaking. Now, we implemented a number of strategies to improve on that by, for instance, knowing that the denominators of the rational coefficients factorize in terms of letters of the alphabet, for instance. This allows you to guess basically all the denominators very efficiently. And then we implemented over finite fields partial fraction decomposition, which also kills a lot of the complexity. So in the end, yeah, so the problem is that we computed many amplitudes. It's hard for me to remember how many points for each of them. But if I remember correctly, for this one, it was order 100,000 points.
Mm-hmm. And you partial fractioned in the dimension, or?
So we partial fraction with respect to one of the kinematic variables.
Okay, thank you very much.
Thank you.
Okay, perhaps we should move on to the next speaker. So let's thank Simone again.
Thank you.
So our last speaker for this session, Nathaniel Craig, will be joining us via Zoom. Can you hear me, Nathaniel?
Yes, I can. Can you hear me okay?
Yes, fine, go ahead.
Great, thanks very much. Well, thanks very much to the organizers for putting together Amplitudes. Every year it's always a delight when Amplitudes comes together, and thanks for the invitation to speak. I do want to apologize to everybody for not being there in person. I know that a Zoom talk is no substitute for being there in the flesh, but I really appreciate the opportunity to speak remotely. I'm actually here in Aspen now at the Aspen Center for Physics, and in the middle of an effective field theory program where most of the people here, of course, are also at least adjacent to the Amplitudes community. And I think that really speaks to what's been a very remarkable convergence of the Amplitudes and EFT communities in the last few years. So what I'll talk about today is the relation between amplitudes and what I'll call the functional geometry of effective field theories. And so most of the talk is just explaining what that actually means and why it's interesting. So this is based in part on work done with Tim Cohen, Xiaochuan Liu, and Dave Sutherland. And here I really want to highlight Xiaochuan and Dave, the postdocs on the project, who I think really had all of the key insights. Tim and I were just fortunate to be part of the endeavor. Of course, this also coincides with independent but very closely related work by Cliff Chung, Andreas Helset, and Julio Parra Martinez, and I think Julio will tell you about that on Friday. So, geometry, amplitudes, and EFT seem to be fairly closely intertwined these days for a lot of very interesting reasons. I come at this primarily as someone who thinks about physics beyond the standard model, and there, of course, what we're endeavoring to do is take the vast space of possible UV completions of the standard model and recognizing that given what we have from LHC data and other places, there appears to be a mass gap between the standard model and everything else that naturally suggests distilling all of these things down to their infrared imprints in an effective field theory. So of course, the way we've pursued that systematically in the last few decades is, as Weinberg taught us, which is writing down an effective Lagrangian containing irrelevant operators organized by the symmetries and the particle content of the standard model. But as we know, and I think this is particularly well appreciated in the amplitudes community, that approach, while very systematic, is plagued with all sorts of unnecessary complications, in particular the redundancy of description that comes from change of bases associated with integration by parts and equations of motion. And so, there's a cumbersome procedure of defining an operator basis, doing manipulations to get into that basis, and then using that to actually compute observables. But of course, the observables necessarily, particularly the scattering amplitudes, they only depend on invariant combinations of Wilson coefficients. And so this intermediate step that Weinberg taught us to do actually introduces a lot of complications that can somewhat then obscure the connection between the actual scattering amplitudes and the theory, the structure of the UV physics that we're trying to get access to. And then the fourth thing that we have to bring into this, of course, is the actual measurements that are made, in particular at the LHC, where right now the collaborations are again interpreting the measurements in the context of Wilson coefficients in some basis and some effective field theory, which also has some advantages, but also can obscure some of the physics. And so one of the reasons I think why geometry is playing an increasingly interesting role in the last few years is it really provides a very useful bridge between these very different perspectives. It allows us to understand sort of universal behavior of particular types of UV theories. Geometric quantities, of course, naturally encode the redundancy of description, or they naturally accommodate the redundancy of description and connect very naturally to amplitude. So there's sort of a nice interpolating object between the amplitudes community, effective field theories, and the UV theories we're trying to get access to. Okay, so the way this, of course, has been done by the way, I should say the geometry I'm speaking about, geometry comes up a lot in the amplitudes community these days in connection to effective field theory. The geometry that I want to talk about now is really field space geometry. And the way that that's pursued has been more or less constant for the last few decades. The basic idea being, I have an effective field theory. I'm going to focus on a scalar effective field theory, but of course it generalizes naturally to fermions and vectors. And the basic idea is that the two derivative terms in the effective field theory define a metric on the scalar manifold, and we can consider the geometry that's given by that metric. And so from this perspective, fields are just coordinates on the space of field values. What you should keep in mind when you do this, of course, is you're considering all of the fields or some basis of fields at a particular point. So this is what you might refer to as sort of a target space construction. And in this picture, non-derivative field redefinitions are just coordinate transforms. So that naturally suggests using a geometric language in which covariance under coordinate transforms is very, very powerful. So with that in mind, you can use geometric quantities to naturally connect your effective Lagrangians and their scattering amplitudes, accommodate this sort of redundancy of description. You can use the geometric invariants to classify EFTs to understand some of their universal behavior. And of course, you don't have to worry about the redundancy of field redefinitions. So this has a long history, mostly from nonlinear sigma models, but it's really undergone a lot of revival starting about 2015, 2016 in connection to the LHC and thinking about effective field theory embeddings of the standard model. So just to give you a sense of some of the value or some of the things that we've learned in the last few years that connect amplitudes, geometry, and effective field theories, particularly for the LHC. Of course, I think it's again been well known, particularly among aficionados of nonlinear sigma models, that amplitudes can be expressed in terms of geometric quantities on the field space manifold. So just to give you a very concrete example, for example, in what's known as the Higgs EFT, which is the EFT contained in the standard model in which the singlet scalar Higgs that we've seen is accompanied by Goldstone bosons. If you just consider the scattering of two Goldstones, longitudinal modes of W and Z into, for example, a pair of Higgs bosons, what you see is, for example, the leading and energy behavior of that amplitude is just the sectional curvature in a particular direction on the EFT manifold evaluated at our vacuum. And so that's sort of a beautiful, if you computed this, of course, in some arbitrary EFT basis, it would depend on some complicated linear coefficient, linear combination of Wilson coefficients. But in a geometric language, it's very natural. It's just probing the sectional curvature of the field space manifold at our vacuum. And this is, again, sort of a surprising thing if you just start with a generic basis in an effective field theory. But one of the nice things about geometry is it sort of gives you a preferred basis for EFT Lagrangians that connects most directly to the amplitudes. So in particular, if you're interested in seeing the geometric structure emerge in the amplitudes, the natural thing is to work in a field parameterization that's basically just normal coordinates. So if you use the exponential map to start with whatever your original field basis is to transform to normal coordinates, the Lagrangian of your effective theory in normal coordinates actually just, the coefficients of the terms in the Lagrangian naturally are the geometric quantities in the theory. So just giving an example here where the two derivative bilinears are just proportional to the metric, and the two derivative four field terms are just proportional to the Riemann tensor of the theory. So there's sort of a nice preferred basis. And again, this is a way in which geometry helps us to organize effective field theory with the amplitudes in mind. Okay. And so I think the other thing that's become increasingly appreciated over the last few years is that that this geometric picture really has a lot of value. I think a historical criticism is that if you were, we're measuring scattering amplitudes around our vacuum, there's really not a sense in which we have access to the rest of the EFT geometry. And so what is the point of talking about it? But I think something that's been increasingly understood is that as you study the scattering amplitudes of an effective theory, as you go to higher point, those scattering amplitudes really begin to probe the geometry of the field theory more completely and not just give you access to information at your vacuum. So again, using the Higgs EFT as an example, if you just study the 2-to-2 scattering that I just mentioned, of course, that measures the sectional curvature of our vacuum. But if you start to study 2 to n, where n is greater than 2, that begins to depend on derivatives of the sectional curvature. And of course, what those derivatives of the sectional curvatures are doing is they're beginning to reconstruct the Taylor expansion of the sectional curvature away from our vacuum. And so if there's some interesting feature in the geometry of the theory, for example, maybe there's a singularity somewhere on the manifold that tells you about the symmetry structure of the EFT, you actually can have access to that singularity structure, even if it's far from our vacuum, by probing higher point amplitudes. And so this turns out to be a very productive strategy, for example, for trying to understand whether the electric symmetry of the standard model is linearly realized by the Higgs that we've discovered by measuring the higher point amplitudes. Okay, so hopefully I've convinced you, geometry is a very interesting interpolating object between effective field theories and scattering amplitudes, and it gives us some very interesting insights. So why is it not sort of obviously and ambiguously the thing that we should always be doing? And of course, the answer is implicit in how I've told you about it, which is that naturally speaking, this is the geometry is something that's constructed out of the two derivative sector of the theory, and then you can of course imbue it with information from the potential from the zero derivative sector. Okay, but it doesn't necessarily include 4 and higher derivatives. And there's an immediate, a disappointment in that is that if you don't have 4 derivatives in the picture, you don't have access to positivity bounds, which we are all very excited about, particularly in the last few years. So this Riemannian geometric picture has no access to positivity bounds. But there's even something more pernicious, which is that if you are not including information beyond 2 derivatives, the geometric invariants that you're using to characterize your theory in a coordinate invariant way, of course, they're susceptible to derivative field redefinitions. We know that the S matrix elements should not be susceptible to them. but this geometric picture only accommodates non-derivative field definitions as coordinate transforms. So just to give you a very concrete example, if you started in some basis of fields where you had some metric associated with your two derivative term, and you did just a simple field redefinition that translated your field by some correction that included derivatives of the original field, you would end up with some effective Lagrangian where you'd actually change the metric, and of course not just shifted the metric in some superficial way, but then if you computed, for example, the Ricci scalar, you would find a different answer. And it's because, of course, the information that was originally contained in the Ricci scalar has now been translated into the higher derivative sector of the theory. Okay, so you lose the ability under derivative field redefinitions. You lose this sort of access to physical quantities. And you might say, and this is the historical perspective people have taken, you might just say, just don't do that. You know, pick a basis for your effective theory, calculate the geometric quantities, and then leave it at that. Don't attempt to carry out derivative field redefinitions. But of course, that's not a sufficient strategy. So derivative field redefinitions, usually arise whenever you do a basis transformation or use equations of motion and manipulating operator bases. And also derivative field redefinitions, they're actually something in an effective field theory that arises if you do a non-derivative field redefinition in the UV theory. And so you really would like your effective, that's a class of transformations in the infrared that is related to very simple basis transformations in the UV. And so it's really quite important to be able to capture it. And of course, if you don't care about any of these subtleties, maybe you do care about positivity bounds. And so maybe that's good enough motivation to try to extend this geometric picture. So this is really the motivation for the work that we've done earlier this year. And the main idea, the sort of animating spirit of our approach is to go entirely off shell and to switch from studying fields all at one space-time point, so the sort of target space perspective, to fields at every space-time point, which you might call the configuration space perspective. In other words, rather than extracting a metric, just thinking about a Lagrangian density defined at some point, we should instead think about the fact that we're dealing with an action, and we should think about the configuration fields at all of the points in space-time. So as we learned when we were sort of partway through this endeavor, this is not unlike an approach advocated by DeWitt in his attempts to construct a fully covariant approach to quantum field theory. And so one thing that we got from that, I think as far as we know, DeWitt didn't end up where we ended up, but he did develop some very useful, very compact notation, which once you get used to it can be very powerful. And so I'm going to adopt that notation in what follows. So the basic idea is to take all of the sort of flavor information of the fields, but also the space-time information, the space-time coordinates promoted to a single index, and also to make an absurd shortening of integration over space-time into just a contraction of indices. Okay, so that makes deceptively simple expressions. And so then in this notation, the objects you should keep in mind, we're interested, of course, in the path integral with some sources, and then there's a simple relation, obviously, to the generating functional or the 1pi effective action in this notation. Okay. So this functional geometry that I'll try to tell you about and persuade you is the correct approach. The interesting objects from this perspective will be what I'll call the amputated correlators. So these are the things that are very simply related to the scattering amplitudes. The basic idea is the amputated correlators, they're just obtained by some number of functional derivatives of the generating functional with respect to the sources, and then you tack on inverse propagators. So as we know, this is sort of textbook construction of scattering amplitudes. These amputated correlators, right, they can be constructed in a sort of diagrammatic way as the sum of tree graphs that you accumulate from some k.1pi vertices that are just k functional derivatives of the 1pi effective action, and then some propagators, which are just, of course, two derivatives of the 1pi effective action. And then, of course, these objects, the amputated correlators, we get to the amplitudes by setting the sources to 0 and tacking on the external wave functions in the usual way. Okay, so I won't be talking directly about the amplitudes. I'll be talking about the off-shell amputated correlators, but then the consequences for the amplitudes follow directly. So once you are sort of persuaded that it's useful to think about this configuration space perspective, then there's sort of some natural things that suggest themselves as being a metric and a connection. Right now, I'll just present them to you, and then I'll try to give you some justification for them. So the thing that will play the role of the metric from this perspective is just the inverse propagator, so two functional derivatives of the 1pi effective action. And the thing that will play the role of the connection is the combination of a propagator and three functional derivatives of the 1pi effective action. And so, at least squinting at it, of course, it has what you might call the right index structure. where again, these indices are these generalized width indices that carry the space-time and flavor information of the fields. Okay, but that's probably not persuasive to you that these are geometric objects. These are just things with the right number of indices. But the first argument I can give you that these are useful generalizations of familiar geometric quantities is they reduce to the sort of familiar target space geometric objects when you restrict them to what you might call constant field configurations. So target space geometry, that corresponds to taking this configuration space and then restricting yourself to configurations where the derivatives of the fields vanish. Okay, so if you start with now restoring the flavor indices, again, just some theory that has a scalar potential and some metric given by the two derivative terms, if you look at the appropriate transform of this generalized metric I've given you, in fact, it gives you something that's proportional to the constant field to the target space metric, plus two derivatives of the scalar potential. So in these constant field space backgrounds, it restores the familiar geometric objects. And this is true, I've given you the example of the metric, it's also true for the connection. So, you can, at this point, you can go ahead and carry out a full functional geometric, again, I've just given you some plausibility arguments, these are good objects, and you can go ahead and carry out a sort of functional geometric approach to characterizing your effective field theories in exact analogy with what's already been done in the target space approach. But what I want to now tell you about is some interesting things that emerge from this perspective that both give you added confidence that this is the correct set of geometric objects, but also I think give us something new that we didn't necessarily know about before. So one reason we were persuaded to make these identifications of sort of a functional geometric metric and a connection is that they actually come together to give us a very interesting recursion relation, off-shell recursion relation, that relates amputated correlators with a different number of external legs. So the observation here is that if I have an n+1 leg amputated correlator, I can actually write it in terms of an n leg amputated correlator by acting with I'll call it a covariant derivative. That covariant derivative is a combination of a normal functional derivative and this connection. And there's the way that the connection, of course, combines with the n leg correlator. The index structure is slightly intricate, but it basically contracts in the natural way. And so this is very interesting. So one thing is it gives you added confidence that these are the correct geometric objects because they combine in a useful covariant derivative that acts in an appropriate way to generate parallel transport of these sort of correlators on the field space manifold. But not only, so that's sort of an interesting confidence builder in the geometric objects, but also this statement itself, this equation itself is, to my knowledge, it's a new form of off-shell recursion. It allows you to construct n+1 leg correlators starting with n leg correlators. Now, it's not, at least at face value, it's not obviously a very practical form of off-shell recursion. More it reveals the in-principle structure of the correlators. But you can, with sufficient manipulations, you can use it to regain things that we already know about. For example, variance Gila off-shell recursion through some straightforward manipulations. Okay. Just to prove to you that this statement is true, that in fact you can generate n+1 leg amputated correlators from n leg amputated correlators by acting with this sort of functional covariant derivative. Keeping in mind again that the n point correlator again is just the sum of graphs of these k.1 pi vertices and propagators. Now you can piece apart the terms in this expression. So generally the n+1 leg amputated correlator, again, I claim I can write as the functional derivative of the n leg amputated correlator plus tacking on this connection to the n point amputated correlator. And then to see that in fact this is true, if you break down the first term in square brackets, you get two types of pieces depending on what objects the functional derivative hits. If it hits one of the k.1 pi vertices in your n leg correlator, then that of course just pulls out another external line from that vertex. But you can also hit a propagator in the n point correlator, and that will now pull a line out of the propagator. Okay. Then finally, you can take a leg, and by tacking on the connection, what that's doing is splitting the external leg of the n point correlator into two legs of the n+1 leg correlator. And so indeed, the sum of these, and you can just prove to yourself diagrammatically that the sum of all of these additions to an n point correlator is in fact the definition of the n+1 leg correlator. You can also prove this statement not diagrammatically, just by using some straightforward manipulations in the definitions. So it's a surprising relation. We didn't know it was true. And so it really suggests there's a sort of a deep connection between the functional geometry of these objects and the amputated correlators, which then give us the amplitudes. Okay, so what I've tried to do is motivate to you a sort of generalization of field space geometry that it reveals some interesting properties and reduces to the conventional objects in appropriate limits. But of course, the motivation I gave to you, one of the motivations I gave to you for starting this endeavor is to construct a sort of generalized geometry that accommodates derivative field definitions, or more broadly, that just accommodates effective field theory operators beyond two derivatives. And so that's not yet obvious from what I've told you, but now you can go ahead and see in what sense this approach accommodates derivative field definitions. So to do that, just think about a general field definition of the fields in your theory. And at this point, this is actually the first point. Everything I've told you so far is completely general, is not restricted to tree level in the theory. But at this point, to prove this following statement, I will restrict to tree level, because at tree level, we know that the effective action transforms as a scalar. And so knowing that the effective action transforms as a scalar, you can then show the following, that these amputated correlators, if you constructed out of the appropriate functional geometric quantities, if you do this general field definition, potentially including derivatives, that the amputated correlators, they transform in the following way. They transform first as something that looks manifestly covariant. In other words, that transforms with the appropriate functional derivatives attached to each external leg, plus two extra pieces. But those two extra pieces are special in that both of them vanish on shell. So the first extra piece is proportional to one functional derivative of one pi effective action. That, of course, is just the source, and so that vanishes on shell. And the second piece is two functional derivatives, but of course, that's just an inverse propagator, and that also vanishes on shell. So the statement then is that in this perspective, what you end up with, the amputated correlators are themselves not completely covariant under general field definition. But once we take them on shell to extract the amplitudes from them, then they are manifestly covariant under generic field definitions, including field definitions with derivatives. So this sort of generalized functional geometry, it does give us what we want, although the manifest covariance is at the level of the on-shell objects at the end. Okay. Now, I should say, I mentioned at the beginning of my talk, there is another parallel approach. Julio will talk about this on Friday, so I don't want to go in any detail, but I just want to advertise it because I think it's a sign both of how interesting these questions are and the very interesting different perspectives that we can take on them. So, Cliff and Andreas and Julio took a completely independent and very complementary approach to the same question. And their insight was that you could treat momentum like a flavor index. That's a little bit like the DeWitt notation I've told you about. And their real insight was that an arbitrary theory of massless bosons is at least classically equivalent to a nonlinear sigma model, where you promote the target space metric to something that becomes momentum dependent. And so what they do is they develop a map between just conventional objects in a nonlinear sigma model and then a general scalar theory with a momentum dependent metric. And that mapping then allows them to translate statements about nonlinear sigma models into statements about these momentum dependent geometries. And the conclusions are quite analogous to what we obtained from our functional geometric approach. You can also see that perspectives seem closely related. I think right now we're in the process of trying to understand how they're related in detail. But in any event, I think Julio will talk about this in his talk on Friday. And so I very much encourage you to listen to him complete the picture. Okay, so that brings me to the end. Hopefully I've persuaded you that field space geometry is a very sort of interesting and compelling bridge between UV theories, their effective field theories, and the scattering amplitudes, both motivated thinking about effective field theories of the standard model that we would probe at the LHC, but more broadly, effective field theories in general. But also, of course, I think the main shortcoming of geometry as a sort of interpolating object is that it fails to incorporate information beyond two derivatives. So what I've tried to present to you in the talk today is one approach to this problem, which we've referred to as functional geometry, a sort of configuration space approach that generalizes in a useful direction. It reduces to conventional target space geometry in the appropriate limits, but it also, so that gives us the right generalization that we're looking for. But it also gives us something new. It gives rise to this new off-shell recursion that at least relates to the amputated correlators. And it manifests not covariance of the correlators themselves, but on-shell covariance under general field definitions, which is one of the goals of going past two derivatives. So, of course, there's a parallel approach, this geometry kinematics duality, and I think we're in the process of understanding the detailed relation between that perspective and the functional geometry perspective. And I think, anytime you have sort of multiple, somewhat qualitatively distinct approaches that end up in the same direction, that's a hint that there is a deeper structure. And I think we're in the process of understanding what that deeper structure is. So it's a very exciting time to really work out what's going on here. I should also say, once you have this, it's not just a nice statement that now you can use geometry beyond two derivatives. But of course, for this audience, I don't think I need to emphasize, if you have a geometric picture that incorporates higher derivative terms, that gives a very new and potentially very powerful perspective on questions we are interested in asking about higher derivative terms in effective field theories, for example, related to positivity bounds. So I think there's a lot that we can gain by thinking about the relation between field space geometry and the geometry of positivity bounds. And so that's a huge question that I think we're beginning to pursue. So that's it for today. Thanks again very much. Again, apologies for giving this talk remotely, but thanks again for the opportunity. I'm happy to answer any questions you might have. And I also know I'm the last thing standing between you and coffee. So thanks very much for the opportunity.
Okay, thank you, Nathaniel, for that very nice talk. Are there any questions? Yara?
Hi, Nathaniel. Very nice talk. This is Sierra. Can I ask you, do you see any abstraction to generalize it also to particles with spin?
No, yeah. So in fact, the one of the advantages of it's good. So I'd say in the conventional sort of target space approach, of course, you can add fermions by going to supermanifolds, and you can tack on transverse polarizations with minimal coupling. But that's all a little cumbersome. One of the advantages of going to the sort of DeWitt notation is it actually correctly incorporates all of the information for generalized indices. And so really the only thing you need to do to actually recognize that you are also treating, for example, fermions is keep track of statistics. But that's easy bookkeeping. And so, yeah, there's no obstruction to using this for particles of arbitrary spin.
Thank you.
Other questions?
Here. Hi, Nate, this is Julio. Thanks for a very nice talk. So maybe a follow-up to Yara's questions. Something that we had a hard time in our setup was when we look at gauge bosons to make gauge invariance manifest.
Yes.
Do you think that this is something that in your setup, do you have any idea of how this could be ameliorated? Or?
Yeah, no, good. Right. So we're working on it. So I think it's as for you, it is, yeah, let's see, what do I want to say here? Yeah, so it seems, I mean, in the DeWitt notation, it seems like it is implicit, but understanding exactly how gauge invariance in particular is manifested is not totally obvious, and so it's something that we're still trying to understand. So it doesn't seem like there's a problem, right? I mean, the notation is powerful enough to accommodate it, but I don't think it's something we've been able to make explicit. I think in sort of strangely parallel ways to the way that you guys have also struggled.
Okay, thanks a lot.
Any other questions? Okay, seeing none, let's thank Nathaniel again for a great talk.
Thanks very much, and have fun on coffee.
Okay, that concludes this session. We'll reconvene after the coffee break at 16:15.
Okay, do you hear me, please, Mr. Paolo?
Yes, I do.
Okay, perfect. So please try to share your presentation.
What is a second?
And even, do you hear me well, please? I'm here just technician to be sure if that everything will be ready.
Yeah, I can hear you very well.
Yeah, I hear you well as well.
Okay, that's great. I'm trying to somehow when I do share screen, it gives me just the whiteboard. Doesn't give me the possibility to take. Let's see.
Somewhere on the bottom supposed to be the button to share.
Yeah. No. But when I press share screen, I get just the whiteboard. I don't get my files on my laptop.
But previously, on a beginning, I saw that you already tried, and it was I saw something like the shared
Yeah,
screen.
that was the whiteboard. That when I did the share, they give directly there. Okay, let's see if I can get some minutes.
Take your time. We have enough time.
No. Yeah, but I want this to be solved because. Okay, let's see. Screen share. Okay. Let's see now. Do you see my screen?
Yeah, I see it's written that you have started screen sharing, but that's all.
Okay.
Nothing appear.
Okay. That's
Maybe try to reconnect.
Okay. Yes. Let's do that.
Hopefully it will be okay. Not, it's not necessary.
Okay. Can you hear me now?
No, unfortunately no. It's still written just has started screen sharing and which browser are you using or are you using the application?
No, I'm using Firefox.
Ah, okay. I don't know. The previous speakers has.
Yeah, you know that's also the first time that it's happening to me. Let's see. We have still
when you
screen share.
But the rights are correct for all participants, I see. Just correctly choose probably which screen do you want to share.
Okay. Let's see now. Let's see now. I can.
Or Mr. Try to use the different browser. Or even the application, just download the Zoom application. Have you seen my sharing, please? já mám tady teda dvě prezentace na teďka a pan Trnka mi poslal tady tohleto, já doufám, že to je správný, ale já jsem mu říkal, že nemám toho... Protože... Guevara a je to Pimentel.
Tohle Lens je... Kde je Lens? Lens není dneska. No, Lens je až zítra ráno.
Aha,
ale
jo.
to je ráno, to se hodí, že to je první to.
Jo, to znamená, že nemám Guevaru.
Guevara, se podívám.
Yeah. Sir, please, how this looks like? Sorry, are you muted?
I was just saying that I have problem with my laptop for some reason that doesn't allow me to share. I'll just share the whiteboard, and I'm trying with the tablet.
Okay, so maybe we can start over with next speaker.
Okay, that's fine with me.
Hi, Paolo. Can you hear me?
Yes.
So maybe we just move on to the next speaker, and then if you can just try to maybe install the appropriate application, the Zoom, and try to share from there, and then we come back to you in half an hour.
Yeah, that's great.
Okay.
This is mine and this is the first. Yes.
Okay, so we have a short delay. There's some technical problems, but we'll start in a couple of minutes. Okay, I think that we can start now. So welcome to this last session of today. We have three speakers. There's a slight change in order of the talk. So the first speaker will be Alfredo Guevara from Harvard, and he will talk about gravitational amplitudes from a color symmetry.
Hi, this is working? Okay. Good. Thank you. First, let me thank the organizers for putting together this very nice conference, and especially in this lively city. I'm going to talk about something I've been thinking on very recently, and I've decided to give myself a little deadline, as you can see, just to hold myself accountable. So this is something that should come out this month. We'll see how it goes. Oh. Yeah, I shouldn't have done that. I just wanted to try the pointer, actually. Is this one?
Yeah, it should be this one. So it's right, left.
But there's no pointer?
Oh.
Oh, okay. All right, sorry about that. Okay, so the title of the talk is Gravitational Amplitudes from a Color Symmetry, but there's also this underlying question that I decided to formulate, whether gravity is to some extent integral. And there's a couple of reasons why we would like to ask this question. there is some hints that come from different perspectives. So just to give you an outline of them, first we have integrability in IDS-CFT correlation functions, and we have heard some of this in yesterday's talks. And it is expected that in some sense, in the flat limit, some of these integrability aspects of super Young Mills are preserved in correlation functions of supergravity. There's also a double copy structure, which is a complementary perspective. And in particular, super Young Mills is double copied into supergravity, and so we expect there are some traces of Youngian symmetry even in supergravitational theories. One instance of this is, for instance, the no triangle hypothesis. On a related, albeit complementary front, we have classical gravity. So with or without supersymmetry, we can have these type D spacetimes where geodesic motion is completely integrable, meaning that there is a set of conserved charge that completely determine the trajectory of a test particle in this particular solution, such as kerr. But this is more general. There's no doubt about it, and there are some traces of these integrability aspects even in the two-body problem through the effective one-body formalism, and I'm pretty sure we will hear some of that on Friday's talks. There's also self-dual gravity, which has played some interesting role recently in some related works. In particular, Penrose's construction involving twistor spaces for CP3 bundles realizes self-dual spacetimes and self-dual solutions to wave equations in an integral fashion. Let me just stress out this important conjecture that's not so well known by Ward, saying that all classical integral Hamiltonians are, in a sense, dimensional reduction of self-dual field equations. Last but not least, we have asymptotic symmetries, and so there's an infinite set of conserved charge in asymptotically flat spacetimes that has been discovered very recently. And so when you have an infinite set of conserved charge, it's a very strong hint that there is some integral field equation. All right, in this same vein, let me just state the purpose of this talk. And the purpose is to link some of these approaches to argue that perturbative scattering amplitudes in gravitational theories are, in a sense, universally controlled by an infinite set of conserved charges. And these conserved charges actually organize themselves in something that we call the W1 plus infinity hierarchy, which was recently observed in correlation functions of celestial CFT. So I'm pretty sure we'll hear more about celestial CFT and celestial holography on Thursday. But the point I want to advocate in this talk is that this W1 plus infinity hierarchy is in many ways ubiquitous. So just to give you an example, we know that it's realized in terms of surface charges in completely classical gravity, so no celestial correlation functions whatsoever. We have a hierarchy of charges realizing this W1 plus infinity algebra as shown in this nice work. And also in parallel, we have a gauge theory correspondence to W1 plus infinity, which has appeared in a completely parallel context of twisted holography recently introduced by Natalie Paquette and Kevin Costello. So we will look forward to hear about those in Thursday's talks. So in this talk, what I'm going to do is I want to concern only the momentum space, the usual momentum space S matrix, and I'm going to show that W1 plus infinity is explicit even in momentum space. So the way it emerges in this case is through a large limit of a SUN color theory, and so it provides an instance of the color kinematics duality. So just to give you a flavor in which this context of color kinematics emerges in relation to W, let me just provide the more simple definition of W, which is the symmetry group of area-preserving diffeomorphisms of the plane. So if you give two coordinates on your plane, mu plus and mu minus, essentially you can consider the nonlinear span of those coordinates, so say all polynomials or all regular functions at the origin, and provided this Poisson structure, you will get an algebra of area-preserving diffeomorphisms. And this area-preserving diffeomorphism algebra has appeared in the context of self-dual gravity and self-dual Young-Mills, and it's what we call kinematic algebra of Monteiro and O'Connell. All right, so this is a very interesting connection between different set of algebras appearing in different aspects of gravity. Let me just give you another one, which is sort of the motivation of W. So why do we call it W actually? Well, I don't know exactly why is it W, but I can tell you the original development that led to W was considering an infinite tower of higher spin fields coupled to a CFT. So if you have CFT with just Virasoro, you can actually extend it by a spin 1 current, and that's the 1 in W, and then you can add an infinite tower of higher spin generators, spin 3 and spin 4 and so on. If you add a finite one, it doesn't close, and you get something very nonlinear. It's not a Lie algebra. So you actually need like an infinite higher spin tower in the same way that you would have to have an infinite higher spin tower in the S matrix, right? Just to make it consistent. So W here arises in this, is realized by this OPE of higher spin operators, small W. Okay. More interesting, perhaps, for our context, is that W has a Hopf algebra structure, so it's in some sense associative algebra structure, which is directly related to the Youngian of GL1, so, which has this sort of kinematic flavor. So even there are some traces of integrability there, and I'm pretty sure it's also related to the Youngian of SL2, although I'm still figuring out how that connection proceeds. But there's all these beautiful mathematical papers. Sorry about that. There's this mathematical literature about different connections of W and Youngians since the 80s. So motivated by these interesting connections, we will introduce here a quantum group at finite n, and then we will take the large N limit to define, in a sense, a classical limit in a very similar way that it's done in ADS-CFT. And the suitable framework to make connection with the momentum space S matrix turns out to be the construction of Jens Hopf in the 82. This is actually his PhD thesis. And he actually has a book also in integrability and W. All right, so the way this works, this momentum space construction proceeds by introducing two operators. We call it mu plus and mu minus. These are the quantum version of these generators here on the plane. And they satisfy just the X and P quantum mechanics algebra. So they are, in a sense, canonical conjugates. But we want to quantize this algebra, so we want them to be on a torus, right? So we have to impose this condition that the exponentials to the n are multiplied to 1. And once we do that, we actually find the Heisenberg group. It's a quantum group. So this is the commutation relation. And there's a model parameter, which is a root of unity. And the nice thing about Heisenberg group is that it represents some non-commutative geometry on the torus, and then the classical limit is this large L limit where the torus deforms back into the plane. And you should think of this large L limit essentially as just taking h bar to 0 here, right, where n is like 1 over h bar. So this is the reason that this becomes a commutative classical space. Right, so, but in the quantum setup, we're looking at a quantum torus in a sense. So this momentum, the momentum of the torus is quantized, it lies on this lattice. We find these momentum wave functions, just a simple exponential of momentum. And what we get is n square generators that live on this lattice. And so this form actually a basis of UN. We can remove the identity, which is the zero momentum generator, and we get SUN. So what Hopf noted is that even though the operators mu, plus or minus, do not have a finite dimensional representation, we can exponentiate them and get finite matrices. The reason they don't is because, of course, they are the X and P system, so you need like infinite dimensional spaces. But here you actually can find n by n matrix that does this, that satisfies this relation. So the good operators for us would be exponentials of mu plus and minus. All right, so now we have this n squared minus 1 generator. So what do we do with them? Well, using the Heisenberg algebra, they happen to satisfy a very simple relation. And now I'm introducing this bracket here, which is just SL2R, the SL2C modular invariant bracket that appears, just from this contraction. And so what we're doing now is we take the classical limit. So if you expand in large n, you get like this term and then some other terms. But after you perform a contraction, which is just rescaling by h bar, you get this algebra. And this algebra happens to be the same as what you would get if you use the Poisson bracket, right? That I showed you a couple of slides ago. So it's actually an algebra, it's actually the structure constants of a color algebra, and that color algebra happens to be the large L limit of SUN, which is, as we just showed, W1 plus infinity. So now you may ask, why am I doing all this? We could have just used the Poisson bracket and just derive this constraint, this structure constant just from the Poisson bracket, but there's a very good reason for that. But before I explain it, let me just summarize. So far, we have explained how the large N limit of SUN provides a classical realization of gauge color algebra, which is W1 plus infinity, as an algebra of matrices. The momentum, which used to live on a lattice, now becomes a two-dimensional spinor. So the resulting color algebra is, in a sense, two-dimensional, right? It's two-dimensional kinematics. It has recently appeared in the context of color kinematics in connection with two-dimensional integral systems and also with self-dual Yang-Mills. So this all has the flavor of color kinematics as outlined by these nice papers. But in our context, we want some four-dimensional theory. Actually, we want four-dimensional gravity. And the way we're going to obtain it is we're going to introduce an affine version of what we just did. So by affine version, I just mean introduce an auxiliary coordinate like CP1, and then promote these generators to functions on CP1. They actually are spinors of weight 1/2. So the fact that they are canonically paired immediately implies that they have this very simple elementary OP. And now you can get back the commutators that I just showed you, essentially by taking contour integrals of this OP, right? So we have the sort of structure constant here, and then we have the fine algebra here. And if we take a contour, we can just get back the commutators of the zero modes. But for many reasons, we are going to refer to this as gravitational Goldstone modes, in the same sense that these are not very good operators. As I just explained, these are also not good operators. What we actually need to consider is exponentials. Mu's themselves are actually non-normalizable operators. Exponentials of these operators, as we just showed, satisfy some interesting algebra. Here we're going to consider vertex operators, which are normal order exponentials of the above, and they will represent positive helicity gravitons. The quantum group relation that we just derived actually gets promoted. You have to do some weak contractions and so on. It's almost identical. It just depends on set 1 and 2, and here you have to consider that set 1 and 2 are different points, and you get this normal ordering here. So it's the analog of the quantum group relation. And we can take the OPE limit now, and we get, in the large N limit and in the OPE limit, we just get this simple relation, which is nothing but the Kac-Moody affine algebra to this group, right? So we just replace these structure constants here, and there is some spin 1 current that gives you spin 1 and this pole. Okay, so this is the OPE from classical limit. So what happened is just we started with a two-dimensional color structure in which color essentially was a two-dimensional kinematic spinor, and we added a worldsheet coordinate. And once we have this two-dimensional worldsheet coordinate with two-dimensional color structure, we actually get four-dimensional kinematics. And the most important point that I didn't stress here is that we are working on 2,2 signatures. So that allows me to sort of separate sets, which you should think of lambda, and lambda, which you should think of lambda tilde. And I think I was too lazy to put all the tildes in all the slides, so you should think of lambda here as just tilde. So this is the way I will get four-dimensional kinematics by combining color and the worldsheet. All right, so just to summarize, we have derived this Kac-Moody algebra. You should think of it this way. Essentially, the color structure constants have just some particular form in terms of spinors. But other than that, it's just a usual level 0 Kac-Moody theory. It's not unitary, but at the same time, we are at 3 levels, so we don't care. And what we can do with this Kac-Moody theory is that we can add matter content in the form of adjoint fields, right? So if we add adjoint fields, essentially we just have a copy of the structure constants, and then the OP relation is virtually the same. The nice thing about this is that you can rewrite this sort of shift in the kinematics in exponential form. And then if you think of this as an operator in quantum field theory, you will have to write this operation in terms of only the angular momentum generator. So if you write in terms of the angular momentum generator, this is how it looks. So it has the flavor of something that we call the exponential soft theorem. Just because the exponent here looks like a soft-leading soft theorem. So in this way, we relate that to the soft-leading soft theorem and higher corrections to it. This has appeared in many different contexts, and it has diverse applications. One is black hole physics. So just to give you like a little of an application, we can actually reproduce this computation, but instead of massless fields, we consider massive fields. Once we consider massive momenta, the direct translation of this factor gives you this. If you have like a classical spin, this factor becomes just a spin vector or something. And then this OPE actually reproduces what we define as a black hole graviton coupling. So you can compute the OPE between an operator that reproduces a black hole and a graviton. The interesting thing is that you can reproduce the black hole metric out of this operator. So this is some work we have been doing with some people at Harvard. to appear, but let me just focus back on what I want to discuss for this talk, which is essentially computing gravitational tree-level amplitudes, right? So the simplest instance of this is just MHV gravity amplitudes. Suppose you have a Kazmui theory of currents. The way you compute correlation functions sort of recursively is by acting with one of them, sort of doing this contour deformation and then picking up the OPE poles, and then you may eventually get an infinite, a residue at infinity. This residue at infinity is just some polynomial term. It's actually required because we don't really have momentum conservation on the set variables. We have momentum conservation on the lambda variables as implemented by this shift here, but the set variables are kind of free. This is just another way to say that we can fix this residue at infinity by imposing momentum conservation in set variables. And after we do that, the exponentiated expression that we see here actually matches the usual BCFW result for MHV, otherwise known as the Hodge's recursion formula. So this is just a way in which we can recover the gravitational amplitude using just the OPE. All right, but even if you have the OPE and you have these recursion formulas, what you really need is a seed, a 3-point amplitude. So let's see how that works explicitly. So to recover the 3-point amplitude, we have to add something that represents a negative helicity graviton. And the way that the negative helicity graviton appears here in this context is just a spin 0 scalar field. So if you have spin 0 and spin 1, the only way to couple those things is through a delta function. And essentially, you can think of this as the color, version just being a delta function in color times a delta function in Z12. So you allow yourself for contact terms because you're in 2,2 signature essentially. So after some analytic continuation, you essentially identify this pole with a delta function as well, and you can compute this 3-point function. What you get is just a structure constant, and there's these two singularities that come from the OPEs. And if you just expand the structure constant, remember that the structure constant knows about this momentum conservation, times some Jacobian factors, and in the end of just looking at the Jacobian, you will reproduce exactly the 3-point MHV graviton amplitude times the delta 4 conservation delta 4 momentum conservation function coming from structure constants and the singularities. So in this framework, actual momentum conservation, which was not implemented in the CFT, is sort of emerging from this color structure constants. So it has the spirit of the color kinematics duality. All right. So in the last couple of minutes, let me just explain how to connect to soft physics, which is kind of the original motivation for this work. So far we haven't really considered soft momentum. We have considered generic momentum. But we can connect to the soft momentum just by essentially doing a soft expansion of our vertex operators. And the motivation for that is that essentially this OPE here just kind of resembles the sort of exponentiated soft theorem that has appeared very recently in these works. And so it would be nice to actually understand the full soft expansion in terms of this vertex operator. So the way we do it is we expand in lambda. We don't expand we expand in lambda tilde, but not in lambda. So if you have something which is holomorphic in lambda tilde, you can define this essentially. As essentially. This is somehow a generating function for these operators, which are normal order products of mu's. And so you can compute now OPEs with these operators, which are essentially multiple moments of G. So the first operator you can compute just a single insertion of mu with a generic matter field, and you get that it gives lambda. So that's exactly the action of translations. You have to remember that lambda here is half the momentum. If you have the quadratic generator with 2 mu insertions, what you get is a derivative. So this is exactly an angular momentum operator, so that's Lorentz group. If you have 3, the cubic generator actually gives you 2 derivatives, so it looks like a Heidegger derivative extension of Poincaré. It involves a conformal group, maybe, perhaps. And then you just can just keep going, so it looks very much like this Youngian hierarchy. And it actually satisfies a very simple commutation relation, which is given by this. This form is kind of the only form that you can write that is SL2R invariant. And after some work, indeed, you can show that this matches precisely the hierarchy that was introduced in this paper, which is what is referred to as the wedge loop algebra of W1 plus infinity. And so I hope we hear more about that on Thursday. And so this is exactly a way of organizing all these generators in a way that's systematically encoded in, from the W1 plus infinity algebra. And it consists essentially of a higher dimensional extension of Poincare group, but by something that we call higher derivative operators. Okay, so just to summarize what we have done, we have derived a kinematic algebra first, starting from a quantum group structure, which was quite rigid. In fact, it was the Heisenberg algebra associated to SUN. Then we have used 2,2 signature that allow us to incorporate 4D kinematics directly from the 2D sort of celestial worldsheet coordinate plus two-dimensional color structure. Then we have taken the classical limit, which is the large N limit, in momentum space directly, and we have obtained a representation of W in which scattering amplitudes actually transform under adjoint multiplets of the symmetry. I unfortunately forgot the reference here, but there are many references for actual corrections of W. One of those is by the Brown group, by Bolovich and her group. But there's also a group at Harvard that's currently working on corrections to W, and it would be interesting to see how these approaches merge with the quantum group structure that I just presented. And finally, we have a symmetry that provides an organizing principle for asymptotic charges. So if you look at classical gravity asymptotically, you have all this expansion in terms of 1 over r and log r's and so on. And it is expected that a symmetry principle would eventually organize them in a systematic fashion. And by now, we already know that W generators actually compute certain kind of charges that generalize the very well-known tower of Newman and Penrose that was first introduced for QED, and it can be generalized actually for interacting theories like gravity. So I guess that's it. So thank you so much for your attention.
Thank you very much for your talk. Do we have any questions?
Hi, thank you for the talk. It still felt like these were all kind of chiral algebras. So why do you expect that the complete theory will be ruled by this?
Yeah, that's a good question. So if you take a anti-chiral, say, negative helicity graviton, you can turn it into an operator that looks chiral if you do the so-called light transform. That's actually kind of what's behind this scalar field. I didn't really explain it, but this actually comes from a light transform of a negative helicity graviton, which was chiral, and then essentially integrating over the anti-chiral coordinate gives you this field. So I'm not saying that this works at all orders, but I'm saying that it's possible that by incorporating these sort of light transforms, which are not in the spectrum of the S matrix, we will be able to reproduce the actual momentum space S matrix.
Thank you.
Lance?
So there are these self-dual one-loop amplitudes. Are they acted on by this symmetry?
Yes. So in this talk, I only discussed three-level amplitudes, but there are recent works by Andy Strominger and collaborators that show that this W actually acts on one-loop self-dual gravity amplitudes. Yeah, and it's uncorrected.
It's uncorrected. Okay. Thanks.
Thanks for a nice talk, Alfredo. Actually, about this slide, so here you're using this OP, essentially 3-point factorization, which is the usual BCFW recursion for the MHV amplitude, but starting at 6 points in MHV, there's like multi-particle factorization. So how do you envision that this will be captured by some sort of OPE?
Yes, good. Yeah, that's a good question. So thank you. Actually, we have some idea how this works. I didn't explain it in this slide, but one thing that happens even in this term is that the way this term enters is by acting with Kac-Moody descendants. So the usual Kac-Moody descendant equation, which is so-called KC equation, actually gets corrected by this term, and so it's expected that also the Virasoro descendants would play a role into these multi-particle singularities. But that's a good question, and for sure I will try to answer it more precisely.
Last question here.
Yeah, so thanks for a very nice talk. So in your conclusion, the last point, you said that this algebra organized one of our charges. So can you say that, so usually you have the translation and the second one give you momentum, angular momentum. So what are the conserved charges beyond these two, and do we have new information from these conserved charges?
Yes. So one thing you can do is you can take sort of this OPE and start looking at this correlation function and start looking at zero modes. The zero modes are these global symmetries that I think you're referring to. And if you look at the zero modes, well, you find that at leading and subleading order, the zero modes actually annihilate the vacuum, but at higher orders, they don't. And then there is some transformation of the vacuum that you need to implement. I presume that after that transformation is included, you may be able to define a conserved charge, which has this sort of extra term. Yeah.
Thanks.
Okay, let's thank Alfredo for his talk.
Hello.
Okay, so the next speaker is Guilherme Pimentel from Pisa, and he'll talk about differential equations for
cosmological correlations. Sorry for the handwriting. Okay. All right, so this will be based on work with a series of collaborators over the years, and I'll highlight some recent stuff with that is not published yet with the people underlined here in the beginning. And let me just acknowledge also lots of people that I interacted with over the years that informed my understanding of this subject. And Paolo in particular, who should appear eventually on Zoom for the next talk. And disclaimer, well, my handwriting is big, so I don't put references. It gets the slides very busy. If you want to know references, you can come ask me. And just as a little bit of bailing out, for Snowmass, I participated in these two review papers, one about the status of inflation, both from a theory and observational perspective, and the other on a more technical part that will be the focus of this talk on computing cosmological observables for the early universe. So you can look there, there's a fairly exhaustive list of references. Okay, so before I give you the talk, I'll tell you the result of the talk so you can doze out if it gets boring. So I will, this is some sort of a diagram that is supposed to show how the seeds of structure formation of the universe are deposited at the hot Big Bang. So time goes up, this is the surface of what we call the hot Big Bang. And there are some primordial density fluctuations around which matter, light, stuff will cluster. That's why we're here. We think that they came from quantum fluctuations in some earlier era that got stretched to cosmological distances. And we would like to understand how to compute this diagram. As you see, it's tree level. but because it's in a curved background, it's not so easy how to compute it. And for a toy model, we're going to compute it in any power law cosmology. I dialed the power law by changing the parameter epsilon. It's not going to be necessarily small during the talk. For this toy model, it's really a function of only two kinematical variables related to what's happening on the left and on the right. And this boils down to an integral that's pretty damn hard to compute. And then thanks to some beautiful work on amplitudes, you can recast it in a very simple system, a linear system that depends on some matrix A. I'll get to that during the talk. And then you can just beat it to death and do whatever you want, find all sorts of amazing relations for this diagram. So that's the main results. Okay, so if these words make you happy, then you should keep paying attention to the rest of the talk. I put amplitudes to try to get a lot of the audience excited for the rest of the talk, but there are some more technical words here that maybe will make you interested. Very good. So now, what is the motivation? Well, we want to understand the beginning of the universe. So this is a cartoon of our standard model of cosmology, how we think stuff like was formed and so on. So here, time goes up. We can measure from direct observation pretty much from the moment that the photons decouple from the plasma that emit this cosmic microwave background radiation to galaxy formation, some scaffolding of dark matter. It seems to be necessary. Here we are, we observe the two-point function of the distribution of galaxies, the two-point function of the distribution of radiation, and we can relate that to very simple initial conditions that were famously imprinted at the hot Big Bang. They look highly acausal because they're imprinted over large distances that naively time equals 0. And we have some paradigm for why we think this happened. We think that there was some earlier era of inflation in which the universe undergoes accelerated expansion, and then spontaneous particle production gets these pairs of particles stretched over long distances and generate this two-point function. It's almost scale invariant. There's a small tilt that you actually measure from the data and some amplitude. So these are 2 out of 6 cosmological parameters. So they play a pretty important role. Even though the model is called lambda CDM, it's not just cosmological constant and dark matter. Initial conditions are as important. Okay? So this talk is all about the initial conditions. So we would like to understand how to compute these initial conditions, how to understand them. What we see from the data is coming from the two-point function, but more ambitiously, we would like to measure, for example, a 3-point function, a 4-point function, and computing these things from bulk perturbation theory is complicated. You have some time integrals that you need to do. These are generically some complicated mode functions. For example, you would imagine that if you could measure some non-trivial correlation among various density fluctuations, you'd be able to do particle spectroscopy during inflation. There are some extra species whose power gets redshifted too fast, doesn't survive till the end of inflation, but might leave some interesting imprint at late time. So how do you compute this prediction, and how do you get some interesting, reliable prediction for what you should see in the data? Okay? So the idea of what we call cosmological bootstrap is to try to, following the on-shell philosophy of amplitudes, try to anchor yourself to the surface in which measurements are actually made, or at least the farthest you can push the standard cosmological model, and then ask a question here, some self-consistency question, and hopefully the self-consistency question is so constraining that you can actually solve the problem from different means. And this has been fairly fruitful the past few years. We did it in the sitter in 4 dimensions, very symmetric arena, so lots of power from symmetry coming in. But it turns out that you can even do it in other arenas in which you don't have that much symmetry power, and you can still make progress from these basic principles of locality, unitarity, and so on. More technically, the upshot of this new point of view is that you can recast the time evolution that bulk perturbation theory would give you explicitly by a differential equation and a set of singularities. Actually, okay, that's annoying. There was an earlier slide with the differential equation. So there is a differential equation satisfied by this correlator that essentially allows you to act on the left momenta and collapse the diagram. If you wish, collapse the green internal line related to a contact diagram that is simpler. So there's a differential operator that knocks down the complexity of the answer. And moreover, there's various specific singularities that should appear in the correlator that come from the fact that you're doing a weakly coupled, tree-level approximation, and so on. And the differential equation actually, if you try to build a differential equation compatible with locality, etc., with all the right singularities, there are 3 of them for this example. It's essentially zooming in to the left or to the right, or zooming into the whole correlator at once. If you try to do that, you generate some spurious singularities that you should forbid in the physical answer. So these are the set of singularities that will appear in this simple diagram from this bootstrap approach. Okay, so the main question behind my talk, if you wish, is where do the differential equations come from? It's actually extremely annoying that the differential equation didn't. Can I write on the... So there's a differential operator, let me call it delta, that will depend on K1 and K2, plus something that depends on the mass of the exchange particle. Let's call mass of the exchange particle, m squared. Looks like a Klein-Gordon operator. If I act, I hope it's visible. If I act on this exchange diagram, I'll get a simpler diagram. It looks like a contact interaction. So that's the philosophy. And then the question is, well, you know, this differential equation, did it appear just because you had a ton of symmetry at your disposal? Where do these differential equations come from? Can we derive them like systematically? It's a bit of it's like baking. It's not, it's more of an art than a systematic science. So that's the basic question. And then here's a model where we can bring some new understanding to this story. So this is a toy model. Unfortunately, it's just too toyish to be relevant to observations yet. I think that it captures a lot of beautiful structure that hopefully will be applicable to the real observations eventually. So this is a toy model of a self-interacting scalar field that I'll tune the mass to the cosmology. So now I'm allowing the cosmology to be not necessarily the Sitter space, the most symmetric inflationary arena. For example, I can give it some phi cubed self-interaction. And now I can dial the power law in the warp factor, in the scale factor, as a function of epsilon. Actually, all interesting cosmologies are specific values of epsilon. So epsilon equals 0 is de Sitter, epsilon equals 1 is flat space, epsilon equals 2 is radiation domination, epsilon equals 3 matter domination. And the first non-trivial thing is that, okay, you have to integrate over these 2 insertions. But there was some beautiful work done by Nima with Postnikov and Paulo Benincasa, recasting bulk perturbation theory in terms of integrals over a rational function, okay? So now these little x's are integration variables. They are roughly a repackaging of the time integrals here. Very useful repackaging, let me stress that. And these big X1 and big X2 are some kinematical variables related to what's happening on the left, what's happening on the right. To make my life simpler because of some scaling symmetry, I set the exchange momentum to 1. That's why there's a 1 here. Looks kind of weird. I'm just pulling some rescaling of the exchange momentum. So this is some integral. Actually, this integral, I don't know, maybe you're very professional on this stuff. Maybe you tell me that it's doable. You can, I don't know if you can do it directly, but I know that the answer is writable in terms of 2f1 hypergeometric functions. But I'll show you how we managed to find the integral. So we had way less ambitious goals. We wanted to understand for this toy model, how do we find the differential equation for this function f? And moreover, can we solve it efficiently? Okay, so this is the key point. So the observation is the following. So the measure is appearing as some sort of twisted power. So I'm going to assume that the value of epsilon is arbitrary. And I'm going to take epsilon such that I can always integrate by parts and throw away the boundary terms. And then at the end of the day, I set epsilon to whatever value I want and hope for the best, okay? So that's what we do in dimensional regularization. And by the way, the epsilon here is dialing the cosmology and is playing a very similar role to the gym-reg epsilon. I think that that's very cute because gym-reg modifies the infrared of the theory, and here gym-reg is modifying the long-distance dynamics of the theory rather explicitly. Okay, so, but the rest of the integrand is not an ordinary form. It's what's called a canonical form for some bounded region. It's the unique form that for a given bounded region has logarithmic singularities along the corners, the lower codimension corners of the region. So this is where this whole story of the cosmological polytope comes from. So the strategy is to exploit because of this factor, the twisted cohomology of the integrands, which is a fancy way of saying you should exploit the fact that you can integrate by parts and partial fraction the integrand. Okay? So there's a whole story about this coming from Amplitudes that I learned about it from Johannes Hen's lecture notes, for example. Some beautiful story, and it applies even more beautifully to these examples. So what's the idea? It seems like a crazy idea, but then it works. So you don't know how to solve one problem, you trade it for infinitely many problems. You consider the general set of integrals that have arbitrary powers, integer powers with the same twist measure, but now there are 5 lines in which the integrand can become singular. So if you look at the original integrand here, it only had these 3 lines, but because I want to integrate by parts at 0 and so on in the twist, I added the lines where it twisted. So now I have 5 lines in which the integrand can become singular, and I consider the general family of integrals that can only have these prescribed singularities. Now the fantastic thing that comes from, I don't know, some mathematical dark magic is that this set of integrals forms a finite dimensional vector space. And the size of the vector space is given by the number of bounded regions. So here, if you count, there's 1, 2, 3, 4 bounded regions, which means that if I take any 4 members of this set of integrals, if I do any operation on this set, it should be rewritable in terms of the set itself. Okay? So it's a finite dimensional vector space. In particular, if I take, if I take any 4 of them and I apply the differential, it should be proportional to the vector itself. So that's what will give me the differential equation. But now here, because there's even more. Now here, because the integral was given by a twist times a canonical form of certain bounded region, then the form of the integrand and the geometric arrangement even suggests the right way of picking the bases. Okay? This required some experimentation, but I'm telling you what happens at the end. So here's the idea. You twisted by these 2 lines, x1 and x2, and now you want to pick here as a vector of your 4 integrals. You want to pick the unique forms, these logarithmic singularities, these canonical forms, that for all of them, they hug the twisted line. So, for example, the original integrand was only this triangle here. But now this triangle doesn't touch any of the twisted lines. So I instead consider this bigger region, this square, because then it has boundary along the twisted lines. So I need to find 4 of them, so here's a way of doing it. I take a triangle, I take this hash region here, this other hash region. The important point is that all the regions hug at least one of the twisted lines. Okay? If you do that, then all sorts of amazing things happen. So let me start describing them to you. The first thing is that epsilon appears only up front. It comes from the fact that the total differential of the canonical form is a total derivative in the integration variables. So you can then integrate by parts. When you integrate by parts, you hit this measure. Therefore, you get something proportional to epsilon. And it's linear in epsilon. That's the only instance in which the cosmology will appear in this formula. Not just that, now you know the differential equation. Now it's just linear algebra. You take the function, you take its first derivative, its second derivative, its third derivative. At some point, you have 5 members of a 4-dimensional vector space. So they must be linearly dependent. That's your differential equation. All differential equations you want follow from linear algebra. Now, another thing is because this is proportional to epsilon, you can just hit it again with the total differential, and you will get separately that it's abelian flat, and all commutators vanish. Okay? So it's a very special matrix. And of course, then you can write a solution. For amplitudes, it's very useful because you're typically interested in small epsilon. This is some Dyson series. You just expand around some given kinematics, and then you find it to arbitrary precision. But here's the real magic. Here is the value of A. So it's because it's abelian flat, it's sum of D of stuff. All the stuff has logarithmic form, and the argument has to do with all the physical singularities that the correlator could have, plus the ones that are forbidden, that they will disappear from the answer because of the choice of initial conditions. Now, notice the cooler thing, it's triangular. If you add all of them up, there's nothing here in the bottom corner. What does it mean? It means I can solve for the bottom components, then I can feed it into the next line, I can feed it into the second line. So essentially, even though I was gunning for a matrix, all lines decoupled. Okay? So this is an accident of physics. If you look at another mathematical integral with same type of structure, but you twist the lines differently, this doesn't happen. Okay? This decoupling of the lines. Okay, so A is triangular, you can solve for each line, and okay, there's some explicit solution. It's writable in terms of 2f1s, and in the de Sitter limit, it's a bunch of logs and dilogs, and it's rational for flat space and radiation matter domination. And now the famous dimension shift formulas for amplitudes, they shift the cosmology. So you can relate a computation done in the Sitter space by a computation done in flat space, and so on. We had noticed this over the years, and it always looked like some crazy stuff, and this explains why. Because when you shift the cosmology, you're keeping yourself in the same space of integrals. So you're just changing the basis. So they must be related one to the other. Okay. So here's an outlook. So, okay, we computed some more sophisticated examples where the matrices have more entries. Same story happens. The integrand is a canonical form times some twist. You add the twisted lines. You count them. Even the counting problem is kind of cute how you do it. Involves some crazy algebraic geometry. And you follow the same procedure of trying to find bounded regions that hug the twisted lines. And you get the matrix A that is essentially triangular. And for this bubble, for example, the integrand, not the integral, you can write the integrand in terms of 2f1s again. This 5-point function, even though it's 25-dimensional, if you're brave enough, you can do it by brute force. Find the matrix A, it's triangular again. You need something slightly fancier than 2F1s to write down the answer. And you can do it for any value of epsilon, finite epsilon. Okay. So why is it so simple? And I don't really know the answer. One thing I can offer to you, so for example, if I just add the twist on another line and follow the same procedure, then the lines don't decouple at all, the matrix. I get some nasty 4th-order differential equation, which is what the naive estimate would give you. For those diagrams, you'd get a 25th-order differential equation. Doesn't look very usable. But the examples coming from physics have much more structure. One simple avatar of that, the fact that you can almost diagonalize, is that A has lots of eigenvectors that are independent of kinematics. So it allows you to find little blocks in which A has some diagonal-looking expression. So I will stop here. So I'm just leaving here a few things. These differential equations are really the way that we've been able to compute these cosmological observables reliably. Even at tree level, we didn't really have very good templates for observations. So they play a very important role in this cosmological bootstrap. I thought that they came from symmetry, but I hope I showed you in the toy model that the story seems to be more general. It shares a lot of structure with loop amplitudes in flat space, but the way you organize bulk perturbation theory in terms of these canonical forms even makes it obvious what should be the right basis for finding this flat connection A. So it seems to have some features that are highly desirable, and it's something that we didn't put in by hand. It was just given to us by the way we organize perturbation theory. And it gives me hope that we can actually use this machinery to solve some thorny issues in cosmology, understand the general structure of loop amplitudes in cosmology, to incorporate the effects of particles with spin, and so on. So that's all I have. I'm happy to take questions.
Thanks a lot. Do we have any questions? Yara here?
Yeah, thank you very much. Thank you very much for a nice talk. When you edit this twist, you can also look at it as adding poles at infinity in x1, x2. Is it possible to add them to the geometry, or do you have to always strip off this twist out?
I was assuming that I can always integrate by parts, so I was always using a value of epsilon for which I can throw away boundary terms at infinity and at 0. And then at the end, I can set epsilon to integers and stuff like that. Sometimes the resulting correlator blows up, but then it's wave function renormalization, and the coefficient up front is meaningful. So, yeah.
Okay, thank you.
Another question?
Could you comment a bit on the unitarity of the time evolution and the bulk? How is it imprinted in your correlator?
I don't know, actually. It's a good question. So now we know how to write cutting rules, for example. So this is, strictly speaking, not the observable yet. It's the Hartle-Hawking wave function of the universe. You specify some profile at late times, and you specify initial conditions. But there are some cutting rules, for example, that should relate this to some cut higher point tree-level correlator. And I haven't investigated how it's manifest in the structure of the matrix A, but I suspect it is. One cute thing, for example, is that you can see when you solve for a system like this that there is a small 4x4 block inside of this 10-dimensional matrix that is essentially related to the tree-level correlator. So I think that it should be related to these unitarity cuts, but I haven't investigated that.
Okay, if there's no more question, let's take Guillermo once more. So the last speaker of today is Paolo Benincasa, and he'll join us through Zoom. And so he's in MPI Munich, and he'll talk about geometry of perturbative unitarity. Paolo?
Okay, thanks a lot. And first of all, my sincere apologies for the technical problems, and thanks a lot for the opportunity to give this talk at the conference. So what I would like to talk about today is a way to try to understand in a completely unified way perturbative unitarity. And when I mean unified way, I mean flat space and cosmology at the same time. And in general, in flat space, we know, at least in perturbation theory, we know very well how unitarity together with other fundamental principles, such as causality and locality, how this constrain the functional form of our scattering amplitudes, and also the type of interactions that we can have. For example, we know that we can have at most poles and branch cuts. We know that there are the unitarity manifests itself in cutting rules, and unitarity and causality manifest also itself in the Steinman relation, which stated the double discontinuity across overlapping, partially overlapping channel vanish in the physical region. And all this provide both with the computational approach, like generalized unitarity or some bootstrap methods, but also a lot of knowledge about which processes can happen or not in flat space. We know, for example, that we can have just a particle with spin 2. We know that we cannot have long-range forces which are mediated by particles with spin higher or equal than 3. And even if there is still a lot to investigate about, especially about causality in how what's the rate of causality in the scattering processes, the picture is allow us a lot of knowledge, and so it's also a good question to ask how much of this we can extend to more fundamental processes, like could be what happens in expanding universes. Because in general, also there, one of the assumptions is that the evolution, it's both causal and unitary. So one would like to have an imprint, would like to know what's the imprint of these principles on the observables, and therefore if they can provide both constraints or both new tools for computation. Guillermo in his talk already made a small introduction, so I will be very brief about it. Again, as he mentioned, what we really care about are correlation function at the end of inflation or at the Big Bang, because from them, they are the seeds from then the structure formation and the CMB. But they also are the result of a cosmological evolution in a period of accelerated expansion, which is called inflation. So typically, what we like to compute are spatial correlations of certain fields that can be, for example, a scalar. We know that which is called curvature perturbation. We know it's the seed for the temperature fluctuation of the CMB and the distribution of galaxies. Or one of the prediction of inflation is that the gravity mode is going to be the seed for polarization in CMB, what is known as B modes that was supposed to be seen in the bicep experiment. So one would like to know what's the imprint of these correlations or other general correlation that you can imagine at the end of inflation of this basic principle, because in a sense you would like some general rules that a sufficiently physical theory needs to satisfy. Now, when you think about the correlations, you can either try to compute directly or also you can think of them as coming from some probability distribution of the field configurations that you are caring about. And this field configuration is actually nothing but the modulo square of the wave function, which describes the quantum mechanical system here during inflation. Now, as a general definition of this wave function of the universe, you can take it as an evolution operator acting on a vacuum and leading to your configuration that you want to measure at the end of the inflation. And this can be also expressed in terms of a path integral. Now, in general, there is a specific choice for the vacuum that is made, which is called bunch evasive vacuum, that substantially tells you that when you go to the infinite past, your modes behave as plane waves. So you can do perturbation theory, you can have schematically an expression like this, and as Guillermo already shown in talk, each of the term that here indicate in red X, psi, and L are the so-called wave function coefficient, which is nothing but the function that you attach to the diagrams. And in general, we know things that we have learned is that these quantities has to satisfy some basic properties. For example, they can have just singularities in some of the modulus of the momenta, which means that you are not allowed to have difference of momenta, which this is called folded singularities. You know, if you take the sum of the momenta of all the external state, your wave function reduces to the flat space scattering amplitude. Or you know that if you take the total energy of a sub-process, your wave function is going to factorize in a product of a lower point wave function and the lower point wave function, lower point scattering amplitude. And also we know there are Steinman-like type of relation. But the general question is that we don't know really all the origin of these properties. We know, as I said before, that in flat space, some of them come from unitarity, some of them come attached to the interplay between unitarity and causality. But in this case, we know that they are there because they can prove it, can be proven by heuristic arguments, or also there are concrete graph by graph proofs. But we don't know if they are the consequence of any of these basic principles. So in this talk, I'm going to focus about unitarity that has been already explored by other groups. And the basic statement of unitarity, again, you can imagine the interacting part being an evolution operator, which sends you your vacuum to your field configuration at the end of inflation at your boundary. And this evolution, it's you assume it that it's unitary. And typically, evolution operator is, as usual, as in a standard quantum field theory course, defined as the time ordered exponential of the integral of the interaction Hamiltonian. The only difference with the usual case is that our integral goes from minus infinity to 0. Now, this is actually a problem at minus infinity because you know that the modes are going to behave as exponential with positive frequencies. So you need to regularize it because otherwise you have infinite oscillation. The only criteria that has been used so far for doing this regularization is convergence, and typically the control integration was modified by this I epsilon around minus infinity. However, this is if you want to understand the consequence of unitarity. It turns out that this breaks, makes this deformed operator no longer unitary, and therefore you need to look for a different type of regularization. You know, the reason for which there is actually a physical reason for which this breaks down. That this operator is non-unitary, and the reason is that the operator is the physics is no longer time reversal invariant. In fact, if you look at the standard quantum field theory in flat space, where you have the integral from minus infinity to plus infinity, then the contour to plus infinity is actually regularized with a different I epsilon prescription. And you see that when you take the Hermitian, then you get that it coincides with the inverse. Okay, so there has been a proposal to have such a deformed operator which actually preserve unitarity. And this has been done by Baumgart and Sundrum. And the suggestion is not to deform the contour integration, but to just deform the Hamiltonian, preserving is leaving it Hermitian. The point is that this is not the only choice. This is not the only possible choice. There is a plethora of choices. So one can wonder if there is some general criteria for picking, for example, one might look also for some I epsilon prescription, which actually has something to do with causality. I will not enter that discussion so far. I will just stick to those deformations which are compatible with unitarity. Now, so let's say that we pick one we like the best. So there is one of such deformation, and so the general property is that U dagger is equal to 1. You can still divide in the interactive part and the free part, and you get a very similar equation to what you get for in standard flat space. So if you sandwich now with the external state, one thing that you get is that while the left-hand side is really the wave function coefficient that you're looking for, the left-hand side is not this complex conjugate, but rather it's the complex conjugate of a process which sends you from some state to the vacuum rather than vice versa. In other words, you have to reverse the direction of the momenta. And also there are some Cutting rules that I will make as reference in his talk, and I will I will show in one second. But these Cutting rules actually turns out not to be unique. So if you like, there are two things to understand: how to properly do the I epsilon prescription, and how to understand this non-uniqueness. And as you see, this looks very different from.
Paolo,
yes.
We have some. I mean, we can hear that you have some guests. I think. So do you need some? Do you need a minute to open the door?
Just 1 sec. Sorry for that. Okay, so so on the left-hand side, you have something that almost recalls the imaginary part of the amplitude, but it's not. It's just some, and also this is a consequence of the fact that you don't have time translation invariance. And on the left-hand side, you actually have, yes, a combination of lower point objects, but this by no means is something that tells you that you are crossing a discontinuity. So this is really a functional identity. What happens is that if you take seriously this functional identity, then you will never reproduce the correct flat space limit. You will get 0 equals 0 because on both sides you don't have the total energy singularity. However, so you can then a posteriori try to introduce properly the I epsilon. But if you do it naively, then you will get some inconsistency. So there is a way for which it's important to understand how to extract all the information out of this equation. That function is correct, but in principle, first of all, doesn't make clear why there are many cutting rules, and second of all, it doesn't make clear how to understand how to extract the total energy, the flat space cutting rules. And this left-hand side has this peculiarity that while the wave function has the actual physical singularity, the other one has folded singularity. So the one that I said that is made by difference of energy. So it's not really it doesn't have any physical singularity. Okay, so in order to clarify this issue, I will pick the same type of toy model that Guillermo was talking about, which is you can think about it as a flat space, a massless field in flat space with a polynomial interaction which are time dependent. You can use a Fourier transform to use an integral representation to push until the end the choice of the specific cosmology, because the specific cosmology is precisely contained in this function. And then you can represent diagrammatically in this way the wave function, where GR is the propagator, which is 3 term, 2 are the standard Feynman propagator, the third one is the boundary condition. And so you can ask this very same question on this integrand, because then anything that you can say here, then you can see how through this integration maps to your final actual cosmological wave function. An interesting fact is that the poles, the singularities, the physical singularities of the wave function are actually associated to subgraph, which means that if you consider a subgraph, you can associate a total energy for this process, which is given by the energy of the external states plus the energy of the edge that you are cutting by considering this process. So in a sense, it's very similar to old-fashioned perturbation theory, with difference with which has you have just plus signs. So as I said before, the beauty of this model is that starting from a very simple toy model, you can actually extract information about a larger amount of theories. Now, another beauty is that this model has a geometrical description. Let's take, for example, this simple graph where this x1 is the sum of the external energy at this vertex, x2 is the sum of the external energy of this other vertex, and y is the energy of the state that has been exchanged. You can pick these 3 as coordinates of some space, which is a projective space, because then you look at the equation associated to the subgraph, which are all homogeneous equation, and in this space you can see that they cut out a polytope, in this case a triangle. To any of this figure, in this case it's just a simple figure, you can associate a differential form with singularities along the sides of triangles, along the boundaries. And in this case, this is simplex, so it's very easy to write down. You can take whatever arbitrary graph and do the same. Create a space which has as projective coordinate all the labels for the vertices and the edge of the graph. And then for each of the edge, you have 3 vertices, like in this triangle. And so the collection of these 3 vertices per edge, the convex hull gives you what we call the cosmological polytope. Again, to all subgraphs of this, of whatever graph you have, you can correspond the denominator of the associated canonical form, while the numerator can be actually fixed by requiring that, by looking for the locus of the intersection of the planes which contains the facet outside of the polytope, which a mathematician call the adjoint. And this is something that we know how to do for the cosmological polytope. So this coefficient that now is in red is actually the wave function. Okay, so there is this correspondence. When you compute this canonical form, you know the coefficient, the canonical coefficient is actually the wave function. Now, an interesting fact is that we already in the past with Nima showed that if you look at the particular facet which corresponds to the total energy singularity, and then you look there to the singularity structure, the structure of the vertices of this facet tells you that it factorizes in 3 pieces. 2 are given by the flat space amplitude, lower point flat space amplitudes, and then there is a simplex which gives you the measure for the Lorentz invariance phase space. So we had already an understanding of how to read off the flat space cutting rules from just looking at the specific boundary which contains the information about the scattering amplitude. I won't explain what this circle means because here the drawing is just for showing that through some diagrammatic marking, we can actually study the vertex structure, and you can answer this type of question. We can discover that what is the vertex structure of each facet, and therefore, in this case, we can read off this flat space cutting rule. Now, when we go, so the question is now, let's go back to the what is called the cosmological optical theorem, that equation that I showed before with the psi star equal to a sum of cuts. And one thing that you can learn is that that object has 2 classes of singularities: the physical singularities and the folded singularity that here correspond to this. If you see my my mouse, these lines which go internally to the triangle, but they do not have the total energy pole. So it's a non-convex polytope. In this case, it's a non-convex square. This is actually very general. I draw this because it's the only things I can draw. It's one of the few things I can draw, but you can do this analysis very, very general. And so really, you can define this in an independent way, knowing the 4 vertices. Now, once you know that this cosmological optical theorem has to be encoded in this non-convex square, you can start to answer the 2 questions we had. First, how can I understand the different cutting rules? And second, how can I get properly the flat space limit, and therefore, how can I implement properly the I epsilon prescription? Let's start with the first question. So we have this square. Now, what we do when we want to separate an object, we can triangulate it. So you can see that if you triangulate it considering this red line, so you have the triangle with the these sides and the red side, and and then you have the white triangle. This precisely corresponds to psi plus psi star. And then you can start to triangulate differently. Another regular triangulation is just dividing with this other red line, which gives you this other cutting rule, which is still unpublished. And then the one that actually comes from the previous work on this cosmological optical theorem correspond to something a little bit more convoluted, which involve 4 terms, which all of them sharing this line. This is line y equal 0. Now, so the answer to this question is that you have some object, and then all the possible way of triangulating it correspond to possible cutting rules, while the only way in which you can separate it in such a way that they share the total energy boundary, even if it's not a boundary of the full object, it's what gives you psi plus psi star. Now, so let's ask this other question about how the flat space cut rule emerge. As I said before, if you take some function which doesn't have the singularity, and you take the residue, you obviously are going to get 0. In this picture, what does it mean taking a residue or taking some limit? It means that you have your object, this non-convex square, and then you consider intersection with the line given by the equation that you are interested in this case, the total energy. You can see that this line crosses the intersects our polytope in just 2 codimension 2 terms, which tells you precisely the distributional meaning of the flat space Carter rule. And what you have is that you obtain the flat space Carter rule precisely summing over the canonical form associated to this point. Now, I write it as 4 terms rather than 2 terms, just to make explicit the fact that when you take x1 plus x2 equals 0, 2 of them become equal in pairs. But otherwise, it's just a sum of two terms. And in general, for an arbitrary graph, you have precisely that this mechanism gives you automatically this codimension 2 distributional piece, where you need to sum over the possible singularity, the possible canonical form of this codimension 2 singularity that this plane intersects. So I'm about to finish. So why this is crucial? Because if you take with the correct I epsilon prescription on the left-hand side of the cosmological optical theorem, individually the total energy pole, you see that they are indeed the same function, but with different epsilon prescription, and that's why then, considering it, you have the imaginary part of the amplitude. This is a very nice way to just implement, without caring about the epsilon prescription, explicitly, to identify this fact that you have some extra term, which is codimension 2, which is not a function. So, so if you want to make explicit the I epsilon prescription, you actually can, and you just have to resort to a contour integral representation for the canonical function, which actually has an embedded I epsilon prescription that I'm not gonna show. But the beauty of this language is that at once you know how the cosmological optical theorem contain the flat space Carter rule, in a sense implements correctly the I epsilon prescription, at least compatibly with unitarity. Now, so let's wrap it up. We started with the 2 general fundamental questions, which are what's the imprint of basic principle, and what is how the imprint of unitarity in flat space is encoded in the imprint of unitarity in cosmology. We see that in principle there are some subtleties in dealing with the I epsilon prescription. Interestingly, the one that I showed at the very beginning, introduced by Baumgart and Sundrum, correspond to what is being called by Sebastian and Sofia Nesdottir the kinematic I-epsilon prescription, which means that you just shift the actual final invariant variables. And it's interesting how in this geometrical language, without ever talking about the I-epsilon, we are able to reconstruct all the results that necessarily require the correct I-epsilon prescription. Indeed, this is not the end of the story whatsoever about the I-epsilon prescription. The important point is still, I mean, there is still a careful analysis of the I-epsilon contour has to be performed, and there is no mention whatsoever about how causality is encoded in this language. If there is some criterium to choose how causality select some I-epsilon prescription rather than another one. And so I think that this point of view start a little bit to clarify how things are encoded in the cosmological observable, and how it's actually related to the flat space limit. And so the last remark is that, as you can see, there is no mention whatsoever about unitarity causing or be the cause of the characterization property that I mentioned at the very beginning. So a general question is that what is their origin, if there is some other principle, or maybe causality or something else, which actually is responsible for them. And I stop here.
So thank you for your talk. Do we have any questions?
Hi, Paolo. It's Guy here.
Yes.
So does this I-epsilon prescription commute with isometries? If I hit the resulting wave function, say that I tune things so that it makes sense in the Sitter space, and I hit it with special conformal transformations, will it be invariant under conformal transformations?
To be honest, I haven't checked it, but I suspect that it does, because this the one at least coming from the cosmological polytope preserve the symmetries of the cosmological polytope itself.
Okay, because the Baumgart-Sundrum one doesn't, naively I wouldn't expect it to preserve it. Now, if I may, another quick question. So, am I understanding correctly that we do this computation in the physical sheet, but then if we want to interpret it for any values of the momenta, there's some I-epsilon hiding that we shouldn't have left out in those denominators of E total, E left, E right, etc.?
Yes, that's correct. I mean, when you do this manipulation, you really need to be careful about the epsilon prescription, because if you don't keep it and you take the total energy pole in this cosmological optical theorem, you get 0. If you keep them, then it's a matter of order of operation. If you just manipulate them, you can make it disappear with a specific choice for the I epsilon. But in general, if you before take the residue, then you see how it affects the epsilon prescription. You see that precisely you tend to recover really the correct epsilon prescription that you have for when you get the imaginary part of the amplitude.
Thanks.
Any other question for Paolo? Okay, I don't see any, so let's thank Paolo again, and let's thank all the speakers of today. And that concludes today.